Uh, Hello. Hi, good morning, Professor Ichu. Can you hear me? Uh, I think, Professor, your mic is mute, I think.
Uh, can you hear me now?
Yes. Okay, great.
Yeah.
Okay. So, good morning and welcome actually for the talk.
Morning.
So, currently there is a plenary talk is going on.
Okay.
So, that's why it
That's
is
fine.
until, yeah, so it is until 11 o'clock. And after that, we will be starting our session.
Sure, no problem.
So, please hold on for some time.
Okay. I'll
Thank
just
you very
stay
much.
here. Okay.
Also, I think Professor Wooty Park is also there. Can you listen to me? Hello, Professor Park, are you there? Uh, Hello, I cannot hear Professor Park. I think.
Can you hear me now?
Oh, yes.
Okay.
Hello.
Hello. Can you hear me?
Oh, yes.
Okay.
Now I
Good.
can hear. Okay,
Good.
so also welcome and good morning to you, and nice to see you after a long time.
Yeah. I like your mustache.
Eh?
I like your mustache.
Oh no, it is because of this COVID situation. Actually, we the only thing IIT professors are now experiencing this stretches nowadays. Lot of them. Okay. So actually, there is a plenary session going on, and it will be ended at 11 o'clock here. So maybe we will start our session in 10 minutes. I hope my voice is clear. Is it?
Yeah, very clear.
Okay.
Very good.
Thank you. Manu, can you switch off your mic, please? Okay, so those who are in this session, so let me tell you that if you have login with this and you can see your names in the in the box, right? So I accept the invited speakers. All of you should be switching off your mic all the time, because if you speak, then you are in this box where you can also interact. So for the rest, I think they are login with the another link, and they cannot speak actually, but you should be careful that your mic is off in the if you are logging with the main link. So only invited speakers will speak, so please be careful. And we will be starting our session maybe within a few minutes only, because the plenary talk is still going on. So just wait 1 or 2 more minutes. So Professor Chiu, can you share your slides? Let's say, I hope your mic is off, sir.
Okay.
Okay, please.
Can you hear me now? Professor Singh?
Yeah, now we can hear you. Yes.
Okay. And do you see my slide?
Yeah, I think it is coming. I think the slide is still not there.
Okay. Let me see. What should we do?
So the screen got changed, but the slide is not visible. So
What do you see now?
now I can see your video here.
My video. You are being. Do you see my slide?
Actually, I think your cursor, your cursor is visible, but
and MOCVD epitaxy, fabrication and characterization of semiconductor material and devices. This include nanostructures and low-dimensional structures, quantum wire dots and wells for nanoelectronics and nanophotonics, based on the groups of 3 nitride and 3 oxides. So he is the IEEE senior members. So with this introduction, I invite Professor Hedin Sir to deliver his talk.
why there is this sound coming in?
Hello.
Yes.
Hello, Lena, can you hear me?
I think so.
I can see your slide.
I think so. It's get mixed with some other. I let me check, sir.
Yeah, we can hear.
Can you
Okay, so thanks very much for invitation and for the introduction, and hopefully
just
some of our recent progress in the work of aluminum gallium nitride-based UV optoelectronics, mainly on the light emitting diodes. So I'm from University of Science and Technology, China, and in the School of Microelectronics.
Professor Singh, what's happening here?
First of all, I would like to share some motivations and why we wanted to work on.
Hold on, there is some cross link
and the devices. As you may notice recently,
Okay, so Vaibhav, are you there? Acha, okay, can I ask Icee double E host? You are here now?
Sir, I told him to a host guy who is tackling this technical.
Okay, now it is fine actually. So Professor Chu, can you try to share your screen now?
In between 200 and 280.
Okay, let me see.
And the second will be your ultraviolet B.
Do you see it?
280 to 315.
Do you see my slide?
UVA. And due to the high energy of the UV
Professor Singh?
I think when you try to share, I think this adds to some other
and indeed verified can kill the bacteria. And
I'm sorry,
besides those,
somebody else is talking.
Yeah. So I think there is some
such as curing and biomedical
Let us we are just checking with our technical team. Just hold on.
Okay.
Conventional UV sources such as mercury-based lamps, there will be tremendous market for us to explore for the UV LEDs. But however, right now we need more efficient UV LEDs in order to reach as high efficiency as like a blue LEDs in order to be finally commercialized. And particularly in our daily life right now, we encountered with tremendous challenges in the healthcare. Right now, the coronavirus has been spread out globally, and it's been a big challenge for us. Especially we have such a large number of cases and a lot of deaths caused by this disease. So.
Hello.
It has been proved that the UV lamp or the UV LEDs can easily kill, particularly in a special wavelength. For example, 280 nanometers can kill almost 99.9% of the coronaviruses by using the UVC light. And many studies have proved that, and a lot of publications and literatures or reports coming out recently. And besides the UV, and traditionally we use alcohol, chemicals, or heat to be used for killing those viruses. And hopefully, what we want to do is we to replace the mercury base or the UV light, because UV light basically is a non-contact method or approach to kill the bacteria. And we conventionally use the mercury lamp, but it's fragile and toxic, and it's like short lifetime. Most important, it's like just like the right now the blue LED is continuously replacing the light bulbs right now in our market, and but it is a similar scenario for the UV LEDs. We wanted to make efficient semiconductor robust LEDs and to replace those mercury-based. And there's a lot of advantages of the UV LEDs because they have lower energy consumption, and they have very little amount of heat, and this is environmentally friendly and without involving any mercury.
Professor Chu, can you stop sharing the thing, because when you stop sharing, then only
the spectrum of the UV LEDs can be tunable based on the materials we choose. And
I think it is still so. Professor Chu, can you share your slide with me? Maybe can you email your slide?
Yes.
Then I will share.
Semiconductor community, and hopefully we can continue to improve the LED performance. And the most popular basically is one of the best.
Can you see my slide?
For making those kind of UV LEDs is based on the nitride. It's a conventional.
I think there is still a crosstalk is there. So there is some problem. So maybe in the meanwhile, can you please email your slide to me?
We can basically.
Let me see.
The opportunity is we can easily tune the band gap.
Oh, I think that mixing is now at least not there.
In the P-type and N-type, and importantly, they can be grow heteroarchitecturally on different chip substrates such as sapphire, silicon as well. And unfortunately, when the wavelength moving down,
Can you see the slide now?
to 250,
Yes, your slide is still there. Yeah, we can see your slide now. Actually. Yes.
like 1 or 3%. This is dramatically.
Okay, so you can see the slide.
Yes. But there is some sound is also coming from some another person actually.
Yeah.
So let me ask the technical team actually.
And right now the QE is determined by IQE and light extraction efficiency. So we have
Just wait. Now your slides are fine. Just wait for 1 minute.
and LE respectively in order to continue
Let me
to improve the external quantum efficiency.
Yeah.
And right now, only Raychem report DPUV LEDs with about 20% EQE, but it's in the lab scale. It's not in the commercialized or the industry widely used. And typically, from different industry or the manufacturers, the most of the EQE of DPUV is from like below 5%, 10%. And normally, what we bought UV LEDs or we in our lab, we make about only 3 to 5% EQEs.
Okay, so Professor Chiu, I think let's wait for 1 or 2 more minutes. They are checking now.
Challenges have to be overcome, including material-wise as well.
Sorry, I cannot hear you.
So it's basically in.
I'm saying that please wait for 1 or 2 more minutes. I think they will solve this issue.
Structure. It's like
Oh.
constructing a building.
So,
Architecture. So we have to optimize.
Should I talk or not?
And including the.
No, just hold on for a few minutes.
Okay.
Or
I'm sorry for this. For the
in this entire building in order to make sure that this device works. So including the N-type layer, active region layer, and electron blocking layer, and P-type current injection layer. So later on, I will divide into 3 sections to discuss about what we can do to improve the device performance. First of all, we propose to grow the aluminum gallium nitride on the large miscut sapphire substrate. And why? And
So, Professor Chu, can you speak now? No, your mic is off. Your mic is off.
significant difference. And that's why I naturally create a so-called compositional inhomogeneity inside.
Do you hear me?
And naturally,
No, actually, I think in our session, I think someone is also login to the another link. So can you please check whether some of you is now logging with another link also?
Very efficient to
That
localize
is why we have a cross link.
without leading to a very high radius recombination inside the wavy or the composite inside.
So can you please check that you are only login with the same with the only link with to this person? Because I think some of you is having login to 2 links. That's why there is a problem. Yes, Professor Chu, can you speak now? Your mic is off, Professor Chu.
As shown in the TM here.
Can you hear me?
Similar to the in-game quantum wells, which we hopefully to create.
Maybe I think there is some maybe I can ask Professor
and they being
maybe,
generated.
Professor Woody Park to share your slide actually. Because let us see if this problem is only with you or with others also.
We grow the 2 types of devices. One is nearly flat substrate, and another one is large miscut sapphire substrate.
Can I request Professor, can you stop sharing your slide?
Can you hear me now?
On the film.
Or maybe I suggest you please log off and then log in again.
And we can clearly.
I'm sorry, I cannot hear you.
Can you please log off and then log in again?
Okay. Sorry about that.
I'm sorry actually.
Mr. Chu,
Yes.
Mr. Ye, please do one thing.
However,
I think-
when we go to the example,
Hello?
How do I log
we clearly
out?
observe very
Yeah, is there any another window you have opened? I think he opened two windows together.
No, I think he just logged off actually, and he's logging again.
Yeah, he logged off now, but he's using two windows at the same time. One is on WebEx, and the second one is front end. And
Okay.
there is 25-second delay. That's why the double sound is coming. So
Okay.
tell him do not use two platforms at a time.
Okay. Okay.
Okay, thank you, sir.
Sorry, I'm back.
Oh yeah. So can you please
sorry.
share your slides now?
Let me see.
So I think there was some problem because I think you were logging with two windows, I think.
Yeah. I just realized that it's all my fault. I'm sorry for that.
Okay. So no problem. So now we can see your slides. Very nice.
Okay. Yeah.
Okay. So sorry for the technical, problem happened, and maybe I can. So before I welcome you all in this session of our MEMS, NEMS, and microfluidics. So in the first, talk, we have Professor Yi Chu with us, and he's professor in Department of Electrical and Computer Engineering, National Cheo Tung University, Taiwan. And topic of his talk is inductive CMOS MEMS accelerometers with oscillator based readout. So in this talk he will be talking about the importance of CMOS and MEMS, integration and their close relationship. So we know that when we develop the sensors, right? So their integration with the CMOS circuit is very important. So then this in this move actually, he will present some CMOS MEMS accelerometers that they have developed in last few years, and in particular oscillator-based readout circuits, which were used to simple topology and quasi-digital output. So let us welcome, Professor Yin Chu, and we hope that with his knowledge, we all will be benefited after his talk. So, Professor Chu, you can start. And
Okay. Thank you very much, Professor Singh, for the kind introduction. And I first want to apologize for causing all the problems of these online meetings. So my talk today will be in inductive CMOS MEMS accelerometers, meaning we measure the accelerometer by using a variable inductor. And these are my students, and also the last one is Professor Hong in our department. He's an expert in IC circuit design. So in our collaboration work, I'm responsible for the sensor design part, and the Professor Hong is responsible for the circuit design. And this is the outline of my talk. We can skip that. And we know that sensors or micro sensors are being used in our daily lives. For example, in the smartphones, we have already more than 10 sensors in our phones, and it is projected that in 2021, which is coming, there will be something like 20 sensors. So as Professor Singh just mentioned, that for each sensor, we actually need some kind of a signal processing or signal buffering or something, so that the response from the sensor can be sensed by or read by the control unit, the CPU of the smartphone, of the computers. So we do need an interface readout circuit. And so there are different ways of combining a sensor chip with IC chips, or the integration of the two. And one of the method to integrate MEMS and CMOS circuits is by monolithic integration, meaning that we fabricate both the sensor and the circuit on the same substrate, on the same chip. And on the left is a classic photo of accelerometer developed by Analog Device. And you can see in the middle here, the blue part is the sensor, and but the majority of the rest area are actually occupied by the signal processing circuits. So it is very important for this circuit to functioning correctly so that we can do some signal processing functions such as noise cancellation and amplification of the signals. So with all these circuits around, we can actually sense the very small input accelerometers. So that's the advantage of integrating the MEMS part and the CMOS part on the same chip. But if we actually want to use this approach, and then we have to design and fabricate our sensors using all the CMOS layers, CMOS materials, and most importantly, it has to be compatible and it has to be consistent with the design rules of the foundry, CMOS foundries. So on the right is another photograph of a CMOS MEMS accelerometer, and you can see the moving structure is here in the center, and there are sensing fingers, cone fingers, capacitors on the left and on the right, and there are springs over here, and all these structures are actually very thin mechanical structures. And because these are laminated lamination structures of various oxide and metal films in the CMOS process, so there are many residual stress issues which can cause the structure deformation or curling for the thin layers, such as the springs here. And if you actually look very detailed at the sensing cone fingers, they can also be curved. So we have to deal with this and we have to solve this. There are some technique, some structural design methodology to reduce the effect. But if we actually look at the cause of such sensitivity to residual stress, let's see in the capacitive sensing, we use capacitors. And we know that one capacitor has two electrodes. For example, on the right is a schematic of a cone finger capacitors, and the two electrodes are anchored at two different locations here, and the other electrodes are anchored at here. So we hope that these two sensing fingers are flat structures so that their overlap area is the maximum, which is the sensing capacitance. But if the residual stress causes to bend, then we can see that the overlap area will be dramatically changed. And in this particular figure, only the central part is effective in sensing. So such a structure is very sensitive to stress-induced curling, and it will reduce the sensitivity, and also it will affect the yield. So we think if we cannot avoid the stress issues, and if we have to face the curling situations, then why not design our sensing structures by anchoring the sensing structures on the same side instead of on the two sides of your sensing structures. So in these diagrams, I show a very simple single loop inductors. And we know that if we pass a current from here and it flows back around here, then this loop becomes an inductor. And if the inductor itself is deformed by the residual stress, and we can see that the inductance, which is mainly determined by the area enclosed by this particular loop, the area will not change a lot in contrast to the sensing structures, which depends on the overlap between the two deformed structures. So we hope and we think that if we use such kind of sensing structures and use a inductor as our sensing element, we should be much robust with respect to the stress-induced problems. So in the past, we have introduced these novel sensing ideas, and we have do some experiment. And in the following, I will show you some of the results. Okay. Yeah. Let's see. Okay, so first is a finite element simulation. We do a simulation for both on the deformed capacitor and the deformed inductor. So you can see this is the structure that we simulated. And on the left is a capacitor. So it has two sets of electrodes. One is red, the other is green. But on the right, is a meandering inductor, which is actually a single piece of structure. And we put a underlayer to introduce the residual stress to cause the deformation of the entire structure. So for the capacitor, we can see that after deformation, this is a deformed structure, and we look at the electric potential distribution in three directions. You can see that there are actually very complicated potential distributions, and also these very complicated distributions change a lot when the fingers, the cone fingers are deformed. But we also make a meandering inductance structures, and we put the same stress to cause it to deform, and we look at the magnetic field distribution or magnetic flux density distributions. We can see that on the lower right corner, the magnetic field is actually relatively uniformly distributed along these sensing structures, and this distribution, the magnetic field distribution, also does not change a lot when the structure deforms. So from either the magnetic flux distribution or from the potential distribution, we can calculate the capacitance and the inductance as a function of the deformation, which is shown here. So you can see that on the left is a variable capacitor. As we apply more and more negative or compressive stress, we have a significant decrease of capacitance, but in the same time, the inductance of the meandering inductor hardly changed. So it is from the simulation, we note that the inductive sensing element is much robust when there is a residual stress in the structure. So we put this variable inductor in our accelerometer. This is a schematic showing the operation of the accelerometer with a proof mass here. And usually the proof mass is anchored to the anchor by a meandering spring. So we have the meandering spring on both sides. So this part is mechanically a spring, but we can also run a metal wire along this meandering spring and route it back, so it forms a loop. So it becomes a single loop wiring or single loop inductor. So this part is actually both mechanically a spring and electrically a meandering inductor. So we call it a spring inductor. So when this proof mass is subject to a external acceleration, it moves to, say, the proof mass moves to the right. So it compresses the spring inductor on the right and to reduce its area. So in principle, the inductance will be decreased because of a smaller enclosed area. But at the same time, the left spring inductor will have a larger area. So it has a positive change of inductance. So by these two inductors, we actually have a differential pair of variable inductors, which enable us to do differential sensing. So now we have a inductor, and we put this inductor with another fixed capacitance, and this forms a LC-based oscillator. And we have a oscillation frequency F, and this oscillation frequency will change with the change of inductance. So we built two, because we have a differential sensing inductor, so we can build two differential oscillators, which has a frequency of F plus and minus delta F, and we mix them together to eliminate the common part of the frequency, and we low pass it, and we get this is output signal. So our signal is actually not voltage, not the current. With our signal, output signal is the frequency of the oscillator output. And we do a simulation of the inductance when we apply the different deformation to the capacitor, to the meandering inductor. So we can see they are quite linear. And so this is our readout circuit. As Professor said that the readout circuits and the sensing structures are designed and manufactured on the same chip. And this is a schematic of the LC tank-based oscillator. This is our sensing inductor, and this is a mixer which mixes the output from two differential oscillators. So you can see that one output of the output of one oscillator goes in here, and the output of the other oscillator goes here, and this is output of the Gilbert cell. So we design our sensors with the sensing circuit here. So in principle, this is our sensing structures, the moving mass and the inductors. And when we get this from TSMC, we do post-process to release our movable structures. So the first we do is put another layer of photoresist, and we etch vertically to remove the arc between the mass, and then to expose the surface of silicon wafer, and then we do a undercut isotropic etching to release this movable structure, the sensing structure. So this is a photo of the one-axis device. You can see this big part is the proof mass, and we have a meandering spring here, and we can use the entire area of here as a proof mass to increase its mass and to increase the sensitivity of the device of the sensor. And as I said, this one and this one here are two differential inductors. So we have oscillator 1 and oscillator 2, the two differential oscillators, and this is a mixer output. So we measure our device. On the top left figure is the output of the oscillator before mixing. So we can see that the oscillation frequency of the LC oscillator is about 2.7 gigahertz. And so we this is one oscillator, and we mix them together. We got output from the mixer or the Gilbert's cell, and then we take that frequency and we measure. So on the left is a electrical measurement, and on the right is mechanical measurement. So we measure the frequency as we turned our sensor around in the gravity field. So we turn it around 360 degrees. We can see that the output falls quite nicely on a sinusoidal curve. And then we can fit our measurement data point with this sinusoidal curve and find out the sensitivity of our device. So this is a static field, a static measurement. And we can also do dynamic measurement by mount our sensor on a shaker, and then we shake the sensor with certain frequency and a certain amplitude, and then we can measure the dynamic response with respect to frequency and signal strength. So here you can see all these output frequency data are actually acquired by using a counter, an external counter. And from this experimental data, the blue dot, we can do some signal analysis to find out the signal strength, to find out how much noise we have, and identify whether there are interference from the power line or some other sources. So anyway, I will talk about the performance numbers later. And as we've shown, this is actually one single axis sensors. It only sends acceleration in this direction. So we want to do a 3-axis sensing by using a single proof mass. So this is our next design. The mass is in the center, and you can see that we put 8 sets of sensing inductors on each side. And so this is a horizontal x-axis. You can see these two Lx plus and Lx minus are the two differential sensing inductance for x-axis directions. And these two are for y-axis directions. And by using differential sensing, we can effectively remove or eliminate the cross-axis sensitivity. For example, if the proof mass moves to the right, and the right inductor will be decreased, but the left inductor will be increased. But the top and while the top and the bottom induction will be changed, but they will have the same change, either become larger or become small simultaneously. So if we do differential sensing, we take the difference from the output of these two vertical sensing elements. They will give you, ideally, they will give 0, meaning that there is no component of acceleration in the y-axis. So that's how we do 2-axis sensing. How about the third, the z-axis sensing? You can see that here we have some inductors in gray scale, and that means we stack the different metal layers in the CMOS structures differently. So for example, these are very light gray part, and this is a darker light gray part. And that means in our particular, if you look at here, so the top layer of these two, of this particular part is made of M6 to M5, which means it is very close to the top surface of the chip. And this part, the light gray part, is composed of only M1 to M4, which means it has a lower position in the vertical direction. So, and you can also note that in this particular direction, I'm sorry, if we look at this inductor and this inductor, this one has a top, this one extended. If we go out from the mass to the anchor, it will start from the higher position to the lower position. But for this particular inductor, it will start from a lower position in the z direction to a higher position. So they are slanted. Their surface plane is slanted, but they are slanted in different ways. So to see it more clearly, let's see here. So on the left is X or Y sensing. The middle is the proof mass, and on the side is the cross-section of the sensing inductor. So this is what I just described. We have a different change of area here and a differential change of inductance. But in the Z direction, we can see that originally they are slanted from the proof mass to the anchor differently on the two sides, and in the rest position they have the same area from B to B prime. But if, say, the mass moves downwards, and then the right sensing inductor will have a smaller area, but you can see that on the right, they will have a larger area. So this is also a differential change of inductance. So we build these different numerous sets of sensing inductors and the sensing oscillators. And this is also, first we do a finite element simulation. This is a planar horizontal movement. We can see there are linear change in the X or Y direction. And we can also deform the inductor in the vertical direction. And you can see that for different Z axis sensing inductor design, they all have opposite slope, opposite sensitivity. So that's how we do differential sensing. And this is a photograph and SEM. And in the lower part, you can see that this is the X sensing inductor. You can see they are all stacked up to M6, the top metal layer. But for the diagonal sensing inductance, you can see that this is from top metal M6 and goes down to lower only M4 in the top. So it goes down from the proof mass towards the anchor. Okay, that's how we do this slender surface. So we measure the response, the sensitivity. We measure their mechanical resonance frequency, and this table shows the measured value as well as the simulated value. And you can see we measure their mechanical response, electrical oscillator frequency, and also the frequency after mixing, and also the sensitivity with respect to the acceleration. And they are actually quite close to our design value, but we do have some discrepancy between the sensitivity, predicted sensitivity versus measured sensitivity. So we look at the more detail in our the performance of sensors, and we found that our sensors, the inductor-based sensors in our previous design are actually not so good, because the sensing inductor is actually a very low quality factor detector. Because we only use single turn of the coil, and usually we make these this coil, which is a spring inductor, only in the lower part of the metal stack, and because it only has a single turn, and it has a very large series resistance because of these slender structures. So meaning the Q is low, and if the Q is low, the noise from the oscillator, from the LC oscillator, is relatively high. So that limit the resolution of our previous design. So we think we should increase or improve the Q of the sensing inductor. So we use a High-Q inductor in the CMOS process provided by TSMC. So this is actually a standard inductor used for integrated circuit design, such as RF circuits. So this is a multi-turn coil, meaning its inductance is higher, and it is made in top metal, which is thicker, so has a smaller resistance, so meaning it has a higher Q. So we put these two together in series, so we can calculate the inductance, resistance, and the Q of these two individually, and when we put them together, we can find that this is the total L, total inductance, total R. We have a total Q. So you can see that the total Q is much higher than the original Q of our spring inductor. So so basically, we just add a series inductor in our design. So this is our chip. You can see that we put the High-Q inductance in the middle of our moving mass. So in addition to being an inductor, it also contributes to the mass of the shuttle mass, so to increase its sensitivity. And we have two oscillators, we have one mixer, and in this particular chip, we put the counter on the chip, so we can get the digital output directly from the chip without using external counters. So these are some SEMs for your reference. And we measure the static testing, and these are the noise, which determines the resolution of our sensor. And we put it in a dynamic testing. We apply different G. This is by using a shaker. So we can summarize all these performance comparison. So the last one is the inductor with the series High-Q inductor. And the first and the second one, the first one is the single axis device, and the second one is the 3-axis device. And we can see by using a higher High-Q inductor, we can have a much lower noise compared to this one here. Okay, so that's our progress for now in terms of this particular sensing scheme. So to conclude my talk, I introduce a inductive sensing mechanism and in CMOS MEMS sensors. And we also demonstrate a 3-axis sensing structure with only single proof mass. And we verified that by using a High-Q CMOS inductor, we can improve the sensor performance. And so currently we are still working on how to design the sensing inductor in a even better ways to make it even compatible with the traditional capacitive sensors. Okay, so that's all my talk. Thank you very much. Hello.
Okay, so thank you, Professor Chu, for this. So interesting, very interesting concept. So we always hear about the capacitive, accelerometers all the time. So you just mentioned in the last that that you are looking for more innovative designs to match performance. So is your sensitivity is lower compared to the capacitive ones?
Well, basically, we figured that the sensitivity is lower because the capacity inductance change is somehow smaller than capacitance change if we are comparing sensing structures with similar dimensions. So we'll probably make a more complicated inductor design. But also the main issue with inductor design, especially in CMOS cases, is that the inductors tends to have very high or very large series resistance. So especially if we only use a single term. So maybe in the future, we need to somehow make a variable multi-term sensing inductors to both increase its sensitivity and also decrease its noise.
Okay, so one more question is there from one of our participants. So he's asking that can this scheme be used for off-chip circuit? So will the series inductance of the wire bond will not kill the sensitivity? So
okay, can you say that again?
So will the series inductance of the wire bond will not affect the sensitivity?
You mean the wire bond from the chip to the board?
Yes, of course.
Well, no, but I mean, if we are talking about the CMOS chip and the inductance from the wire bond only affects its output to outside the board. So the sensitivity is actually determined by things that are inside the chip. So the wire bond is not part of the sensing loop in our design.
Okay, and what about the mutual inductance between the coils? So you say there are different coils being used for the conductance, right? So is there any effect of mutual inductance?
In our particular design, I don't think the mutual inductance is a serious issue because they are put side by side. They are not stacked together. So the mutual inductance should not be very significant.
Okay, so sir, maybe we can ask last question because there are many questions actually in my chat box, but I can ask one question because we are running out of time because we got some technical problem. So can you comment on like how much inductance really changed from the rest position of the proof mass? So let's say if we even excite at the resonance frequency, so what is the maximum number of inductance change?
Okay, that's let me see the sorry. Actually, I do not have the number in my head, and I don't know why I can. Let's see. So from the simulation, for example, here, but I do have to convert this to the input acceleration. But if you can see here on the left, if we only move the displace or deformed the inductor by 1 micron, it will have very small change. It's like a 0.01 nanohenry per micron. Yeah, but 1 micron displacement is actually a huge.
Yeah, it's a huge
displacement. Yeah. So the change in that is actually much smaller.
Okay, so before we conclude, we may have just one last question. So
Yeah.
how does the inductor compare to capacitor-based sensing in terms of output impedance?
Output impedance.
Comparison with the capacitive,
You mean the output impedance of the sensor?
Yes.
Oh, okay. The impedance of the sensor is actually taken care by when we design the interface circuit. And if you look at for our case, we use a LC tank oscillator. So we have either a fixed capacitance with a variable inductor, or we can also use variable capacitors with fixed inductor. Anyway, the impedance is actually taken care of the design of this particular oscillator. And we also, from the output of the oscillator, we connect it to the Gilbert mix cell, and we connect to the output buffer and connect to the wire bond. So for the, for the actual application, it doesn't matter whether the internal sensing is a capacitor or inductor.
Okay, so maybe just one last question from my side actually. So the whole discussion started to avoid the this stress issues, right? So there are stress issues, and capacitive sensing is badly affected because of that. So do you think this method is really solving that issue? Because there may be stress also in the inductive sensing as well. So is not affecting this performance much compared to capacitive ones?
You mean the residual sensing, the residual stress effect?
Yes.
We actually haven't have a fair comparison of devices with residual stress and the devices without residual stress, because it's really difficult to control the residual stress in CMOS MEMS. So we can only investigate this effect by using simulations. So here we can see that when we can apply a similar or the same amount of stress, and we actually do not have any significant change of inductors if we use inductor. But if we use capacitors, we do have some problems.
Okay, so thank you, Professor Chu, because we are running out of time because there are many questions still there. So I asked maybe other people to, you can write email to Professor Chu.
Yeah, you can email to me and I will reply you by email. Yeah.
So we are sorry that we cannot ask more questions. So, okay, thank you, Professor Chu. So
thank you,
for your...
Yeah. Sorry for my fault to delay the session.
It is okay, no problem. So
thank you.
Thank you for your... Okay, so actually next we have Professor Woo-T Park, and so I can introduce Professor he is a professor in the Department of Mechanical and Automotive Engineering, Seoul National University of Science and Technology. And I can just briefly introduce him. So Professor Woo-T Park received the BS degree in Mechanical Engineering from Sungkyuan University, Seoul, Korea in 2000, and MS and PhD degrees from the Stanford University in 2002 and 2006 respectively. So in his PhD work, he was working on the optical measurements of electrical contact deformations, wafer scale encapsulated MEMS devices, and some millimeter piezoresistive accelerometers for the mainly for the biomedical applications. And his research is conducted under the guidance of Professor Thomas W. Kane. Okay, so after his PhD, he started working as a senior packaging engineer with Intel, and then he worked on silicon chip test chips for assembly, test, and reliabilities. And then he moved to Freescale Semiconductors and leading many projects on MEMS process development in the sensor and actuator solutions. And after working 4 years in the industry, then he moved to Institute of Microelectronics Singapore, where he was working as a MEMS designer, and then later on promoted as a group leader and leading the group. So I also want to introduce that he was also my guide. I say co-guide in PhD also. So big thanks to him, for guiding me also. So at IME, he was working on the implantable biomedical MEMS sensors systems and wireless neural probes. And now he's currently working as a professor at Seoul National University of Science and Technology, working on fundamental and applied research in micro and nano device used for mainly for the biomedical applications. So his talk will be today will be on the circular biomimetic microstructures by air expansion. So I'm not reading the talk much, but maybe I can just ask maybe Professor Beauty Park to start his topic now.
Okay, thank you, Professor Singh. Can you hear me well?
Yes, please.
Okay. Thank you, everyone. Thank you for inviting me for this conference. Too bad it's held virtually, but I think it also has its advantages. This session is on MEMS and microfluidics, and I guess I'm the microfluidics part. My background is actually in silicon accelerometers and vacuum packaging, so I do have interest for other talks, but I hope my talk is also interesting to the audience. Okay, so today I'd like to talk about a pretty simple fabrication technique used for microfluidics and used for biomimetic microstructure fabrication. Okay, so I'm from Seoul Tech, Korea, in Seoul, South Korea. This is a picture of a blood vessel and microvascular structure. And obviously, this structure has been evolved for a long time, and we all believe that it's mostly in a pretty optimized form. And in order to mimic this structure for various reasons, we do have a need to make a circular or kind of an oval or at least a curved shape cross-section microchannel. And these days, people are trying to mimic the botanical structure, and also in the botanical structures, the channels are also kind of a curvature shape in terms of the cross-section. And also in the positive side, positive microstructures like this is a hair cell sensor inside the inner ear of a chicken, and these hair cells fluctuate with the flow of the fluid inside that corresponds to sound, and this is also kind of a cylinder shape, which is also a curvature shape. So I finished with talking about the background and motivation. So we're basically trying to mimic the biomimetic structure. And next, I'll talk about some example applications. So a glimpse of the applications, some previous works in this field, my fabrication idea, the results, applications, and I'll end the talk. So the first application is trying to mimic the blood vessel. There are many disease models and drug discovery. People are trying to test on blood vessels, and because of the problems with animal testing, and we want to test on real human vessels, it's becoming more challenging to do on real live animals or people. So people are trying to make a mimic structure that mimics the blood vessel. And to do that, we need a very curvature structure for the microfluidic channels. And this is one example from my group that we make these curvature cross-section channels and intentionally make these kind of narrowings in the microchannel so that they mimic the thrombosis, which is kind of what we do not want happening in our cardiovascular arteries. So everybody know this is a problem, but it's really difficult to know exactly how the thrombosis is developed, and people are trying to find out the mystery and trying to counteract for that problem. And this is a simple thrombosis on a chip to study the thrombus phenomena. So you can see these circular shaped cross-section microchannels. Other people worked on this as well. This is work from a researcher called Costa. He took the CT image or MRI image and reconstructed the blood vessel narrowing using 3D printing, and then used that to make the negative mode to replicate this thrombosis in a 3D form. So a lot of people are interested in this area to test what's happening in the thrombosis phenomena. Another area is making small drugs out of polymer, and you can make it out of very small nanoparticles or microcapsules or nanocapsules. On the right is the work from MIT's Bob Langer, and they're making these type of 3D focusing microstructures. And in order to, when we're making this, in order to make a nice, very uniform microstructures, it's better to have a coaxial flow stream. So our fabrication technique was also used to make this type of device to make the polymer nanoparticles. So I talked about microchannels already. Also, we can use the curvature, so circular cross-section microchannel as a negative mode to make a positive structure. So this is an example of making a high aspect ratio structure. This is actually trying to make a neuroprobe, polymer neuroprobe that dissolves inside the body. And so this has a kind of a, not exactly a circular cross-section, but kind of a curved cross-section, so that it has minimal minimal insertion stress to the tissue, while still being able to insert, having a sharp tip. So this is also similar. So it's a microneedle. So it's a short form of the previous one. And microneedles or polymer microneedles are a very hot topic these days in terms of drug delivery and cosmetics. And as you can see on the right side SEM, this is kind of a half oval shaped cross section, so that it has a smooth insertion and it can dissolve inside the tissue without much problems. We also made a interesting shape. This looks like a Christmas tree. It's like a microneedle that has these barbed edges, and this is also enabled by the fabrication. And this is designed to kind of anchor itself inside the tissue and not come out before it kind of dissolves inside the tissue. So previous work started, of course, from the soft lithography from Whiteside's group at Harvard. So people use this method. A lot of people use this method to make these rectangular cross-section microchannels for microfluidics. And because other people wanted to make a circular or curved cross-section microchannels, this is one of the efforts. They made these channels and used pneumatics to inflate the very thin membrane, and then use like PDMS to mold on top of it. So using different air pressures they were able to make different shaped curvature structures. So this is a kind of a half microchannel, and you have to have another half to align and bond to each other to make a complete channel. This is another work. They made the rectangular cross-section microchannel and then flow kind of uncured PDMS or uncured other polymers, and then introduce a high-pressure gas. So that would dislodge all the polymer except the corners because of the surface tension of the fluid. And after curing it, we can get a circular shape microchannels. And using different pressure, they can get different sizes of the microchannel. The next one is also quite common method, using photoresist and patterning it, and then reflow the photoresist to make a curved shape from surface tension, and use that as a positive mold to make a negative mold out of PDMS. And if you look at the H picture, it's almost a perfect circular cross-section microchannel, and it's made by very carefully aligning two formed PDMS halves to make it without any alignment problem. This one is also pretty similar one, using CNC micromachining to make, using a curvature shaped end mill to make the microchannel that has a curvature shape, and using that as a negative mold and replicating to make the final microchannel. And again, you have to carefully align them together to completely form the microchannel. This is a pretty recent work from France, I think, from LabChip last year. They use a very interesting lithography technique called backside illumination lithography using a light diffuser. So light diffuser is like a translucent film coated on top of glass, and that diffuses the light in different directions, kind of random directions. And that enables the light to diffuse not just straight, but kind of in a kind of isotropic fashion. And because of the light traveling that way, it can cross-link the SU8 in a curvature shape. So they worked on similar application like us, trying to replicate the microchannels to form as a blood vessel and a microvascular structure in PDMS. So this is kind of a half shape, half channel, half microvessel formed on PDMS. So our idea came from the PDMS solidification process. A student from MIT did a whole thesis on this, trying to characterize the curing condition of PDMS and the intermediate phases and the mechanical properties of it. So if you've used PDMS before, you probably know that it's liquid, and then you mix it with the curing agent, and after some time, it becomes solid. But actually, there's a phase in between that phase, and we call it the gel phase. And we can characterize that gel phase in terms of the stiffness by this apparatus on the right, using a force meter to poke it and then retract to quantify the modulus and the gel, kind of a gel phase, we call it. So we can quantify and control how much is cured, and we know the corresponding modulus for that curing phase. So let me go through the fabrication real quick. So we start with SU8 lithography, and then use PDMS molding. So this is soft lithography. We take out the PDMS, we flip it, and then we coat it with some HPMC. So this is kind of like HMDS. It's like an anti-stiction coating by polymer. And then we take this partially cured PDMS. So this orange color PDMS is kind of what we call a gel phase, which is not completely cured. And then if we heat it up, the gas trapped inside the microchannel expands and forms this type of a curvature structure. Okay, so then we solidify the PDMS. And because we attach the anti-stiction coating, we can detach the mold without any damage. And then we repeat this process on another kind of a gel phase PDMS. And then we expand again, and then we can form the circular structure. So the main advantage of our process, I think, is we can get rid of the alignment process, and if you've aligned and bonded PDMS structures before, you probably know it's pretty difficult because the PDMS is, or other polymers are very flexible. So if you align on one part, the other area is hard to align. So this fabrication takes away from that complexity. We also tried expanding not just by the expansion of the gas, but we use a controlled gas pressure. So we can use a syringe pump or other means to pump in some gas and control that, and use that controlled pressure to expand the gel phase microchannels. But the problem here is we have to connect each channel with this pump. So that becomes a little bit more complex in terms of the design. We can also make positive structures out of this process. This one is kind of summarizing the whole thing. So up to the top part is the same as what I just explained. And then we can use a blade to cut the top side to expose the channels. And then we can cast some polymer that we need. The polymer, there's many different polymers used for microneedles. And we can insert that polymer and mold that polymer, mold that polymer inside this mold, and then take out the desired microneedle array patch. So the gel phase, depending on the level of the curing time, so the level of rigidity, when we expand using the thermal expansion, the level of expansion is obviously different because, for example, if we cure less, it's more soft, softer, so it deforms more, rather than if you cure more, it's harder, so it deforms less. Okay. So by the different curing time, we characterize different designs of the channel, and we measured the depth, the deformation depth. And this purple line, straight line, is showing kind of a 1-to-1 width to depth ratio. And you can see that this data is showing that it's difficult to get exactly what we want. It kind of saturates in terms of the deformation. So after a certain point, it stops deforming. And this is because we're heating up from the bottom or from the outer surface. When we're heating up, it expands, but we're curing at the same time. So the obvious way to get rid of this problem is to expand and then cure separately. Okay, so this is again showing from separated channels and connected channels, and we also have this problem of kind of saturating. So the next phase, we try to separate the expansion step and the curing step. So we expand by the compressed air and then cure it by heat later. And then because of this extra step, now we can get pretty linear response, and we can get the required channel depth that we want. But the design complication is that the channels now all have to be connected together. Okay, so if we don't need exactly a real deep depth of deformation, we can use the previous fabrication process. But if we want a large deformation in terms of the channel, we have to use this compressed air so far. So this is showing from when we change the air pressure, we can get different channel depth. So this is what we expected. And this is from different designs of the width of the channel. We can also combine the different deformation. For example, we can combine a shallow deformation and a deep deformation to form kind of a different shape. And of course, again, this is not combining the two form channels. We're just combining the processes. So still, we're free from the alignment problems that the other fabrication process has. So this is showing combining the different cases to make different types of different shapes of microchannels, and we can get very close to perfectly circular microchannels using this way, combining the different techniques. We also did a pressure burst test to make sure that it has enough strength in terms of the channel. And you can see that this bonding is, because it's kind of a fused bonding, it has very similar bonding strength or even better bonding strength than the traditional plasma enhanced bonding of the PDMS. So let me share you some results from the applications. So the first application that we were targeting was a barbed microneedle. So this is the kind of like a tree-shaped microneedle that has these side barbs, so that it's mimicking the honeybee stinger. And we're simplifying and making this shape. Okay, so this is the same process that I just explained before, so I'll skip this. And this is showing the mold being filled with dissolvable polymer containing some red dye for illustration. And we tested these microneedles. The main point is that we can get higher force during the retraction phase compared to just normal microneedles. So in the insertion, we have an increase of force. And then when we retract, we also have this force that is coming from the barbs that's holding on to the tissue because of this shape of the microneedle. So this is the stinger from the bee. This is all from the reference. And we made a shape just copying the 2D structure, 2D picture of the stinger. And we used our process to replicate this in a 3D shape. So this is how it looks like. We're still trying to optimize the shape of the barbed microneedle. And if you look at the number 3, which is the natural honeybee stinger, this is still the best performing barbed microneedle, because you can see that it has a very small insertion force and a very large retraction force. And in this work, the simplified form still had the best performance, but still we need to reduce a lot in terms of the insertion force. But if you compare the retraction force to the other works from other kind of anchoring purpose microneedles, our microneedles are still better than the previous reported anchored microneedles. The next one, which is the final application I want to talk about, is trying to mimic the thrombosis and test with real blood. So you probably know that in the coronary artery, if you have a narrowing, this can progress and become really dangerous and lead to heart attack. So we try to mimic the thrombosis shape. So this is kind of a coaxial form of the thrombosis, which is a very simplified shape of the thrombosis. And we also try like kind of eccentric thrombosis. So this narrowing is kind of more geared to the one side rather than kind of a coaxial, sharing the axis in terms of the two locations. So we look at the number of we also try different levels of stenosis, and then we perform some CFD to see the shear rate difference between the two different types of stenosis for different degrees. And then we fabricate these models based on trying to replicate the shear rate that will happen on real blood vessels. So obviously these channels are smaller than the coronary arteries. So we try to replicate the shear rate, not the exact shape. Okay, so this is the CFD result. This is a short video showing the thrombosis test using real blood. The platelets are stained with fluorescence. So this white thing is the accumulation of platelets. And there's many different models of the thrombosis formation, but the platelet agglomeration is one of them. And this is showing and trying to measure when this is happening and the different models for different shapes of the microchannels. Okay. So we model by the light intensity because the platelets are stained. We measure with the light intensity because the platelets are stained with fluorescence. And we also measure the pressure change between the inlet and the outlet to see the degree of the thrombosis. And we can see that from the concentric and eccentric case, the formation style of the platelets are kind of different. From the concentric case, you can see that it forms a big narrowing and then dislodging the clogging and then reforming again. Whereas eccentric, this formates and then dislodges more frequently. So in terms of the disease, I'm not exactly sure which one is more harmful, but definitely the formation of what we call embolization, which is the formation of this clot, is different from two different shapes of microchannels. So we're hoping that this can serve as kind of a basic research tool to study this phenomena. And later on, if we can optimize the shape, we can use it as a clinical use to assess the thrombogenicity, like how much the patient can form this thrombosis with the blood type they have, or monitor the drug use, like antiplatelet or anticoagulant, like aspirin is one of the drugs. And we're not the only people working on this. Of course, there's many different commercial products that simplifies this phenomena and trying to standardize this. But our goal is to first study this phenomena better to make a more novel design in terms of the clinical use. So this concludes my talk. We formed the fabrication technique to make curvature cross-section microchannels or structures from 25 microns to 500 microns It has a very smooth surface, and then there's no alignment required, which is very nice. We use the structure to make biomimetic structures, positive and negative. It has very good sealing strength, and we used it for many applications. And I didn't talk about sensors, but we're trying to expand the applications. Okay, so I think I went over my time, so let me end my talk here, and I'll take the questions.
Okay, so thank you, Professor Park, for your talk. So, of course, this is a very innovative and easy method to make this structures. So, just one or two quick questions because we are running out of time. So, in the slide 9 and 10, you showed some micro needles structures, right? But
right.
where is the place where the drugs can be transferred from that? Because I think the main purpose is to transfer the drug delivery with this, right?
Right.
So
your question is, where is the drug?
Yeah, from where we transfer the drugs actually with this needle.
Okay, so there's many different types of microneedles. The microneedles that we're currently working on are biodissolvable polymer microneedles. So the microneedle structure itself, this one, the whole thing is designed to dissolve. So it's formed with biocompatible polymers and containing the drug itself.
Okay, great. Okay. So, and one more question is that, so, you are making some kind of, with this 3D printing and some material, and which is very equal to the actual blood vessels, right? And so how do you make sure that they, what mechanical properties of the material you choose to make sure that the performance is is matching very much equal to the actual blood vessels?
Yeah, that's one of the limits, or maybe one of the things that we need to work on when we're trying to mimic the blood vessels. Actually, there's many different factors that we're not exactly copying except for the shape. We're just copying the shape, but there's also the texture. There's also some roughness, and also what you just said, the elasticity is different. The blood flow is not a constant flow. It's usually a pulsatile flow. So we're not exactly copying the exact structure of the blood vessel right now. We're trying to, because we cannot copy exactly, we're trying to find what are the key designs or like texture or factors that affect this. And we're just trying to take maybe a subset of the copying the biology.
Okay, so I think we are, again, because of the time limitation, I'm not taking more questions. So others who has questions, can you please email to Professor Park, and he may reply your questions through email. So I once again thank you, Professor Park, for giving a talk to us, and I am sure that our participants will be benefited from this technology also. So thank you very much. And
thank you.
We now actually introduce to our new to the next invited speaker, and he's Professor Ashwin Sheshia from UK. So he's professor in the Department of Engineering, University of Cambridge, and I just read his biography. So Professor Ashwin Sheshia received his BTech in Engineering Physics in 1996 from IIT Bombay, MS and PhD degrees from the University of California, Berkeley in 1999 and 2002. So, and he joined the Faculty of Engineering Department at the University of Cambridge in October 2002, where he is presently working as a professor of Microsystems Technology and a fellow of Queen's College. So he is a fellow of Engineering Institute of Physics, a fellow of Institution of Engineering and Technology, and a senior member of Institute of Engineering and Electronics Engineers. Professor Sheshia currently serves as a editorial board of IEEE JMEMS and IEEE transactions of ultrasonics, ferroelectric, and frequency control, and the executive committee of European Frequency and Time Forum. He received the 2018 IEEE Sensors Technical Achievement Award for pioneering contributions to resonant microsystems with application to subsurface density contract imaging and energy harvesting systems. So today he will be sharing his experience on the talk, and which is titled as vacuum packaging and environmental control of micro mechanical systems. So we know that this packaging is very important aspects for the MEMS sensors, right? So let's now hand over the mic to Professor Aswin for his talk. So thank you, and we welcome Professor Aswin for your talk.
Thank you very much, Professor Singh, for that kind introduction, and thank you for the invitation to speak at this conference in IIT Delhi. It's always a pleasure to come and speak to the IIT audience, and I recall very fondly my visit to IIT Delhi just 2 years ago when the IEEE Sensors Conference was held in Delhi. So as Professor Singh mentioned, packaging is an issue that doesn't get enough attention at academic conferences, but is an absolutely indispensable need to realize practical microsystems. And I'm going to try and talk through some of our own learnings around packaging, really. Only too often, academic researchers come up with great ideas, and when they want to try and move these ideas from the academic domain to the to commercial translation, find that often these are limited by the packaging approach adopted. So hopefully like to motivate from our learnings, a discussion around packaging in the community. So in particular, I'll be talking about vacuum packaging and environmental control, but there are, of course, many, many dimensions to MEMS packaging, and I'll try to seed some of these ideas at the end of my talk. So this is the outline. I'm going to start off by highlighting some examples, really, to show the current state of the art in MEMS packaging. Very briefly summarize the approaches around wafer level and die level packaging, then talk around 2 case studies from our group around packaging of MEMS, energy harvesters, and then inertial sensors. All right, then conclude with some ideas for future work. So this is a slide out of a paper from Bosch at the IEEE Sensors Conference. And this shows the emphasis that industry and cutting-edge R&D in industry places on packaging. See this highlighted right up front in the abstract that discusses the evolution of Bosch inertial sensor technology. This is going from essentially a 2-chip to a single MEMS chip evolution that was part of the work described here, bonded ultimately to a single ASIC within this package. So what's interesting here is the innovation around the packaging, really, where you've got the accelerometers and the gyroscopes sealed under different pressure levels to accommodate the different design requirements. So the High-Q requirements, high stability requirements for the gyro, and the damping requirements for the accelerometer. This is achieved at a wafer level using a laser resealing process, which is described in another paper at the same conference. And absolutely essential both to the performance, realizing the performance of these sensors, and the miniaturization demands on the product. Now, another example is the outstanding work of Stanford, SciTime, and Bosch, which in fact Professor Park was involved in the early work as well. And this is now a product. These resonators, these silicon single crystal resonators, are encapsulated at a wafer level. And the very low pressures are essential so that you've got a pristine vacuum environment in the cavity that allows high quality factors and high stabilities for the MEMS oscillators that integrate these resonators to develop timing products. And so you can see from that paper, they thought of the quality factor of the resonator as a function of pressure, and often you'd like to be limited by intrinsic loss in the resonator, so to maximize these quality factors, and therefore the demand for vacuum packaging. Of course, the vacuum environment also provides a highly stable local environment for these resonators, prevents issues that might otherwise lead to long-term degradation in the metrics, and ultimately, so the stability of these devices, which is critical for these applications as time and frequency references. Again, in this particular paper, packaging highlighted up front, and it continues to often limit the not just the performance, but also the cost and miniaturization of MEMS products. All right, so those are two examples of the state of the art in packaging, and to highlight some of the approaches at the wafer level. So on the left is the Stanford SciTime Bosch approach, a thin film wafer encapsulation approach. So you have your MEMS devices that are rated in the starting wafer, say for instance SOI, and you run through the etching to create your device structures. There is a thin film encapsulation layer that goes on top, and then vent holes in that thin layer that allow you to come in with, say, a HF vapor type etch to release the structures, reseal the holes. You've got a thicker film that's deposited that seals in the vacuum, and then you can run the rest of the process, including the metallization and so forth, to make contact to the devices. So that's the thin film encapsulation approach on the left-hand side. On the right-hand side is the wafer bonding approach. This is in fact out of IME Singapore as an illustration, applied to their work on inertial sensors. And in this particular case, this is showing a eutectic bonding approach. So in this case, I think a germanium aluminium eutectic. And so the two wafers brought into contact, and it's more a reflow type process used to under vacuum to seal the wafers against each other. You see a getter incorporated in the cavity as well, and that's activated prior to seal. All right, at the academic domain and low volume, we've used an approach that's similar to what's shown here schematically, where for low volume prototyping, you're looking at essentially die level encapsulation. So for instance, you've got the MEMS die seated into a package, an LCC package, for instance, and then in a vacuum setup, you run the a bonding process of a lid with solder preform on the lid, and perhaps getter deposited on the inside of the lid as well. That's brought again together under contact in vacuum conditions, and solder reflow process used following getter activation to seal these devices under vacuum conditions. So an example of some of the early devices, these are examples of energy harvesters showing under similar sealed conditions differences between going and the response is going from atmospheric pressure to vacuum conditions where you've got the clearly the same device, very clear improvement in the Q factors. And for a resonant energy harvesting context, this is relevant because you can extract more power from the device, the same vibration levels when operated in round resonance. Some of the energy harvest you're looking at were in fact based on parametric amplification, and again, low damping conditions facilitates the onset of parametric resonance and the accessibility of higher orders. And this is showing the difference between essentially going from atmospheric pressure to vacuum conditions as power output on the vertical axis versus the excitation amplitude on the horizontal axis. And you can see that, for instance, cases under atmospheric conditions, where you really would have to go to very high excitation levels to see onset of parametric resonance at the higher orders, but these do onset under vacuum conditions. So again, the ability to recover higher output power levels, relative output power levels for the same excitation amplitude. Okay, so moving forward, talk about a little bit about energy harvesting and some of the other considerations that are involved in packaging. One of the other considerations involved is in terms of optimizing for robustness. So these harvesters can be applied to generating output power under high vibration environments. And as you can see here, an example of a device that's excited to extremely large amplitudes. You'd see post the excitation on a shaker, where these cantilever structures can fracture due to those very high excitation forces. So you want to mitigate this, and one possibility of doing this is by optimizing the packaging. Published this in the Journal of Micromechanics and Microengineering a few years ago, where we looked at essentially squeeze film damping under low pressure conditions, such that you engineered a nonlinear damping in the mechanism. So for low excitation amplitudes, you have lower damping levels, and as you increase the excitation amplitude, the nonlinear damping starts to self-limit the oscillation amplitude, and so you're able to both engineer good responsivity under low vibration conditions when you're often struggling to extract high output power from these devices, and also trying to optimize for robustness at much higher vibration levels. So that's basically, if this is designed right, so an optimal pressure level in the cavity, you can show a saturation of the displacement response. This is indeed another approach that was used by integrating foam stoppers, so mechanical stoppers into the package. There's a particular example that we presented at Transducers last year on MEMS energy harvesters used to power up a wireless sensor node for an automotive application. You can see representative rectified output power levels from a single MEMS device under fairly high vibration excitation conditions. The schematic of the package and the way these cantilever harvesters are integrated within the package, showing the spacer arrangements to accommodate the motion of the harvesters vertically up and down, the foam stoppers, carrier lids, and so forth. And it turns out that you can mitigate the issues that are associated if you don't otherwise limit the amplitude. So in this particular case, the application context demanded operation to an excitation level of 10 G RMS. Without the foam stopper, you end up with devices fracturing at lower excitation amplitudes, but with the foam stopper, the devices operate just fine, going up to 10 G RMS sort of levels, at the same time extracting the more than sufficient power at those vibration levels to power up a wireless sensor module. So again, further data from the module showing the rectified power of a single MEMS device. This rectification was achieved using a full bridge configuration at a board level and an off-the-shelf unit power management that was integrated at that board level. So representative oscilloscope traces on the top is the excitation waveform. So this is from an accelerometer demonstrating essentially the acceleration that was subject for this platform. And then at the bottom, you've got the rectified output waveform and the output of the power management unit essentially supplied the power to the wireless sensor module that was powered up by the single MEMS device under these conditions. So in comparison, between this work and some of the other work, this shows some of the metrics here, the ability to operate at much higher acceleration levels, as well as to build these from single MEMS die, a self-sustained wireless sensor mode for an automotive context. All right, so that's one example where the package and the design of the package plays a significant role. I'm going to talk about another example as well. In this particular case, we're talking about power output and the robustness of energy harvesters. And move on to another example of inertial sensing. Talk more about the stability and signal-to-noise considerations of a resonant MEMS device. So this is a schematic of vibrating beam accelerometer that can be adapted as a tilt sensor or gravimeter. And the way this works, for instance, is schematically as shown here. Instead of a capacitive accelerometer where you let the proof mass displace freely and measure the displacement using a set of capacitive electrodes, you couple the inertial force on the proof mass to a set of resonant force transducers, and the resonant force transducers respond just as the strings in a musical instrument. So the natural frequencies shift as varying levels of axial loading are communicated to them. So for instance, if you were to orient the sensitive axis of the accelerometer relative to the vertical at different orientations relative to the vertical, as we heard in the first talk, you will be coupling different inertial loads on the mass due to the component of gravity acting along the sensitive axis, and that results in a tensile loading on one device and a compressive loading on the other. And so you've got a push-pull effect on the resonant frequencies of the two tines, and the differential frequency is measured to obtain a measure of the acceleration level. So you could in fact use this technique to either measure theta, or for a fixed small g value, or the value of small g if you fix theta, right? So that's the basis of a tilt sensor or barometer, but also essentially this is an accelerometer. Now, what we have to do for these devices is, because the output stability critically depends on the quality factor of those resonant beam transducers, and of course for similar considerations for the time and frequency reference application, where we need to package the resonators in the vacuum conditions. Here as well, that's necessary. We've used a fusion bonding approach, so wafer bonding, silicon-silicon fusion bond under vacuum conditions to create that sort of pristine vacuum environment for the MEMS devices and the resonant beam transducers. There are through silicon vias integrated into a lower wafer to provide interconnects to the MEMS structure under vacuum. And that's a picture of the wafer. Now, I want to illustrate here the issues with environmental dependence, because this is the key limiting factor for inertial sensors. You can see dependence of the output frequencies to variations in pressure. So this is recorded pressure levels in a module where these devices are built in, and the corresponding output frequencies. In fact, this can be modeled numerically as well, with good qualitative alignment in the models and the actual measured responses. But these are in fact measured responses. So you can see sensitivity to pressure even in a vacuum condition. This is because of mechanical stresses that are communicated to the resonator, time varying stresses due to the fluctuating ambient pressure levels outside of the cavity. If you were to, for instance, try to extract the dependence on pressure, you see, just plotting, this is frequency versus time, or pressure versus time, you plot frequency versus pressure, you see a correlation, do a linear detrending, extract the residuals, and you see very clear correlation between the frequency fluctuations that often mischaracterized as noise. They're in fact directly correlated to fluctuations in external ambient pressure levels instead. So this can be compensated for through suitable packaging approach. Now, if you're able to eliminate the pressure dependence completely, you end up with a residual temperature dependence. And this is sort of showing measurements of the chip temperature using an external thermistor, and the residual frequencies following pressure compensation. And so you see here, and this is also shown separately through a correlation analysis, that there is dependence, sensitive dependence to environmental variables that just need to be accounted for. So one of the home-built configurations that we have here is shown here. This is one of the early ones to ovenize some of our devices, but indeed, ovenization is now built into time and frequency reference products, and that can be achieved at a wafer level as well. And it's absolutely key to ensuring the stability, the long-term stability of resonant sensors as well. So elements of the packaging, so vacuum packaged device here that showed earlier, a wire bonded to a lead frame carrier, and of course there's a die attach. That's indeed very critical component as well in mechanical ensuring mechanical stability for the die, but also that does end up being a significant component of any stresses that can be communicated from the external world into the package device. This is then mounted onto the PCB with the electronics. So in terms of achieved stability levels, this is the Allen deviation of the oven temperature, the chip temperature as a function of integration time. You can see even at very long integration times, as to half a day or so, we get stabilities under 100 microkelvin or so. The short integration time, this is in fact limited by the detection limit of our noise of our thermistors down to about 20 microkelvin. And that allows us to build these very stable output accelerometers that can be used for gravity and seismic measurements. So this is the Allen deviation of one of the accelerometers that was tested a couple of years or so ago and published in scientific reports earlier this year. This is now down to integration times of over 30,000 seconds, overlaid on the ideal Earth tide tracking model. And you can see these levels are down now below 100 nano-G or so. This is the response of these over a period of time course of 3 to 4 days. We overlay the output response on top of the theoretical Earth tides model. And again, the excursion that we're tracking here is on the order of 150 plus or minus 100 to 150 nano-G over the course of several days. So you do need to have excellent long-term stability to be able to perform these measurements. This is achieved through the packaging in big part and the environmental control. So those are two examples of packaging enabling MEMS. And in terms of just wrapping up, because I've run out of time, ultimately there's a number of interesting problems that are being looked at in the community. We open this up into wider domains as well, but ultimately we'd like to move into a paradigm where the design of the MEMS fundamentally considers the design of the package as well, and the package might ultimately become part of the device. And this is especially critical as you miniaturize and are pushing towards higher performance, lower cost products. So I'd like to stop by acknowledging the many contributions of my PhD students and postdocs over the years to the work described here, collaborators and funders. Thank you very much.
Okay, so thank you, Professor Ashwin, for your talk. So we know that this packaging is a very, very necessary requirement for the MEMS sensors, and usually at the universities we always face problems actually how to package our devices, because this wafer level packaging is only good for the when we have the whole wafer actually, and then we can bond it together. And mostly at universities we have small chips, and once we make sensors for some applications. So in that thing, maybe you mentioned about the thin film encapsulation, right? So that can be a hope for the students. So can you please mention a little bit about how this thin film encapsulation can help to achieve, let's say, packaging on the chip level or maybe small wafers level? Is it possible?
So at the wafer level, yes, absolutely. And Professor Saurabh Chandorkar at Icee Bangalore is, in fact, I think working with SCL Chandigarh to establish some very similar platform. This is something that I think can be accessible to academic researchers as well. I understand that there are facilities at that would allow this sort of possibility. If you're looking at low volume prototyping for academic purposes, the die-level approach that I mentioned is something that is certainly very viable. Custom versions of these systems, we had a home-built version built up in the machine shop for us, that would allow us to do some very basic initial vacuum packaging work and encourage academics to look at those sorts of tools that could be built up for academic purposes, and shared. There's some that you could build up for low volume prototyping internally, and there are services that you can access for low volumes that are not too expensive as well if you're looking at die level packaging. So a number of options for academia that exist that didn't exist, maybe 10, 15 years ago.
Okay. So one more thing you mentioned about in very first 1 or 2 slides, right? So you said that there is a process to have different pressure levels for the gyro and accelerometers, right? So is it possible to have different? How is the packaging like, which can create different pressures in the in the sensors sitting nearby?
Yeah, exactly. So that's a really interesting challenge. But Bosch has in fact delivered on this for their commercial products that are sold in very high volume. And as I said, there's a laser resealing process that you adopt. So essentially, what they do is that they run a initial vacuum sealing step where they package at a relatively higher pressure. Then they open up vent holes in the gyro regions and then pump up further, and then follow it up with, seal up those vent holes using a laser resealing approach. So deliver on the lower pressure levels for the gyro parts. And this is all done, on an industrial scale, wafer scale, So very impressive work. And I'd encourage you to look up the IEEE Sensors Conference paper where they describe more details around that approach. Yeah.
Yeah.
Okay.
Right.
Thank you very much. Yeah. So, any more questions? So you can ask directly now.
Yeah. So Ashwin Bhaskar here from IIT Delhi. So actually related to this, so we have kind of a project where we need to package at higher than atmospheric pressure some noble gases. And I was wondering that there isn't much literature. Most of these techniques are vacuum sealing techniques. But at least to my understanding, a lot of them don't translate well to higher than atmospheric pressure sealing or even atmospheric, where you want to package with a noble gas or something. So, would you have any comment on, those kind of packaging scenarios?
Yeah, so I personally don't have any experience in that area, but yes, I would think that that's an sort of it's an interesting challenge. We have looked at some work around integrating fluidics with MEMS devices in the context of air fluidics, basically in the context of particulate sensing, where you have to integrate potentially active miniature pumps and so forth at that scale. But no, we haven't looked at higher than atmospheric in any of our work so far. But yeah, interesting challenge. I'd be happy to look into that. So see some ideas for what's possible.
Yeah, some of methods, I think all of them are vacuum sealing, and we've been experimenting with higher than atmospheric pressure. And these are like fairly high, not just 1.1, looking at 5 or 6 atmospheres. So,
okay, interesting. Yeah, what's the application, if I may ask?
So we want to make, so I work in microplasma devices, So it turns out these these plasmas can exist at higher than atmospheric pressure if you scale them down. And if you package it at higher pressure, this operates at higher than atmospheric pressure, then the Excimer reactions, which are the three-body reactions, they get prominence. So if we package it at, make the device operate work for 2 or 3 atmospheres, we can get very intense UV radiation from these devices, which we won't get at atmospheric pressure. So if we have to package with argon fluoride or krypton fluoride, ideally, at about 3 atmosphere, that would be very nice. But right now, we're trying at 2. And so we have not succeeded so far because things tend to leak out. But
okay. Yep. Well, that sounds really interesting. So keen to follow your progress, and of course, yeah, if I do locate anything, I'll pass it by you.
Okay, so if anyone else has any questions, maybe just one last question we can ask. Otherwise, we have to, because we are really running out of time basically. So it's open for the questions if you can ask directly, because I cannot see the chat box. Okay, so if no, then let's thank Professor Ashwin Shashia for his talk. So, sir, thank you very much for your introduction, and I hope the audience will be really looking this packaging activity as we all know, it is very important actually. So, thank you again for your talk.
Thank you.
Okay, so now our invited lectures are coming to end for this session, and then we have 2 more oral presentations. Let's start with Mr. Vikram Mehersi from IIT Delhi, and his title of presentation will be Contact Study of MEMS High-G Impact Sensors. So Vikram, can you please start? So please, as you know that we are getting a little bit late, so please stick to the 15 minutes limit actually. Vikram, your mic is off. Vikram, your mic is still off.
Yes, sir. Yes, sir. Now I'm audible?
Yes.
Yes, sir.
Yeah. Please go ahead.
Thank you, sir. Good afternoon to everyone. My name is Vikram Mehersi. I'm a PhD student at IIT Delhi in Electrical Engineering Department under the supervision of Dr. Bhaskar Mitra. As the title of my presentation is Context Study of MEMS High-G Impact Sensor. So basically the MEMS impact sensor is a device, is kind of a G switch that has a latching mechanism, and it engages the latch and closing the electrical circuit, and that lead to the detection of a threshold acceleration. So here's the schematic of the MEMS impact sensor. It consists 3 parts. One is the acceleration sensor, second one is the impact mask, third one is the cantilever latching beams. So once the acceleration comes, the acceleration sensor hit the impact mask and it engaged to the latch. And by closing this electrical circuit, and the change in resistance lead to the detection of a threshold acceleration. By using these electrostatic electrodes, we can reinitiate this design by delatching this impact mask from these cantilever beams. So this particular configuration has the advantage of that the post-latching, it is relatively insensitive to the acceleration due to this smaller mass of is a movable electrode. And the use of this folded acceleration design makes this device insensitive to this orthogonal direction. So this device is designed to be a passive device that it doesn't require any constant power just to detect the threshold acceleration, unlike any other conventional accelerometers. And it can be used in application like detecting the crash events. And we modeled the shock. The shock is modeled basically as a half sinusoidal waveform. So the motion of this sensor is divided into 3 phases. In first phase, the impact mass, the acceleration sensor will move only. In second phase, the acceleration sensor will move with the impact mask. And in third phase, the impact mask will be latched between these 2 cantilever beams. So the sensor is designed such as that impact mask will be latched with the time duration of t/3 to 2t/3. To set this threshold acceleration latch accurately, so it is important that latching phase should be centered around the peak of this half sinusoidal wave. So once the acceleration starts declining, so the restoring force of the springs dominates then the inertial forces, and then proof mask will come back. So here's the impact sensor design. So this the resonant frequency of this acceleration sensor is designed for a 8.8 kilohertz, and we have a two contact surface are there. First between this acceleration sensor and the impact mask, and second one is the impact mask and the cantilever latching beams. And the design equation of threshold acceleration is given by this formula, where three terms are there. First one is coming from this acceleration sensor, second one comes from this impact mask, and third one comes from this latching cantilever beams. So the complete design we can discuss in other time, in the off time as well. And basically in this work we wanted to model the accurate behavior of this impacting force, impact validation, and the contact behavior of the microstructure and the latching beams. So we started to model this sensor in the COMSOL multiphysics tool, and we use this solid mechanics tool to use the contact solver. And in the we are using this half sinusoidal waveform. So in the first phase, the impact mask will hit the acceleration sensor hit the impact mask, and there is a first contact between this acceleration sensor and the impact mask. So at some time, the acceleration sensor and impact mask will move together at a certain extent, but after once the spring force dominate to the inertial force, the larger proof mask will come back, and the impact mask will travel only. And the second one is the stress which is caused by this impact at the flatter side of this impact mask is shown here, and which is around 11 megapascal, which is quite less than the yield strength of silicon, which is around 7 to 9 gigapascal. So this is the first contact, and now we wanted to model about this curved surface with this latching cantilever beams. So we are using this static Hertz model. So in this, basically we are taking as a case of elastic curve body that comes in the contact with this frictionless surface. So a small area basically is created through this elastic deformation. So the both bodies are deforming, and the effective Young's modulus of these bodies are given by this formula, where V1 and V2 is given by the Poisson ratio of these materials. But for this static Hertz model, we have to make some assumptions, which is like the strain should be small and should be in the limit of this elastic behavior. And second one is the surface should be continuous, like we have deposited the material, and it should be continuous, and the contact on the bodies should be the frictionless, and each body can be considered on the elastic half space. And the stress generated because of this contact is given by this force upon area. So by using static Hertz model in our FEM model, which we are doing in COMSOL multiphysics tool, so we opted for this augmented Lagrangian method, which is the combination of Lagrangian multiplier as well as penalty method. So there are two variables are there. One is for the penalty factor, second one is the contact pressure. First, the penalty factor just for decide the converging time for the iterations, and contact pressure is just we have opted from this Hertzian model, and using this we decide the we give the boundary condition between the master and slave boundaries. So by using this, we done this simulation. And second one is the contact resistance. Basically, is a very critical parameter for any MEM switches. So basically, metal contact size may affect how the electron is are transported through these tiny spots. So different electron transport mechanism may result in the different form of the resistance. So we are having three different transport mechanism are there. First is diffusion transport mechanism, where the mean free path of the electron should be less than the contact radius. Then the diffusion transport formula is given by RC rho divided by 2R. But we are using in like metal contact, we are using gold material, as the both contacts. So the properties we are using for this study is shown in this table. And for this ballistic transport mechanism, where mean free path is greater than equal to the contact radius is given by the RS, where is the Kn is the Knudsen number, and in third one is the quasi-ballistic transport mechanism, where the mean free path is comparable or equal to the radius of curvature, contact radius, sorry, and which is given by the interpolation between this diffusion transport as well as the ballistic transport mechanism. And where one is the Kn is the Knudsen number and gamma is a interpolation factor. So now we are using this contact Hertz model in our FEM model, and here's the second phase of our sinusoidal waveform, where the second contact is there between this impact mask and the cantilever latching beams. So once the impact mask have a contact in with the latching cantilever beams, so latching beams are stiffer in this X direction and can move in only Y direction. So it will open the switch like to having the displacement in Y direction. And after that, the stress figures are shown at the curved body of the impact mask as well as the cantilever beam. So these the stress caused by this impact are at the impact mask is around 0.3 gigapascal, and at the latching cantilever beam is around 6.5 megapascal. So the third phase at the impact mask, definitely after the phase second, this cantilever beam, when the stiffness of this cantilever beam is dominate the impact or inertial force, so it will come back to their original position, and this impact mask is lashed between these cantilever beams, and the stress at this impact point at the curved body of the impact as well as the latching cantilever beam. So the impact at the impact stress will be the same with the second phase stress, and at the latching cantilever beam, the impact stress is given by around 9 megapascal. So after this contact modeling, we have using this Hertzian model, we analyze about the contact pressure at this impact mask. So which is observed, which is created around 8 gigapascal, and which is quite close to our analytical solution, which comes around 7 gigapascal. And secondly, the contact resistant about, since our contact radius is 27.3 micrometer, and which is higher than the mean free path of electron of the gold material, which is around 36 nanometer. So the diffusion transport occurs. So for the calculating the contact resistance for the diffusion transport phenomena, so the resistance is calculated around 0.45 milliohm for this 0.19 micrometer contact area. So by concluding that our FEM model basically is designed and for the impact sensor was modeled using the Hertzian contact theory as well as the contact mechanics, and the maximum pressure of the contact area was analyzed for the 8 gigapascal using the FEM, and it was quite close to analytical 7 gigapascal. And diffusion transport occurs since the mean free path is lesser than the contact radius. So the diffusion transport resistance was calculated around 0.4 milliohm. So these are our SEM images of our MEMS impact sensor. So right now we are in drop tower testing, and here's the I want to acknowledge the NRF of IIT Delhi and CSIR CD Pilani for my experimental work, and Impact Lab and Dr. Vikrant Tiwari sir for their support in my testing of the devices, and MHRD for the fellowship. Any questions?
Okay, so thank you, Vikram, for your
Yes,
talk. So,
yes, sir.
I have some, so when your talk title is like contact study of MEMS High-G impact sensors, right? So
Yes, sir.
what is this High-G actually for in your case? What is the target?
Yes, sir. So basically, our sensor is designed for 2000 Z, and the pulse width is around 2 milliseconds. And yes, sir.
Okay, so basically, 2000 G, because if you are planning this sensor and this contact study or something, then you should
Yes,
must
sir.
have some application in mind, right? So for what application you are really, targeting this?
Sir, basically the application is like crash detection events. So where there is these are the like passive devices. So we do not need any constant power.
No, so actually, I'm asking this question is because I was in a in a review meeting in DRDO also, right? So
Yes, sir. Yes, sir.
they were also designing a similar, very similar kind of switch for their, some missile applications or
Yeah,
something.
yes, sir. That
So
can be used, sir. In yeah.
okay, so
Yes, sir.
yeah, so
Yeah, one
basically,
second.
so it may be the same application. Actually, I got it.
Yes, sir. Can
And
be used in like.
hmm.
Yes, sir. Yes, sir.
Okay, so one more thing is like how to test this, because
Yes, sir. Sir, basically, right now we are to, try to test this sensor using the drop tower testing, and another method is sir Hopkinson bar test. So by using Hopkinson bar, we can get the sensor tested around 20 to 30,000 G, sir.
And have you done any simulation to, because at this much high G value, right? So once the impact is really there, because whatever simulation values of stress you are mentioning is much lower than the actual fracture limit of the silicon.
Yes, sir.
So why you are so conservative? Like you can, to increase the sensitivity, you can go for thinner beams, which can experience the, stress is a little bit lower than the fracture stress.
Yes,
Uh,
sir. Sir, the beam is chosen around like 5 micrometer. The width of the beam is 5 micron. But about the fabrication compatibility, and second, we have tested our sensor for around 40,000 Z. The survivability of our sensor for the 40,000 Z at the 5 micron beam width.
Okay. And
So
so there is no detachment required, right? So this is only the impact. After that, you do not need to detach the proof mask, right?
yes, sir. I want to detach by the using the electrostatic electrodes.
But how much voltage is required for detaching? Because once there is a dot loop, it is like a locking
Yeah,
mechanism
yeah.
is there.
Yes, sir. Yes, sir. So the
So can you
electrostatic
limit this?
yeah. So, sir, 80 voltage is required. Actually, I have done the experiment that, and at around 80 voltage, so it will delay this impact mask from this cantilever beam.
So this is all from my side. So if any another person has any questions, so you can directly ask the last question. Okay, so thank you, Vikram, actually for the nice talk. So
Thank you, sir.
okay,
Thank you.
so before we move to the next and last oral presentation of this session, so let me tell you, we are running a little bit late. So after this last talk, we will be starting the next session. So even though we had a planned lunch break, so we are sorry that we somehow will start immediately after this talk. So please be there actually, and there is a Professor James Ducree. I think he's already joined. So he will be starting after this talk. Okay. So the last oral presentation for the first session is Mr. Kaustav Roy from ISC Bangalore, and title of the presentation is an experimental study of the acoustic field of a single cell piezoelectric micro machine ultrasound transducer. So let's welcome Mr. Kaustav Roy for his talk. So you can start, Kaustav. Kaustav, I think you are mute, so we cannot hear you. So I think it is Vibhas Nayak, right? So I think your mic is off. We cannot hear you. Can you please switch on your mic? Vibhas, your mic is on.
Hello?
Okay, now we can hear you. Okay.
Yeah, sorry for the delay. I'm Vibhas and I'll be speaking instead of Costa because he had some last minute stuff to attend to. So is that okay?
No problem. Okay.
Yeah,
Thank
so
you.
I'll be presenting on the topic titled An Experimental Study of the Acoustic Field of a Single Cell PMUT, that's a Piezoelectric Micro Machine Ultrasound Transducer. And I'm a project associate who works under Professor Rudra Pratap at MEMS Lab at SENSE, Indian Institute of Science. So, yes. So the motivation behind this topic was that the effects of packaging on the radiation pattern of a single PMUT is not a widely explored area. And from existing literature on loudspeakers, the packaging, or rather the speaker cabinet, can strongly influence the directivity of the transducer. So these are two images shown just for representation. And so I'll talk about what the PMUT is. A PMUT is a multi-layered MEMS structure, and it is fabricated by the deposition and patterning of its electrode and piezo layers on a device layer, followed by the subsequent release by backside etching. And these devices are typically operated at their resonance frequencies. In our case, as you can see at the bottom right, the PMUT is a MEMS structure containing a circular diaphragm with a diameter of 2 millimeters, and it resonates at 50.7 kilohertz. And the device layer here is silicon, while the piezo layer is PZT, that is lead zirconate titanate. So the way we fabricate the PMUTs is that we sputter titanium and platinum on an oxidized soy wafer, where titanium is the addition layer. Then we deposit PZT by sol-gel deposition method. Then we pattern the top electrode and sputter chromium and gold, where chromium is the addition layer for the gold electrode. Then we use liftoff for the top electrode and pattern the PZT and etch it. Finally, we release the device by bottom side deep reactive ion etching. So now I like to talk about the directivity of a piston, which is used to measure the performance of a transducer or a piston here in across different angles of observations. So in that equation, you can see that J1 is the Bessel function of the first kind, A is the radius of the piston, K is the wave number of radiation, and theta is the angle of observation. The takeaway point from here is that the piston's directivity is omnidirectional if the product K is less than 1. So you can see the picture at the side where we have different values of K. As K becomes higher, the piston becomes more and more directive. Then I would like to talk about diffraction. That is, we understand it as the bending of traveling waves upon interaction with some kind of a discontinuity or an obstacle when it's comparable to their wavelength. And based on Huygens principle, diffraction causes the obstacle to act as a secondary source of spherical waves. Now, you can see that there is a tweeter placed on a speaker cabinet, and we see that the direct sound is converted to secondary sources of sound at the edge of the speaker cabinet. Now, this topic is a very big and pedantic topic in the audio and audiophile community. So I'd like to reel the discussion back to PMUTs and see how diffraction can potentially affect the PMUTs in its radiation environment. So we have prepared two PCBs, that is a small PCB and a big PCB, that are respectively dimensioned as 12 cross 8 millimeter square and 24 cross 24 millimeter square. And we measured that using a experimental setup, which I'll speak about next. So yeah, the experimental setup is we basically retrofitted a 3D printer to serve as a 3-axis motion control system, where we converted the printer's printing head to act as a microphone holster. So that allowed us to sample the transducer's radiated sound field in a grid-like fashion. And we performed the scan in the XZ plane, if you can see the picture, and the PCB's breadth was facing the Y direction. And the point to note here is that the PMUT was driven at its resonant frequency of 50.7 kilohertz, which is in terms of Ka is equal to 0.93. So by the equation which we saw earlier, the PMUT should be omnidirectional. So now here are the scan results. We see that the behavior is not as predicted by the equation. We see that there is, for the case of a small PCB, we see that there is a strong prominent mid lobe. And for the big PCB, we see multiple side lobes appearing. So we try to recreate these results in COMSOL, where we simulate a simplified 2D axisymmetric simulation of a PMUT with its package placed on a rigid infinite baffle. The PMOT radiates into a 2 pi steradian space that terminates into a perfectly matched layer. The perfectly matched layer is used to enforce a non-reflecting radiation environment. And just to match with our results, we modeled the residual stress in the PMOT's piezo layer as 300 megapascals. Now, the PCB's diameter over here is based on the breadth of the PCB baffles which you have used in the measurements. And all the physical phenomena were fully coupled in COMSOL. So the simulation for the small PCB shows a good agreement as between the simulation and the measurement. Likewise, we see a similar agreement for the bigger PCB, and this is mostly due to the diffraction effects affecting the directivity of the piston, or rather the transducer. Next slide will show a comparison of the directivity of the PMOT in different scenarios, where we have the reference piston on an infinite baffles analytical solution compared with a PMOT with its diaphragm flush mounted with an infinite baffle, and the two cases which we have physically measured, that is a PMOT with a small PCB and a PMOT with a big PCB. So we see that the PMOT with a small PCB is more directive compared to the big PCB. Of course, there's a relation between this. The takeaway point from this study was that PMOTs are always diced to finite size and bonded onto a PCB package. But due to this PCB package, diffraction effects can significantly influence the directivity of the device, as we had observed and demonstrated by simplified simulations. The objective is that the packages can be potentially engineered towards application-specific requirements, that is to make the PMOT omnidirectional, such as in case of air-coupled acoustic communication, or to improve its directivity, such as the case of rangefinders and all. That's it. Thank you.
Okay, so thank you for your talk. So now we can have one quick question if any of the participant has it, because as we all know that we are running out of time. So
sure.
Is there any questions? Please ask directly. Okay, so it seems like if there is no question, then let's thank Viswas Nayak for his presentation. So thank you. And we are just finishing our session on time. So basically, as I said, that we will be starting a next session immediately after this. So for that, we have Professor Dhiman Malik. Actually, he will be chair for the session. So maybe I hand over to Professor Dhiman for to take over this session.
Thanks, Pushparaj. Good afternoon, everyone. So welcome to this afternoon session of this symposium. So just in order to maintain the time, maybe we can directly go to our first talk, which is by Professor James Dusry from Dublin City University, Ireland. So let me just briefly introduce Professor Dusry. Professor James Dusry holds a full professorship of microsystem at the School of Physical Science in Dublin City University. He has been the founding director of Ireland's first Fraunhofer Project Center for Embedded Bioanalytical Systems. Professor is also an academic member of National Center for Sensor Research and the 3U Joint Institute of Global Health, and the principal investigator at the Biodesign Europe. He has a master's and PhD in physics. Before joining DCU as an associate professor in 2008, he founded and led the group on Lab-on-a-Chip technologies and Lab-on-a-Chip foundry services in Germany. Since 2005, Professor Dusry was also a senior faculty member at the world-renowned Institute of Microsystem Engineering at University of Freiburg. He has more than 400 research publications in the field of microsystem, microfluids, lab-on-a-chip technologies, blockchain, and among them over 100 scientific papers in mostly top quality journals. So without wasting any time, I would like to hand over the stage to Professor James Dusry, and Professor, you can start presenting.
Yeah, thank you very much for your kind introduction. Can you hear me?
Yes.
Oh, yeah, great. Okay, so today I show you a little bit how we try to migrate from research lab to commercial applications in microfluidic lab on a chip systems. And the talk is entitled Digital Twin Technology Enabling an Open Platform Approach Towards Microfluidic Larger Scale Integration and Nucleation of Supply Chains. So I show you essentially the difficulty of characterizing complex, in this case, microfluidic system, why it is so complex. And then we essentially developed an in silico, so a computational approach to navigate around this very fundamental problem. Okay, let me just, okay. So if you want to rephrase the title, it's about the efficient development of microfluidics-enabled solutions for automated sample prep and multi-parameter testing of biosamples at the point of use. So what are the key challenges? Well, one problem is intrinsic to microfluidics as a whole, right? In microfluidics, it's essentially the same physics, the same system as on the big scale, but you have a drastically increasing surface to volume ratio. So if you shrink the size, in this case, of a cube, you get to extremely high surface to volume ratios, which means that, sorry, the clicking there doesn't work, that there is some technological opportunity to leverage these effects like capillary action, mixing, fast temperature control. But as a physicist, I also learned that God is in the bulk and the devil is on the surface, right? So that essentially creates a huge problem towards reproducibility, right? The surfaces are much more different from chip to chip than the bulk, right? And so forth, like, and if you have applications, they have to work reproducibly, otherwise nobody buys them. In lab on a chip, you have a complex interplay, so that's to some regard way more complex than in electronics. So you have microfluidics, but that doesn't help you much. Microfluidics is by itself just a toy, right? You need to know how to manufacture your chips. You need to run a bioassay, and you need some detection. And if you change one component of the system, like if you change your manufacturing technology, for example, that might also affect the bioassay if you change or the microfluidics, or you change the microfluidics, and that has an impact on detection. So it's not so easy to qualify these systems due to the high surface to volume ratios with the irreproducibility of the surfaces and the and the complex interplay of these things. So testing and characterization turns out to be highly complex. Then you have some commercial issues. Typically, like every presentation on microfluidic technologies essentially starts from scratch in many cases. So you have a lot of tools for scientists, but very much lack of standards. We actually just published a paper in Lab on a Chip on promoting a little bit of standards for interfaces, but in particular also for testing. There's a huge need in microfluidics actually for larger scale integration. So of course, not to the degree of microelectronics, but often if you have like a more complex system, actually there is already a lot of products in the market doing very simple stuff. But if you want to integrate like sample preparation and detection with multi-step bioassays and so on, that's really where the market need is, and where they're willing to pay a higher price than let's say for a simple lateral flow test strip. You have an absence of essentially industrial standards, so product development is not as straightforward as in more mature technologies. There's a gap from prototyping to scale up. So a lot of people develop very exciting systems in prototyping techniques like soft lithography and milling and so on, but often they don't scale in manufacture. On the other hand, you carry out essentially some biology, some bioassays, but some biotests on the chips, and if you have ever done that, you need a whole lot of devices to just characterize them, right? So you need like 100 chips or 1,000 chips to just have some sufficient statistics to prove that your assay works to the required performance characteristics that you often don't have if you work with typical microfluidic prototyping technologies. And on the other hand, applications from diagnostics industry point of view only tap into niche markets. So it's hard to reach an economy of scale. And therefore, One measure that I want to show here is that we essentially shift the engineering part to a virtual prototyping. So we test in silico. So essentially we compute the testing to go towards, well, Six Sigma is a very ambitious goal, but in that direction at least, to perform reliability testing, performance optimization towards key performance indicators, and also configurability. So you only have a limited space here on these disks, similar to a silicon chip where you do electronics, right? You want to cram essentially as much function on the chip as possible to essentially make it cheaper and more usable by your customers, by the users. So you integrate, you want to have a high density of space, and that, of course, for the user will then deliver a high functional integration density. So we choose a microfluidic platform called Fluidics. It's very simple, and that's good because it's actually quite straightforward. You have a centrifugal force and a so-called Coriolis force, which you induce just by spinning a disk, right? And as you can imagine intuitively, the faster you spin, the more pronounced these effects. So centrifugal microfluidics is essentially then the interplay from a physicist point of view of inertial forces that you induce by rotation, which is the centrifugal force. That's very intuitive. The Euler force is essentially a rotational acceleration similar to a linear acceleration in regular mechanics. And the so-called Coriolis force, which emerges on flows on a rotating frame of reference. So in a non-inertial frame of reference, where you actually, the flows are deflected perpendicular to their direction of flow. The interesting thing is that that force, even though I don't get deep into that, it becomes bigger than the centrifugal force on typical centrifugal microfluidic systems, simply because it scales with the cube of the spin rate and the centrifugal force with a square. And then you can use, for example, like some non-rotationally controlled forces like the capillary action. And the orchestration of all this with a microstructured substrate essentially creates some functionality on the disk. So the main thing actually is similar to a transistor in microelectronics is the element of flow control. So on the one hand, you have very simple pumping, right? You just put a piece of or a little drop of liquid or some volume of liquid on the disk, you start rotating, and the liquids don't really have a choice. They will all start flowing. On the other hand, if you carry out a biological assay, you don't want them all to come out at the same time, right? You want to hold back some because they might be used later in an assay, and others should be released first. So you need something like valves indicated with the green stuff here. So without them, some liquids will move, the others are held back. You have some sort of a stimulus to remove the barrier, and then if you spin, then also these liquids will move, right? So that is essentially how you can mimic like a bioassay on a disk where you have several steps in sequence, while all the reagents on the disk for practical purpose should be on board at the start of the assay. Otherwise, the user would have to do a lot of pipetting during these stages. So the valve then coordinate essentially so-called laboratory unit operations like loading, metering. All that can be implemented on the disk, and a lot of publications have been done to essentially have the full gamut of a bioassay available. So loading, metering, aliquoting, mixing, incubation, particle separation, solid phase extraction, reagent storage, and detection. All that has been shown. But the key factor, I mean, this works really well on a centrifugal microfluidic platform, so comparable to what you can do in a lab or even better. But you need to coordinate them, and the transistors of centrifugal microfluidics are the valving technologies. The big advantage of centrifugal microfluidics is similar to like a optical a disk carrier. You can use similar detection technologies, optical detection based on lasers, so absorption, fluorescence, chemiluminescence, also implant laser tweezers to manipulate small particles. All that has been shown numerous times. You have surface plasmon resonance techniques that have been used, electrochemical techniques, and a few others. But the thing is, okay, you have the whole portfolio of doing sample prep and detection on the same disk, right, in a very simple apparatus similar to a Discman or something. that those at least who are older like me still know, and streaming and so on. You don't need all that anymore. Okay, so centrifugal microfluidics provides a robust, high-performance liquid handling by unique use of artificial gravity conditions induced by the spinning of the disk. So you can integrate a full bioanalytical process chain, including sample prep, assay, and detection. And in the past, over the last decades, several assay techniques have been shown here symbolically. Actually, they really work on real disks, so immunoassays, general chemistry, nucleic acid testing, and cells and bioparticles. Now, the degree of complexity is very important. So for a lot of commercial applications, that really makes sense, similar to like computers or so. You want to have a lot of storage, a lot of processing power, right? So you integrate a lot of different functions. That essentially the main challenge is there, the valving between them. On the disk, you see some examples, right? We call that a centrifugo-pneumatic valving that I will show you. There's other techniques, but this one is the one I will focus on. So essentially, the arrival of one liquid at one location on the disk triggers a release at a distal location. This is kind of like a handshake mode, which is very reliable, and that's how you can coordinate so many different valves. You can valve at constant spin rates. You can introduce conditionals like and or automation of fluidic networks, controlling like up to 10 valves. Through this particular technique, usually with conventional techniques, you have like a fraction of that, like 5 maybe. And this here is, if you can squeeze the disk even more, you could make that to, let's say, 50 or even 100 valves on a disk. So that's called large-scale integration. As I mentioned, the fluidic function will be integrated through these valvings. Now, and this is used then as a platform approach. So evidently, a valve is not specific to a particular assay application. So once you develop these valving technology, you can generalize that to implement a lot of different technologies. So for this, we created a common platform. So essentially, you have this microfluidic technology for the valving and the different laboratory unit operations. We defined, I'm not showing that here, different microfabrication schemes, how to prototype and then scale them up seamlessly. And then we partner with people for doing the assay development. So the biology and the detection is often like by partners and so on provided. So this is the core platform. And for creating an entire application, you need these two components, usually by partnering. We have seen that there's a couple of pilot applications in these areas, so immunoassays, general chemistry, nucleic acid testing, and cells. And the main applications are health, agro-food, environment, and safety. The library then geometrically parameterizes the different functional elements, so you can handle different volumes because you might have different sample volumes, different reagent volumes, and so on, flow rates and timings. And then it makes sense to that what you prototype can also go through scale up in terms of manufacturing, the fluidic function, and the bioassay. So let's get into large scale integration and how tightly it is connected to reliability testing and failure mode and effects analysis. So this is just an example how dense we compacted function on these disks, right? It's very complex, very hard to explain. This is like a flow chart. I'm not going to go through that with you, but let's say on an abstract level, you have n independent elements. Let's say all of them work at a reliability X. Then the reliability on the system level, so whether somebody buys this thing and finds that if everything works, drastically decreases with the number n. So if you have like n equals 20, a reliability of 99% of all these individual elements for themselves as standalone, you only have 82% reliability on the system level. So that's something users wouldn't really appreciate, that every fifth this essentially wouldn't work. On the other hand, if you ask microfluidics people whether their chips work to 99% reliability, that would raise some eyebrows, right? So that shows you the integration density puts extreme requirements on reliability. That's why we, for example, had this handshake mode valving that I briefly introduced on the previous slide. So it's absolutely critical, high reliability. So how to make chips and how to make them work? It's microfluidics technologies are mostly developed for applications in medicine and life sciences requiring large-scale integration or larger scale. Again, that's orders of magnitude less, of course, than in microelectronics. even prior to deployment in real-world applications, you need comprehensive test series to carry out such translational research. Like if you take, for example, tests for the coronavirus now at present or so, you cannot just throw them on the market. You need to have like 1,000 chips or test kits or so to show to regulatory offices that they work. So these microfluidic solutions need to implement large-scale integration for sample prep and multiplexing, work reliably. You need to have a plan for scale-up of manufacture that is astonishingly often neglected. And you need to, these systems also need to work under different ambient conditions, so pressures, humidities, transportation, and so on. And that needs to be done through the life stages, so through manufacture, through storage, like a chip, through transportation, through different logistics companies, manual handling, activation, on-site, and operation. If one of that fails, the whole system fails, right? So, and for all this, evidently, you need some reliability testing by either standards or standard operating procedures that you create. So let's show the dilemma now. Application in point-of-care testing, let's say, should aim towards something, maybe not necessarily exactly this, but this famous Six Sigma. You need a large number of devices to even show something in the Sigma language, right? Thousands of chips often. But in prototyping in academic environments, you usually make more like 1, 2, 3, or 5 chips rather than these, especially if they're highly integrated. So you need like a system level testing would be very expensive in RTD because that's all made manual. It's very hard to then on a system level to do a failure mode analysis because you don't really see why the whole thing failed if you already have the entire system. So evidently then the recipe would be to do a component level testing. And in particular, the most vulnerable element on the disk is the valving. So this is a function of the experimental input parameters. And what we do here is we reduce them to what I call experimental primitives. So things that are easy to measure, width of channels, depth of channels, volumes of liquids, right? This is where we know best what the tolerances are that impact then reliability. So for manufacturing is the geometrical fidelity of essentially width and depth and shapes, right? Mostly linear dimensions, metering of volumes. You can get that with the data sheets, let's say of a pipette, for example, that you do, or it's pretty easy to establish. It's much easier to measure the tolerance of a defined pipetting volume than to measure the reliability of an entire integrated system. We do that now instead of experimentation by so-called virtual prototyping or digital twin technology. So we identify the dependence of the key performance indicators for the system level performance, let's say for the amount of liquid that eventually arrives in a detection chamber. And then we depend the dependence of this on these primitives, so the accuracy of manufacturing and volumes. And these can often be taken from simple data sheets. Like if you have a milling machine, you pretty much know, I mean, you can measure it, but you can even look at the data sheet and they tell you you have an accuracy and precision of this and that. So often there's not, at least you have a good estimate of that even without doing any measurements. The deviations come from different sides. So you have systematic deviations that you need to compensate, like ambient conditions, temperature, humidity, atmospheric pressure. Of course, all of them impact microfluidics. You can do that, for example, on-site measurement, like just these are very trivial, like a standard household gauge or so would do that. Manufacturing, for example, thermal shrinkage, rounding of edges, and so on can be studied and factored into the design. Yeah, so that requires characterization and process optimization to have a grip on that. And then you have statistical deviations, for example, in the manufacture geometries like width and depths might have a certain delta essentially. Surface chemistries like contact angles and so on, roughnesses are often either not well defined, or if you change the manufacturing technology, you might change this. So that has to be factored into your design in order to achieve reliability. In fluidics, you have like volume definition, on-chip loading, off-chip, the loading with a pipette of the chip, and the spin rate. So for this, you can, if you do this in silico, you can optimize your structure to be very forgiving for tolerances arising from these statistical deviations. Otherwise, you don't have a chance because you cannot get rid or compensate statistical deviations other than you whatever, spend way more money on your manufacturing technology. And for the bioassay side, which is less the subject of this talk, but of course very important, essentially only test series will help you. So you need to have some scale up of your manufacturing technology available, which also has to meet requirements on tolerances in order to make meaningful test series that statistically confirm that your assay works. We focus here on this part. So the point is, if you look at tolerances, if you have small tolerances are always great for an engineer because they are typically enhancing your reliability, but they cost a lot, right? To have an injection molding process that has very low tolerances, for example, just have to spend a lot of money, and your application might not let that happen because then nobody buys this thing anymore. If you have large tolerances, the costs are usually better, right? It's cheaper to make it, but of course reliability suffers. So you have to kind of find the sweet spot between the small and large tolerances that have the right compromise between cost and reliability. And these are the tolerance forgiving designs. So for example, if you look at our valving technology, which we call centrifugal-pneumatic, essentially these larger scale integrations that you've seen before are essentially based on this technology. So you have an inlet reservoir, a connecting channel. Here you see the cross-sectional view, and an outbound channel, and a so-called compression chamber filled with gas. So this is a dead-end channel. This is closed. This is open. You have a vertical through hole connecting essentially this here with an outlet. And this here is in the lower plane. So this is a two-plane thing. And these planes are sealed by a membrane, which is here in the purple. And that's a dissolvable film at a given actual position, and that is impermeable to gas, but dissolves in liquid, so in the sample. The whole thing is at ambient pressure, so that's the initial pressure for here, and on top of the liquid column, a centrifugal field then moves essentially this liquid into this channel, and you have a certain liquid level difference created by the centrifugally induced pressure and counteracted by the compression of this gas here. And liquid meniscus essentially then decides if the valve opens, right? So if that meniscus, because it's a liquid, gets in touch with this here, this is similar to like a paper tissue type of thing, a little bit more sophisticated, then that opens and the liquid essentially flows out here. So you have a meniscus position that depends on the strength of the centrifugal field, and a position capital Z would then determine whether the valve opens. The good thing about the technology is because the devil is on the surface, the technology doesn't really depend on the contact angle and the surface tension, right? So it's a pretty brute force approach here where you have pretty simple equations that govern that. So if you load the disk, you have some intermediate state, right? So you introduce just a liquid volume, then you at a critical spin rate, that meniscus has risen to touch essentially the dissolvable film, and then essentially the outlet here is opened, and then the outflow would be that above this critical frequency, the liquid goes into the lower level to an exit here. So the equations are pretty simple. You essentially have an equilibrium between the centrifugal pressure, the ambient pressure, which assists essentially the centrifugal pressure, and the counter pressure. You can express them essentially in abstract equations, right? They're very simple, essentially some freshman or even high school physics. And then you can calculate the spin rate, which sets the radial extension or the liquid level difference, which is delta R, that would be between here and here, and the mean radial position of the meniscus, which would be somewhere here, for example. So you have a liquid segment with U0, the radial measures, I don't get into the details, pretty straightforward. Centrifugal pressure calculated here, compression. You have dead volume, so essentially an initial state of this volume at ambient pressure. And so you create a spin rate as a function of different geometrical parameters, the liquid volume, the ambient pressure, and these measures of the the liquid segment here that is in the channel. But so this is for the omega. Often we want to know now for the valving function, the Z, right? Because the Z is the discriminant whether the valve opens or not. If Z equals the capital Z, then the valve opens because then the meniscus touches the membrane. So this will be a function of the what we call the primitives, right? So the real down-to-earth measures here, which will be the radial position of the valve, the distance of the or the height of the dissolvable film valve, the cross sections and depths of these chambers, and the dead volumes of these enclosed gas volumes. Right, it's pretty straightforward. I mean, the equations look quite complex, but it's essentially very simple geometries like of little squares or rectangles and so on. Right, so radial positions, cross sections, chamber depth, dead volumes, the loaded liquid volume, so what you pipette into the disc, the ambient pressure and spin rate. So all this here is essentially, you know, these values, you can measure them much better than these delta R's and R bars and some other stuff. And you know the tolerances. If you have like a milling machine, you know the accuracy and precision of these parameters, right? And the same for the pipette. You usually know how accurately you can pipette. It's printed on the pipette, and this can be measured. And the spin rate is even a closed. The motor itself essentially has a closed loop system to set the spin rate. So essentially, you can create a critical frequency which is required to set the liquid meniscus to touch the dissolvable film and therefore open the valve, expressed as a function of geometry, the loaded liquid volume, and the pressures. And then evidently the deviation of that is a function of the deviations of these experimental primitives, know their tolerances. Okay, so in multiplex valving then, what you do is to release liquids at different stages in time, right? This is on the x-axis and the spin rate on the y-axis. So you raise the spin rate, that's one example, and then at different stages, so at different levels of the spin rate, you open the valve. So these are these opening frequencies. In the multiplexing, you need to separate them to have a time sequence so they don't open all at the same time. So let's say you have 3 frequencies. You have a practical envelope, like you cannot spin as fast as you want. That's like a centrifuge. I mean, there's some safety concerns. The motor might have limitations. And also there's usually a lower limit. But essentially you have a certain envelope that you can really use. And the spreading of these experimental primitives leads to kind of a spreading of these. So these frequencies are washed out. So if you want reliable valving, you need to space them sufficiently so they all fit into that envelope. So that means that if you move from lines to these bands essentially, then that limits essentially the number of independent steps, so the integration density of your system, and you can only enhance it if you decrease essentially these widths. So multiplexing is limited by the ensemble of these different frequencies and their width. So we have random and systematic errors. For example, the dimensions are statistical, like lateral width and depth of channels. The assembly of this dissolvable film, which is a separate material, essentially might have some shifts. So that's how you get some tolerances. The liquid volume for pipetting or upstream metering on the disc. The ambient pressure is weather and altitude dependent, actually quite drastically, and the spin rate. Right, the spin rate turns out to be negligible. The ambient pressure is systematic, so it can be compensated. So the main statistical error lies in the dimensions and the liquid volume. Right, this is where you cannot avoid certain statistical variations that do actually have a non-negligible impact on your result. You need to study the bandwidths as a function of these parameters. We do that on the one hand by Gaussian error propagation, so essentially building the derivative for the KPI function that depends on these primitives. These are very long equations and so on. I'm not printing them. This is like the analytical approach. This, of course, assumes that all these parameters are independent, and you need to validate that, of course, that you pick them right. But of course, the depths and the widths of a channel, for example, are independently manufactured. This approach, this analytical approach, is great for design optimization because you have formulas, right? But we also use a Monte Carlo simulation, which is essentially rolling the dice to essentially just simulate experiments, right? So you essentially simulate the statistical spread by doing a lot of computational runs, and each run has a different set of experimental primitive with a given spread, a Gaussian distribution of the spread according to the data you have on these the dependency of these technologies, or the bandwidths, or the statistical error that you know that these parameters like width and depth of channels have as a result of your manufacturing technique. So this is very reliable, but a huge computational effort. So to determine just a statistical deviation, let's say, of your target frequencies, this is very good. And this is very good to optimize the design, so you can shrink the statistical deviations and fit more function onto the same disk, more independent elements. We do that by virtual prototyping. Now, that's not a very intuitive thing to do. For example, it really depends on a lot of parameters, but I show you here like a Monte Carlo approach where we have these critical frequencies and the statistical spread as a result of the Monte Carlo simulation, right, for an intuitive design. And here you can easily see, just for the example here of this peak, that you have a much smaller spread here of the thing when you use this analytical approach on the last slide, for example, and then the computation can automatically minimize the width. Here you can look into configurability. So how can you achieve, for example, and here if you have like valves at the same radial position, that they all kind of are simultaneously released, or released, for example, in a certain sequence. And this here is just one example. I mean, there's a whole lot of parameters you can tune. If you change the volume of this compression chamber, which is the counter pressure essentially against the centrifugal pressure, then the computation model lets you essentially forecast the volumes of that chamber that you need to do to release the things. If the valves are all staggered in the radial direction, you know how you have to tune these volumes to enable a reliable sequential release of reservoirs that are positioned at certain radial positions. You can also do virtual prototyping on the manufacturing itself. So here is like a mold flow simulation. We can say, okay, if I have a certain design as indicated here, you know, what distortions, what deviations from the target parameters do you get in order to fill that into the model? We have a couple of pilot applications, just very briefly. I mean, we did a lot of that, like general chemistry immunoassay panels. We have a multi-parameter liver assay panel, fluidic automation of all the sample preparation, reagent storage, and detection with this technology from a colleague of mine, and we deployed that in the field and calibrated that against the target or the clinical gold standard methods, and are in pretty good agreement. For nucleic acid preparation, we integrated like a complex multi-reagent step. Like this would, for example, be some template for a coronavirus or mRNA test or so, you know, where you have like a sample purification and concentration steps, and detection all integrated on the system, even a slight heating step to essentially amplify then the product for detection. And we published a lot on this, so I just give you like a brief insight what this does here. This is the instrument that we're using with a spindle motor, a temperature control, like this here is the heat control unit, and detection by a photodiode. And for cells and bioparticles, we essentially should have a video here where particles, sometimes you want to find certain target cells, like let's say cancer cells, in a huge background of other cells. It's like a needle in a haystack problem. And we tagged essentially the target cells with surface-specific magnetic beads that are coated against the surface antibodies here. And we separate the background cells, the target cells, and the unused magnetic bead cells here, collected them and counted them. We did a lot more here, but I don't have the time to get into that. So in summary, we use the centrifugal microfluidic as an example of a lab-on-a-chip platform that provides high-performance sample prep with downstream detection. We showed larger scale functional integration to a significantly larger degree than the state of the art has done. Before we introduced that, the virtual prototyping essentially is based on modeling the key performance indicators as derived from experimental primitives like linear manufacturing scales and volume definitions through pipetting, which are known, right? So you know essentially the dependence on the performance, like the switching frequency of a valve from parameters that you know, so you can skip essentially the testing of large test series and use that. You have an in silico analysis that replaces costly experimental testing. You have an automated robustness optimization and automated configuration towards high spatial integration density. And towards commercialization, this will, of course, allow to tap into economy of scales. With the platform approach, you essentially have the same microfluidic technology, similar to have like the same way how you make a transistor, and they go into whatever, an iPhone or a PC or like an onboard system and so on. It's not a fundamentally different approach. That's how you reach an economy scale, despite of tapping often into comparatively small niche applications for a lot of microfluidic systems. You create like design tools, like similar to SPICE or so in electronics, or some MEMS tools, and create like foundry services, you know, which if you have predictable reliability by design through these tools, you can kind of ship it to somebody who makes it, and you wouldn't have only very little doubt that it works. And that also creates, like on a commercial level, then supply chains. So thank you very much for your attention. Actually, this is the team that has done a lot of that at different stages. Thanks a lot, and be happy to answer your questions.
Thank you, Professor Dusri, for your nice talk. So we have time for a couple of questions, maybe, if anyone wants to ask. I have one question. So you talked about this technique, and you told that there are few concerns like the ambient conditions, manufacturing issues, and so on. So what will be so if you consider the scalability of this kind of technique, so what will be the main challenging factor in determining the scalability of the proposed technique?
Yeah, the main challenge is, I mean, it's in principle for a researcher, the tolerances can all be managed in your research lab, right? You can have like controlled lab conditions. You can buy a very expensive milling machine, buy some state funding or so. But if you scale it up, right, and put it in the place of a consumer, you know, especially if it's a point of care for home testing, the price will be critical. So all the fantastically low tolerances that you achieve, whatever with super expensive 3D printing or ultra precision milling, nanoscale milling, or sub-micron scale precision and so on, that in theory are possible, are not transferable to a manufacturing technique that would meet the target price that customers would pay for it, right? So it's really like the scale up of manufacturer. And if you talk to companies who really support the manufacturing, right, they tell you that often they get designs from exciting startup companies who only prototyped it, and then often they have to start from scratch the design because it's not compatible with the scale up. In terms of doability, so certain geometries or so might not be like undercuts or so are not compatible with typical injection molding. Cycle times in injection molding, which is one of the most standard technologies to structure and replicate essentially microfluidic chips, at least those single-use ones, you know. And the tolerances, of course, in injection molding can get fantastic tolerances, but it's very, very expensive. You know, you have to change your tools, which are reasonably expensive, you know, a lot of times, and so on, the process development times. So it's usually finding the right compromise between what is doable in general for a researcher with high-end equipment and what is feasible to a commercial application, right? And that concerns essentially everything. In addition to, as I said, the changing conditions in different ambience, right? In your lab, you probably don't put your chip into the sunlight directly or so for days or even months. At the consumer level, you don't have controlled environments, don't have professionals who are paying a lot of attention to what they're having, and they still expect it to work reliably when they open it and use it. So that's one of the challenges.
Okay, thank you. So any more questions? If you have any question, you can directly maybe ask Professor Dusri. Okay, if not, then maybe we can thank Professor Dusri once more for his very nice talk, and maybe we can move to the next presentation now.
Thank you very much.
Thank you. So the next presentation is by Professor Toshiyuki Tsuchiya from Kyoto University, Japan. So Professor Tsuchiya received the MS degree from University of Tokyo, Japan, and PhD degree from Nagoya University, Japan in 1993 and 2004, respectively. He worked with Toyota Central Research and Development Laboratory from 1993 to 2004. In 2004, he joined Kyoto University as an associate professor, and now he belongs to the Department of Microengineering, Kyoto University, Japan. He is currently engaged in the research of silicon surface micromachining with its application in MEMS, mechanical property evaluation of micromaterials, and reliability of MEMS devices. So his presentation title is Single Crystal Lithium Niobate Piezoelectric Vibratory Disc Gyroscope. So I will invite Professor Tsuchiya to kindly start his presentation.
Okay, hello. Can you hear my voice?
Yes, it is clear.
Okay. Hello everyone. My name is Toshiyuki Tsuchiya from Kyoto University. It's my great pleasure to give this talk to all in this nice conference, and it is very nice virtual platform. And I also would like to say thank you for committees who invited me this conference, and especially Professor Prempal of IIT Hyderabad invited me this conference. Today I'm going to talk about new vibratory disc gyroscope using single crystal lithium niobate piezoelectric material. This work is a collaboration with a company named Tamaga Seiki Corporation in Japan. First of all, I would like to talk background. In Japan, all over the world, automated driving technology attracts us in order to realize more convenient and safety society. Japan government conduct a big project to realize autonomous driving, and now we started partial automated driving in public road, and in the near future we are going to full autonomous driving by using MEMS technologies. In order to realize full automated driving, we need to localize the car, and in terms of the Earth, mainly the localization is done by using GPS, satellite-based localization, and also the feature-based visual localization by using camera, and also radar, and also LiDAR is used for the localization. But if there's some troubles or in a bad weather or in a tunnel, and this information is not provided, we need inertial navigation by using accelerometer and gyroscope to know the car's relative position by using the information from these sensors. in order to the needs for the inertial navigation can be found in this slide. In the tunnel, there is no signal from the GPS, so the position accuracy is low, and with the inertial navigation, the localization is realized by this sensor. Also, in the downtown, there's a big building that needs to receive the signal from the outside, the GP satellite. So, with inertial navigation, the car position is accurately recognized. So, in order to realize this kind of positioning, there is a requirement for the gyroscope specification. The most important parameter is bias stability, because the gyro output is the angular rate, so we need to integrate twice to get once to get angle, so that 0-point offset bias is very important to get the accurate azimuth angle. So in order to realize for the automatic driving, the required accuracy of localization is 30 centimeter or smaller. In order to realize this accuracy, the bias stability of 1 degree per hour or less is required. If we consider the error of smaller than 30 centimeter on traveling at 80 kilometer hour per hour while traveling 1 kilometer. And this is very small, which is much smaller than Earth's rotation. MEMS technology gives us some gyroscope devices, but the performance is not reached to the target. This is one example of the MEMS gyroscope, which is developed by Tamago Wasei Corporation. The cost is low, but the bias instability is much higher than our requirement. So the current automatic driving test or driving is done by using fiber optical gyroscope, which is very good performance, but the cost is very high. More than 2, very high, and very high. And there is some device which has there is some MEMS gyro devices which has very good performance, but because of the tuning or the calibration, that the cost is much higher than. I'm sorry, this K is missing in this price, and our target is like this. So as I mentioned, that the automotive MEMS devices has very low cost, but the stability is not good as enough. And the fiber optical gyro and high performance MEMS has such as good performance, but cost is too high. So our target is like this, to develop the device with good bias stability with a relatively low cost to equipped to the automobiles. Our approach is to find a new material to construct the device, which has high electromechanical coupling coefficient and high quality factor. Those parameters is needed to realize high performance gyro. And the conventional structural materials, silicon, quartz, piezo, PZT, zirconate, titanate, has shortage of the performance. But in this research, we use lithium niobate, which is a single crystal material and has piezoelectricity, and it has high electromechanical coupling coefficient and high Q because of the single crystal. So we are going to use this material. So our target is like this because lithium niobate has single crystal, so it will have high Q, and because of piezoelectric effect, we have good electromechanical coefficient, which expect the much better performance compared to high performance MEMS gyroscope in our in previous research. Single crystal lithium niobate have already been used a gyroscope device available from Tamagaseki, but the device is tuning for structure, and bias stability is relatively good in among the MEMS gyroscope, but because of the structure, it has a problem of quadrature vibration and the LC coupling because of this structure. So what we want to aim is to realize, provide the axisymmetric structure, which is disk. This image is a wine glass hemispherical structure, but we are aiming this first disk structure. And the vibration mode is wine glass mode like this. It has small quadrature and it is robust to vibration input. So we expect high performance. But the major issue is the anisotropy of material properties because this is single crystal. So our research objective is to develop the low-cost MEMS vibratory gyroscope with bias instability of less than 1 degree per hour or localization. So in this talk, I will introduce piezoelectric this gyroscope using single crystal lithium niobate. And in this talk, I will talk about design and fabrication and measurement, initial preliminary measurement of this gyroscope, especially about the optimized wafer orientation and electrode pattern to meet the problem of the anisotropy of single crystal. Operation principle of this gyroscope, I think you all well known, but I will explain. The disk is drive this wine glass mode like this, and when the disk is rotated around the 3 axes, this vibration rotates somewhat. This rotated vibration is superposition of drive mode and sense mode, which is 45 degree rotated from the drive mode. So if we measure this sense mode vibration, we can get the Coriolis vibration. In order to think the optimization of the wafer orientation, I will introduce the governing equation of the in the material. This is the piezoelectric coupled equation of lithium niobate, which contains the elastic matrix and piezoelectric matrix and the dielectric matrix. And this is the piezoelectric properties of lithium single crystal lithium niobate. And this is the parameters. As you can see, because of this single crystal and anisotropy, it's difficult to get the uniform vibration in each direction. So in order to mitigate the anisotropy, we consider the wafer orientation. We optimize wafer orientation. In disk-shaped gyroscope, we can assume the plane stress condition in which the 3, 4, 5 axis stress is 0. So the compliance matrix here is expressed or omitted like this. and only these 6 parameters should be considered in the elastic covariance matrix. So in order to realize uniform elasticity in plane uniform elastic constant, we need to optimize the angle to make these parameters is constant irrespective to in-plane orientation. So the elastic matrix of the lithium niobate is rotated by Euler rotation, and the first psi and theta rotation gives wave orientation. So this S dash dash indicates the matrix of this orientation. And if we see then we rotate this matrix again around this on this disk to check the change in elastic parameters, and we found that if these highlighted parameter is 0, that there is no dependency on the wafer orientation in elastic constant. So we introduce the coefficient of variation of S dash 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 1, and we mapped into the arbitral orientation in these figures. Then we found that the two orientation 0 and 0.65, and its equivalence shows a very small or almost 0 dependency on the orientation, in-plane orientation. In short, there is a two good orientation, two optimized orientation, Z-cut wafer and 155-degree Y-cut wafers. But among them, this Z-cut wafer has very small electromechanical coefficient, so we choose this 155-degree Y-cut wafer for this experiment, for our devices. So this is the elastic and piezoelectric and dielectric matrix of the 155-degree Y-cut wafer coefficient. And we can see the in-plane coefficient is almost constant, but there is an anisotropy in still there is an anisotropy in piezoelectric coefficient, as shown here, especially D31 and D32 is very important in the next slide. So we needed to consider the electrode. So as I mentioned, that D31 and D32 is different polarity. So for zero mode vibration like this, it's very easy actually. By applying the voltage in the plane electrode, automatically this kind of zero mode actuation is realized. In order to realize 45-degree mode, we check the wave if we check the strain distribution at the 45-degree mode vibration, and we found that this kind of strain is generated. So we decided to 8 electrode arrangement by applying the opposite polarity voltage in neighbor electrode, which causes a 45-degree vibration, as you can see. So in summary, the electrode design like this. We have a disk resonator made by lithium niobate, and for the zero mode actuation and sensing, we put the plane or electrode inside. For the outer mode, 45-degree mode, we arranged 8 electrodes for actuation and sensing. In reality, we divided both inner electrode also for experiments. So we arranged this connection to actuate the device and sense the vibration. This optimization is confirmed by FEM simulation, and we verified that the 0 mode vibration and 45 mode vibration by applying the voltage respectively, and we also confirmed that high electromechanical coupling coefficient. Fabrication. This is very simple. We use a single crystal lithium niobate wafer, and using conventional standard microfabrication technology, gold electrode with chromium with adhesion layer is patterned on both sides with same pattern like this. Then the 4-inch wafer is cut into disc shape by using core drilling machine, which has a tool of cylindrical tool, and grind. By using grinding technology, we cut out the disc of about 26 millimeter diameter and with hole inside at the center of 4 millimeter, and thickness is optimized to avoid spurious vibration, and the thickness is 330 micrometers. And the fabricated disc is inserted into the socket, custom-made socket to make the electrical contact to use a pin, and first measure the electrical impedance using impedance analyzer. And we check the impedance for 0 mode and 45-degree mode, and we observe the resonance at about 95 kilohertz as designed, and the frequency split about as fabricated. Disc has very small delta F frequency split of 2 mode, which is suitable for disc resonator. The measured electromechanical coefficient is well agreed with simulation, but the Q factor is not high as we expected, but it's enough for the experiments. But in order that this low Q value is caused by poor massing process or anchor loss in the middle, so we need to optimize the process and assembly to increase the quality factor. And the vibration, wine glass mode vibration is confirmed also by using optical laser heterodyne vibrometer, and horizontal vibration with amplitude around 100 nanometer is confirmed, and so the observed vibration is wine glass mode. Then we operate it as a gyroscope. The measurement set up like this. This is a disc resonator assembled is a socket, and the output is connected to locking amplifier. This is a rate table, and we apply the angular rate, constant angular rate. Gyroscope system is realized by using digital locking amplifier from Zurich Instruments, and we use the closed loop driving with phase lock loop circuit, and with a constant amplitude control using PID function of the locking amplifier. In this step, for the sense mode in this step, we use open loop detection. Just the output signal is demodulated by the actuation driving signal to get angular rate. This is output on applying the 30 degree per second constant rotation. We observe the good response of output from the angular rate, but there is there's some drift during the measurement. The sensitivity scale factor is measured from the similar experiment, and we found that it has a very good linear output, and the scale factor is 0.34 microvolt per degree per second. And if we considered this is without no preamplifier after the sensor output, it seems to be good value. And this is bias instability plot, and this is very preliminary results. So the still bias stability is not good as even as a MEMS gyroscope. But by optimizing by using a closed loop force rebalance loop circuit control system, we will get much better results. So in summary, we have proposed the new type of disk gyroscope using a single crystal lithium niobate. And in order to realize mode matching in between the driving and sensing mode, we optimize the crystal orientation and optimize electrode arrangement. Fabricated device at good mode matching as we designed, and we observed angular rate output, and we have demonstrated the capability of high performance gyroscope for automotive driving. That's all, and thank you for kind attention. Thank you.
Thank you for the presentation. So the floor is again open for few questions. If you have any questions, you can ask directly. Okay, again, I have one question. So your measured quality factor is not very high. So what could be the reasons and how you plan to deal with it?
Okay, we expect the much higher quality factor, but currently the quality factor is about 100 or 500 or 1,000. This is one of the reason is damage during the machining process and the edge inside outside. This large roughness, so we need to polish this edge to improve the quality factor. And also we suspect the anchor loss, so energy loss from the socket. We use resin or resin for the package, and it is not stiff enough to, and the vibration energy lost and here. So we needed to improve the package or assembly process.
Okay. So what is the typical dimensions of this kind of custom packaged gyroscope? So what will be the typical different dimensions or
You
the
mean that
size of this packaged? The entire packaging.
Our final target is about the 1 centimeter square, including package, but the current is not much larger than that.
Okay.
Is that okay? I mean that this package is around, I guess, the 40 millimeter square, but this is the first prototype device, and we want to reduce the size in the future.
Yeah, right.
And the target size is around 10 millimeter square or cubic. including the circuit and the packages.
Okay. Okay. So thank you, Professor Suchiya, once more
Thank you
for
very
your
much.
very nice presentation.
Thank you very
And
much.
now we can again move to the next talk, which is by Professor Yan Jing from Southeast University, China. So Professor Yan Jing is a member of Jiangsu Key Laboratory of Design and Manufacture of Micro Nano Biomedical Instruments at the Department of Mechanical Engineering in Southeast University in China. In the recent years, his lab undertook a number of major scientific research projects in the area of MEMS microstructure, processing technology, CAD and CAM technology, and in general in MEMS and NEMS research. So I would like to invite Professor Yanjing to kindly start his presentation.
So, okay, thank you, Professor. Thank you for the introduction. So I'm I'm Xin Yan from the Department of the Mechanical Engineering, the Southeast University. My topic is the structure facet recognition for sapphire crystal in anisotropic wet etching. And the outline of my topic is the motivation and the experiment on the H rate distribution of the sapphire. And then I will move to the structure facet recognition of the H geometries and the H rate model of the sapphire based on the step flow mechanisms. And then we will set up the Monte Carlo and the level set simulation tools on basis of our experiment data and the calculation model. So the motivation, as a simple and reliable method to fabricate sapphire microstructures. So the wet etching of sapphire is generally performed in various mixture of the sulfuric and the phosphoric acid with different ratios. So this work is about the fundamental work to explore atomistic origin of the anisotropy of this material. So we will review some step flow model of H rate and understanding the anisotropy of such kind of material. And this research will bring the practical tools in the micro and nano fabrication of sapphire, and then understanding the predicting the H geometry by simulation, these kinds of simulation methods. So this is the setup of the experiment in order to identify the H-rate distribution of the sapphire material. So the hemispherical samples of the single crystal sapphire with radius about the 20 millimeter was mechanically grounded, laminated, and polished in a very similar manner of the specimen from the Professor Sato Nagoya University. And the top of the hemisphere was orientated towards the C plane, the 001 the directions, the similar as the coarse material. And one reference flat was also machined on this sample to serve as the reference for the measurement. And this hemisphere was wet etched in many kinds of different mixture by the volume of the sulfuric and the phosphoric acid. So in order to determine the geometry and the center of this hemisphere, and we measure the longitude and the latitude. So sampled every 2 degrees in theta and phi. So we define the longitude and the latitude. So in this manner, so we can see that the H rate of the quartz is similar as the new H rate of the sapphire, and most of the orientations has a very low H rate comparing with the silicon. And also we can see the Z direction of quartz appear as the local maxima. So here is we got very right. That means the H rate is very high at the center. And then the sapphire, the center we have relatively lower H rate. And similarly, the H rate distribution of the cores has three kinds of the three symmetry things is the crystalline structure, and also the sapphire displays 6 high H rate regions. We can see these three. It's also follow the three symmetry of the material, and all the other orientations belongs to a very low H rate region. So traditionally, the large number of these low H rates of orientations is difficult for us, for the designer, to identify the transit and the stable orientation planes appear during the aging. And then we have tested the concentration dependent of the H rate. So to address the concentration dependent of this material, so this slide shows the result obtained from 3 hemisphere aged by the different ratio of the acid, the 1:1, 3:1, and 6:1 at 236 degrees. And in addition, the 3 H rate distribution exhibits the expected 3/4 symmetry about the C axis, the C plane. So it shows like the H rate curve from this figure, the H rate curve of the 1,1 minus 2, 0, the crystal zone always contain the 3 peaks, while the H rate curve for the minus 1, 1, 0, 0 zone always contain 2 peaks. So the global maximum always located at one of the 3 peaks in the 1, 1 minus 2, 0 zone. That's the property, H rate property, that's the of this material. And from the experiment, so we can see we also test the temperature dependent of the H rate of this material. So the change in the aging temperature does not influence the characteristics of the H rate distribution in any essential manner. So at the first sight, we can see the 3 H rate distribution always are very similar. So simply scaling down the temperature decrease the H rate. So however, we can see there is some very small changes, such as the move of the maximum and the local maximum H rate orientation. It could happen, but it doesn't move so significantly. So in overall, regarding the lowest H rate, so the temperature source is influence a lot. When we lower the temperature and the H rate slow down very fast. And it is also so, it's mainly the lower H rate planes and orientations always distributed near the equator. So with the value almost near to 0 for all the temperatures. And with the 3 temperature, the H rate coming from the 3 temperatures, it allows us to plot these the figure of the apparent activation energy for any planes, to any orientations of this sapphire material. And according to the experiment data, the H rate followed the same order in which the activation energy increased. So similarly, by using the experiment method, this kind of in our study, so the other H rate, the H rate in the other temperature, sorry, can be estimated. So okay, for this convex structure, so with the experiment data, so we can investigate the formation of sidewalls on the convex structures. So here is the common for the bottom surface substrate for the industry. We call this PSS, and result from the circular mask pattern. So from the top of the aged structure, it consists of a round mesa resembling a cylinder. So below the mask, it has a very It's not a long distance neck like this. And the bottom of the structure consists of the pyramidal base. So for the footing structure, we call this footing structure. And initially, this is the initial structure. So we can see the three-fold symmetry about the C-axis, and we have totally the 9 structure planes. They are from the A1 to A6 and the B1 to B3. So because of the crystallographic plane on the footing structure, so that can be the orientation and the orientation and the index can be easily get from our experiment data. So here is the H rate get from the equator, and because of this crustal plane will have the local maxima along the equator. So we can see the experiment agree well with the experiment result. And after further etching, so we can see the A1 to A6 plane will gradually dominate the structure of this footing base. So this also strongly suggests that the experiment database obtained in this study can be used for the numerical prediction of the evaluation of H front for any given sapphire wafer, such as we can etch in the R plane or other planes for the deposition of the gallium nitride material, other material. So as well as optimizing the design for the mask pattern. So here we also can identify the concave structure etched on the C plane of the sapphire. So even we have the simple mask pattern, a square mask pattern. So after H for some times we will get at least 10 stable structure planes. So every structure planes can be identified by our experiment date. This is the triangle mask pattern with some rotation to another angle, and this is the circular pattern, but create the concave structures. And next, let's move to we will set up the relationship of the H rate of a crystal plane to its atomistic structure according to the crystallographic theory. So this is the basic crystal plane for the sapphire crystal. We have R plane, N plane, A plane, and of course C plane. And we will use the step terraces structure to analyze the crystallographic plane. So here, with this assumption, so we have the terraces planes, and we have the step structure, we have the text structure, we have the kinks, and the etching will happen mainly on the step structure. So with this assumption, we will examine the crystal zone, the two important crystal zones with the maximum H rate orientations and the most number of the local minimum and the local maximum H rate distributions in the H rate distributions. The crystal zone 1, and the first crystal zone is the -1, 1, 0, 0. This one, that means we will examine all these planes along this way, and then we will observe. We will study the atomic structure of another crystal zone of 1, 1, -2, 0. So that means we will examine the orientation planes along that way. And because of the complexity of the sapphire, comparing with the silicon, the sapphire has the aluminum and the oxygen, two kinds of the items. That means we need to simplify this atomic structure if we don't do this according to the same manner we in our previous study on the silicon material, so we will get more than 500 kinds of the items, so needs to be considered and calculated in the system. So here we select a crystal unit. That means the cluster. That means a number of the items will organize as the cluster items. So we will remove these crystal unit and define the step terraces structure according to the a cluster, several cluster of items. So this is the original. Item structure with the aluminum and the oxygen items, and this is the simplified item. So we can see when we cut with an angle from the 001, the C plane, so we can see clearly the step flow structure. So here we need to determine some the fundamental structure planes like the primary crystal plane in the silicon, like the silicon 111, the silicon 100, and the silicon 110. So here we have the C plane, M plane, R plane, and N plane. So after we simplify the item structure, so we can see clearly it follows the layer by layer remove of the items of the surface. And then for any general crystal plane that can be considered as rotated as the inclination angle of theta from the basic crystal plane. So from this, so we can simplify the cluster of items as small blocks to illustrate our idea. So here is the general crystal plane. So we have the step size, which is in the green color, and the age the age type, and means it has the slower age rate but higher age rate than the terraces. And here is T means the terraces that we colored by the red color. And when we resume this block to the item structure, so here is the basic crystallographic planes, and here is the general crystallographic planes. So the size of the H1 and H2, so that means if this is general any crystal plane P1 has a higher H rate, that means it has more edges. More edges means it has a higher H rate. Usually the terraces has the slowest H rate. So after this, for a general crystal plane of the sapphire, so we can get this figure. This figure is, so after the delta of T, and then the crystal plane will go down at the delta of H. So for the any crystal plane P, so we have the I is from 0 to 1. 0 means the fundamental primary plane, and 1 means a general plane. That means those planes are rotated from an angle towards the primary plane. And M from 0 to 2 means the size, means the length of the edge, and N means the length of the terraces. So the delta H for any plane so can be expressed as a function of L. The L means the two L1 and L2 and the theta of P. So L1 and L2 are the geometry length parameter of the atomic structure of the crystal. So we will try to explain the anisotropy of H rate according to the geometry structure of the atomic structure. So the theta of P is the angle between the crystal plane P and the basic crystal plane. And then for any orientations, any planes, we measure the H rate from our experiment. We got H rate RP, and then we can have two types of equations. The first one, when I is 0, means they are all the basic for those basic planes, and the other is the the general planes means it contribute by the function of L, and then the contribute of the RS means the steps, the remove rate of a cluster of items on the step position, and the remove rate of a cluster of items on the edge, and the remove rate of those items on the terraces. So we will give an example of how we calculate every cluster of the items for modeling this H rate. So here we will consider the -1, 1, 0, 0 crystal plane. That means we will examine all these planes along this way. So we have the six primary planes, and then we have 10 different edges and the other clusters. So we will set up a matrix along the following these equations. So we have 10 inner variables. We have six basic H rate. So when we select any 4 other orientations, so we can solve this equation. So we will get every cluster of items, the remove rate. So after this, so we calculate all these orientations, the red points, every 2 degrees, every 2 or 5 degrees. So we test it, we calculate, we do the comparison of the calculation model of the experiment H rate for these 3 concentrations, so we can see the result. The result shows the model explained the anisotropy of H rate according to the atomic structure software accurately. So the proof of our proposed method. And then, so after this, we can use this idea to set up the simulation method. So usually there are several atomic simulation methods, such as the Monte Carlo and the Accelerometer, and some of the other simulation model. The geometry is known as the level set, which has developed in our group, and the Monte Carlo method has the advantage to simulate the complex fabrication process directly using the atomic crystal structure, remove the surface item by item. So it also shows the better ability in our previous study to modeling the morphology during the fabrication process of maps, generally based on the classification of the surface item types, which we have done in our previous slides. And for this, so here is the level set method. So level set method is considered as a type of the geometry method with good performance for tracking the interface of the edge front of the software. So in this figure shows the framework. So our way to propose the simulation system, and it has 2 important parts. So one part is the database. It's just from our experiment. It includes the anisotropy property of the substrate at different temperature and the different concentrations for different agents. So all these factors contribute to the H rate of the interface tracking space. And the other part is the level set equation. As this, we have, this is the this is the overall level set function. It has the external vector field and the normal direction velocity field. So we don't have the external vector field in our study. We only have the normal direction velocity field, which is evident from our experiment. And then here is the aging process is represented by solving this partial differential function. And here is the schema we use. And this is the LF schema is fulfilled using the our proposed model. It shows good calculation performance in practice. So here is the result. So here is the result from the experiment we did for the convex and concave structure, and used directly from our hemisphere data. And here we do Here is the experiment from other groups. So we use as a benchmark to test our simulation model with the orientation and with the inclination angle returned from the 1-100 direction, and we can see the different structures, and this is our calculation result, which follow the experiment very well. And here is the application of the Monte Carlo simulation. So we propose the 6 indexes classification method just according to the step flow model we proposed, which can classify type of the surface items of software in detail. So mainly according to the bonds of the surface, the first neighbor and the second neighbor, as we study in the quartz and the silicon. So here we give the remove probability function for the surface items. So we design the new type of the removability function to calculate in our Monte Carlo simulation. So we define the beta is the Boltzmann constant and T the temperature, absolute temperature, and epsilon 1 and from epsilon 1 to epsilon 6 represents the average energy to break the bonds between the target items to fulfill our simulation. So here is the result of the Monte Carlo simulations. So here we can see it almost similar as the experiment result. It has some deviations from the experiment, not so good as the result of the level set method, because the level set method is a pure geometry method. So here the Monte Carlo is remove item by items, and this is the simulation result for the convex and concave structure etched by the circular mask pattern. So in conclusion, in this study, so we set up the H-rate model based on the step flow mechanism, and we talk about the prediction of the geometry and the general expression of H-rate of the crystal plane by our function, and we set up the atomistic structure of the crystal plane of sapphire and to the experiment date by the classifying the type of the crystal unit. And then we talk about the level set and color application for simulation of this etching process. So this model can provide a reference to analyzing the anisotropy of H-rate of the crystal very complicated atomistic structures such as the silicon carbide and the gallium nitride. So that's all. Thanks. Thank you very much.
Thank you for the wonderful presentation. So it is actually great to see that the kind of accuracy, high accuracy between the modeled H results and the experimental results. So if you have any questions in the audience, can you just ask Professor Ying directly? Okay, so there is no question. So I just have one small question. So what was the criteria for choosing that temperature of 236 degrees centigrade? So is it from the experiment that you determine that this temperature is optimum for your etching and then you choose that temperature in your modeling, or was there any other criteria?
So, okay, thanks. And the sapphire crystal is quite different from the quartz and the silicon. For the quartz and the silicon, so we etch this material is about room temperature less than the 80 degree, and for the sapphire crystal, that's very difficult to etch. So the etch rate in the room temperature means nothing. So for the industry to create this bottom sapphire substrate for the LED devices, it almost reached to about 250. So so you can see that temperature dependent of this material. When we lower down the temperature down to less than 200 degrees, that H rate will decrease very, very fast. So we will see nothing happen. So the H temperature should be, I think, should be near 250 at least. So that's why we choose higher temperature.
Okay. Any question from the audience? If not, then maybe we can thank the speaker. Thank you, Professor Ying, for your wonderful talk.
Thank you, Professor.
Thank you.
Okay.
So the next presentation is a contributed talk, which is by Nadeem Tariq Beg from IIT Delhi, and he will be presenting his work on highly efficient parametrically forced MEMS mechanical energy harvester for wideband application. So Nadeem, maybe you can start presenting.
Good afternoon, everyone. I hope my screen is visible and my voice is audible.
Your screen is visible, but your voice is not very clear. Maybe speak a bit loudly.
Okay, good afternoon, everyone. I'm Nadeem Tariq Beg from Integrated Microsystems Lab at IIT Delhi, and I'll be presenting my work on highly efficient, low threshold, parametrically forced MEMS vibrational energy harvesters. To start with, this is the general overview of my presentation. I'll be starting with the basic motivation behind this work and what led us to take up vibration energy harvesters as a solution to the problems we face. I'll be giving a brief introduction to parametric resonance in MEMS and then start with my proposed design and follow-up discussions. The motivation behind this work is Internet of Things. Internet of Things is a network of connected objects via numerous sensors, exchanging data and executing tasks. IoT connects everything around us and has huge computational possibilities and opportunities. IoT is predicted to go into the largest tech industry ever. We already have a huge IoT market that has expands to $12 billion industry. IoT, the number of devices connected by IoT are increasing every year. Currently, it is predicted to go beyond 50 billion connected devices by 2025. This number is surely going to increase in the coming years due to further miniaturization of low power electronics. We are going to start our discussion with a simple IoT node. A simple IoT node can be represented with this figure. It comprises of various electronics such as the main sensor module, the MCU, the transceiver module, and the most importantly, the powering system, the powering source. The technological growth of IoT seems to be constrained only by the powering source requirements. A 50 billion connected devices will require an equal number of powering sources. And the battery technology is not the best solution to this problem. So batteries are not suitable for this application because of different problems associated with them. Some of them being maintenance, lifetime issues, environmental hazards. So the only logical solution to this problem in the energy harvesting technologies. There are already a number of energy harvesting technologies present, like solar, thermal, RF, and vibration, but all of them have some limitations with respect to IoT powering. For example, let's consider the average power required by an IoT node from Texas Instruments. It is clear that the operational cycle of an IoT node uh, is divided into two parts. First, it is the sleep time, which is the most dominant, and second is the active part, which is the least dominant part. The requirement of IoT power is necessary only in case of active mode, when it is to either receive or either it has to transmit data or sense the data. It has been calculated that the average power required for a simple IoT node is around 50 microwatts for its operation per cycle. If we look at this figure, we get a prediction of different types of energy sources and their energy densities as well as the average power. We see that the mechanical sources producing vibrational energies uh, is within the limit of our power requirement, as well as it has a good energy density. The other high energy sources, high energy density sources such as outdoor sun or RF are not always suited for IoT applications, because we know that IoT nodes are not always used in open, but are always used as a standalone nodes. The thermal energy is not always possible. So for this work, we have chosen mechanical sources producing vibrational energy as our energy sources. A general vibration energy harvesting system can be represented by a spring mass damper system, which receives energy by excitations from ambient vibrations and converts it into usable electrical energy by conditioning it and leveling it to the level of low power electronics. But the main issue with vibration energy harvesters is the power density and bandwidth. Normal, conventional, linear vibration energy harvester design is not sufficient for this application. So it is necessary to shift from linear energy harvesting design strategies to the non-linear design strategies. We can see that by increasing the non-linearity, the overall power density increases and the output power gain is around 4 by pi for simple non-linear design, which can further be optimized by using different optimized non-linear strategies. For comparison, we have several different strategies for vibrational energy harvesting. We see that not only a single strategy can be used for vibration energy harvesting, because only one strategy is not always sufficient. But for the sake of high power and high bandwidth, we will be focusing our attention towards autoparametric vibration energy harvesting, because it is suitable for amplitude broadband excitation and is based on parametric resonance effect. The other nonlinear strategies are also useful, but for a larger power density, autoparametric vibration energy harvesting is the best suited application. So the parametric resonance is the backbone of autoparametric vibration energy harvesters. It is a non-linear design strategy to overcome the narrow bandwidth issues of linear energy harvesters and comparatively low output power of other nonlinear strategies. The parametric resonance effect is based on periodic modulation of system parameters such as spring stiffness, damping, or effective mass. And these systems are defined by a Matthew damped equation, wherein the stiffness is a time-dependent term, which has a parametric modulation term at a frequency omega, which is equivalent to 2 times omega naught by n, where n is the order of parametric resonance. Such a system of equation has a non-trivial solution only when the parametric amplitude is greater than a damping dependent threshold acceleration amplitude. That is, this system is only effective when the acceleration amplitude is greater than some given threshold acceleration amplitude, which is based on the damping of the system. This figure makes it clear how the threshold amplitude varies with the system damping. When the system damping is zero, the parametric oscillation can start at a very small acceleration amplitude. But as the system damping increases, the threshold amplitude requirement also increases. Parametric systems are unstable systems which require some initial excitation to start the system oscillation. Previously, there has not been much work done in parametric systems in the specific field of MEMS energy harvesters, but recently YGI et al. Isha et al. Have demonstrated dominance of parametrically excited systems over directly excited systems at same acceleration levels. They have taken output power and bandwidth into consideration for energy harvesting purposes. The design used by them is cantilever beam excited parallel to the beam length to induce periodic stiffness modulation to decrease the damping dependent spring in the design to bring the much needed threshold amplitude down to 0.8 meter per second square. The cantilever beam is excited parallel to the length and the response is perpendicular to the length. So the proposed work requires design of an autoparametric vibrational energy harvester, which has an integer ratio of 2:1 with piezoelectric transduction. An autoparametric system is characterized by this integer ratio. So this integer ratio is very important. Second, we are using initial springs like before. The initial springs are double clamp beams, reduce the viscous damping and thus reduce the threshold initiation amplitude for low acceleration energy harvesting application. We are expecting a higher power density, better reliability, and larger bandwidth with this proposed design. So we have designed, this is the given design that we have used. We have simulated all the results, all the designs in COMSOL multiphysics using piezoelectric multiphysics. The initial spring is a double clamp beam with midpoint cutouts, vertical autoparametric cantilever, which are excited directly to the initial spring, and it becomes parametric excitation for the vertical cantilever. The dimensions and other specifications for the design are given in the table. To start with, we have analyzed the eigenfrequency of the system so that sure that the system is actually autoparametric. For that, we performed eigenfrequency analysis and we verified that the two mode shapes, the initial spring mode shape and the vertical cantilever mode shape, have a 1:2 frequency relationship. This strict frequency relationship was done with strict parameter tuning to match the frequencies. The same can be verified.
Nadeem, you need to wrap up in maybe next 2-3 minutes.
Yes, the frequencies can be analytically calculated using the given formulas. After that, we did a frequency setting up to 400 hertz with 1 millinewton per Pascal force, and we saw that we obtain a parametric amplification gain using COMSOL simulations. But the frequency response was not nonlinear as expected because COMSOL does not have the parametric resonance physics in it. Later, we modeled numerical equations of the system by making a coupled differential equations which have parametric coupling terms, and these are the given specifications we use for the simulations. We followed earlier papers on these mathematical modeling, and we performed several time-dependent modeling of the system, in which we saw how the energy buildup is taking place between the two modes and how an initially zero response system or the initially zero response vertical cantilever is slowly and steadily gaining energy, and that energy is in the mode 2, which it is acquiring from the initial spring that is decreasing in amplitude. We saw that after the things settle down, we have a 12-fold amplitude gain. This is because of parametric amplification effect present in the autoparametric system. Initial delay that is resulted is due to the energy buildup to transition from mode 1 to mode 2, and the duration of this delay is based upon both excitation amplitude as well as the system damping. Later, we performed an acceleration sweep on the two systems, and we saw that the parametric system dominates after a given acceleration amplitude as expected. By doing the modification in the spring, we were able to reduce that threshold amplitude to 0.6 meter per second, which is lower than the earlier works, and we saw that the dominance of parametric division keeps on increasing after we increase the acceleration amplitude. We also did a piezoelectric simulation on the system, and we saw the amplification gain of around 250 microwatts using autoparametric systems. Later, we also did a placement analysis of the vertical cantilever on the initial spring, and we saw that it is dependent on the beam shape that we want to use. For example, for mode shape 1, the maximum transduction efficiency is obtained at the midpoint, while for the other mode shapes, it is at the quarter length. So the mode shape decides the frequency, decides the efficiency of the transduction. By concluding our work, we have presented a 1:2 autoparametric VEH design for low frequency, low amplitude broadband energy harvesting with reduced initial threshold amplitude. The parametric amplification effect is exploited for response amplitude growth over a directly driven oscillator. It is seen that the amplification is around 12 times that of a directly driven initial for the same excitation value. Further geometric modification of initial spring decreases the threshold amplitude than the same reported by the previous work. Further, we can include stability into the initial spring to allow for interval oscillations to build up the energy in the parametric oscillators. Detailed analysis of stress will be useful for optimizing the placement of piezoelectric transducers for further improvement. Thank you. Any question?
Thank you for the presentation. So, if there is no, is there any question? Maybe one small question, if anyone has. Or if not, maybe we can thanks the speaker. Thank you, Nadeem. And we are kindly running into the poster session time. So I would like to thank everyone for joining this afternoon session on this MEMS symposium. And we now can conclude this session, and maybe we will join for the next session from 5.
Okay, thank you, sir.
Thank you.
Hello. We can start the presentation quickly. So, hello, Shumit. Hello, can you hear me?
Yes, sir. We are starting now.
Start. So, give it like 2 minutes maximum for each presenter and summarize their main finding. So, you don't have to go do any introduction or anything. What is your work and what is your finding? You can
Okay,
highlight
sir.
that.
Okay, sir.
Hello, Akshay, can you start?
Yes, sir.
Start the presentation. You can ask one by one. Start.
Okay.
Is there any problem?
No, sir. I'm looking for candidates actually.
So all the candidates are there. You don't have to looking
Sir,
for
we
any.
are starting from post number 72.
You
Neelu
just ask
Sharma.
that. Ask that who?
Neelu Sharma.
Neelu Sharma is here or not? Then you skip it. Go to the next presentation. Neelu Sharma, are you here? Then go to the next presentation.
Yeah. Then poster number 73. Somarjit Singh.
Somarjit Singh, are you there? You announce the poster number, then if he is not there, then
Yeah.
you leave it.
Poster.
Hello, can you hear? I'm here.
Yes, who?
I'm Ningthojan Somorjit Singh, poster number 73.
73. Can you open the poster 73? So you can
Yes, sir.
summarize within 2 minutes. What is your main finding?
Yes, sir. So actually, today's presentation, my topic is large area graphene oxide. We have synthesized graphene oxide and
Just
reduced
wait. So can you share the poster?
poster. So
Okay,
this
that's right.
one, actually, I'm talking from mobile, sir. Yeah,
Okay,
that is.
large area graphene oxide for reduced graphene oxide sheet for high efficiency SARS application. Is
Search
it
application. Yes, sir.
Yes, go.
So in this presentation, I'm demonstrate how to synthesize the graphene oxide as well as reduce graphene oxide with simplest method. In our method, we want to control the size of the graphene oxide. So in we achieve up to the 102 micro generator size of the graphene oxide sheets, which are demonstrate optical image are we shown in surface analysis. And using our graphene oxide sheets, we are using for such application for rhodamine B molecules. So we have measured different concentration of the rhodamine B starting from 10 to the power minus 4 to 10 to the power minus 8. In this, so for the beginning means 10 to the power minus 4, 5, 6. For higher concentration, graphene oxide has enhanced more intensity of the Raman as compared to the reduced graphene oxide. But for higher concentration, 10 to the power minus 7 and 8, reduced graphene oxide is more enhanced compared to the GO. This is our finding. And then here we are demonstrate the comparison graph for intensity versus concentration. And also we have shown the Raman spectrum for rhodamine B for its Raman intensity, which represent the bonds for the means abbreviation for the rhoda B molecules. So here CC bond and CO bonds which I represent. And for structure analysis, here we have demonstrated our material is graphene oxide as well as reduced graphene oxide is proved using XRD. And also it is one of the analysis, structure analysis. And then here also we are fitted our reduced graphene oxide as well as graphene oxide using multiple peaks. So here defect related and all defect enhanced Raman peaks are reduced as when it comparison with the graphene oxide. So all our poster I can summarize is we are finding the comparison here I shown here is only the GO as well as RGO, but as compared to the others, our it is not shown here, but it is still a better from compared to as we are study from the literature review. Yes, sir. So these are my conclusions.
Number?
Hello,
Samarjit, what was your question number?
73, sir.
Okay.
Yeah.
Next. Next presentation.
Hardeep Singh.
Next presentation is poster number 74. Hardeep Singh.
74.
72, are you there?
Poster number 72 is Neelu Sharma. Sir, she is not there.
Neelu Sharma, are you there? Then go to the next.
Yeah, poster number 74, Hardeep Singh.
Hardeep Singh, are you there?
74, sir, Sajal Shraddha.
Okay, Hardeep Singh and Shadal.
Yeah.
Okay.
So go ahead. Can you open that?
Oh.
Okay, go ahead.
So, sir,
Yeah.
Sajal Shraddha.
Yes. This is Hardeep Singh and Sajal Shraddha.
Okay, yes, sir, yes, sir, yes.
Go ahead, we can see.
Okay. Can you see my poster?
Yes, go ahead.
Okay. So good afternoon, everyone. I'm presenting this poster on the topic of a study of piezoelectric response of MOS to PVDF nanocomposites prepared with polyaniline interlinker. So PVDF is known for its piezoelectric properties due to the orientation of CF dipoles. So it has 4 phases: alpha, beta, gamma, and delta, and beta being the polar phase. So different strategies have been established to develop the polar beta phase of PVDF. So in this study, we enhance the piezoelectric property of a polymer by combining few layers of MOS2 nanosheets with PVDF using PANI as an interlinker. So we have also compared these the piezoelectric properties of MOS to PVDF with the MOS to PVDF PANI nanocomposites. So from first of all, we prepared the MOS to nanosheets by liquid exfoliation method, and we prepared the MOS to PVDF nanocomposites by dissolving MOS to nanosheets with different concentrations PVDF solution. And to prepare the MOS to PANI PVDF nanocomposites, we made MOS to nanosheets with HCl to aniline, also added ammonium persulfate, and then added MOS to PANI at different concentrations in PVDF. So from the XRD graph, we can see that as we increase the concentration of MOS to PANI in PVDF, the intensity peaked at 20. Intensity peak corresponding to beta phase, it at 20.7 degree is highest, and it decreases if we increase the concentration further. And similarly, from the UV visible absorption spectra, we can see that in the exfoliated MOS2 nanosheets, we can see that the peaks are at 628 nanometers and 672 nanometers, which correspond to the characteristics peaks of MOS2 nanosheets. And from the EDS mapping, we can see that MOS2 PANI particles in PVDF have homogeneous dispersion, and indicating that they are interfacial interconnected, and hence indicating that pani is plays a very crucial role as a compatibilizer. And and we used a quasi-static method to find the piezoelectric coefficient of D33. And as we can see from here also, at pure PVDF, the D33 was around 7 picocoulomb per Newton, and it increased at 3 weight% and decreased if we increase it further. So, and on comparing the D33 value without pani and with pani composite, the increase was 1.65 times or 1.52 times at 1 and 3 weight%. So in conclusion, we can say that pani with pani in in PVDF increases the D33 value, and hence increasing the beta phase, and it can be crucial in increasing the piezoelectric coefficient. So thank you.
Okay, go next.
Sir, am I audible? Sir, am I audible?
Yes.
Question number 75, Samim Reza.
Shall I share or you will share from that side?
You can share.
Go ahead.
Okay, good afternoon to all. I shall be presenting on growth of large edge length high quality tungsten disulfide. Tungsten disulfide is a two-dimensional material. It belongs to the family of transition dichalcogens. It has a formula of Mx2. So N can be a chalcogen atom and X can be a chalcogen atom. So in tungsten disulfide, the tungsten is sandwiched in between two sulfur atoms. Unlike graphene, we know that graphene has zero band gap, but tungsten disulfide has a band gap, and the band gap here is tunable. That means if we decrease the number of layers to single, the band gap changes from a bulk 1.3 electron volt to a monolayer of 2.1 electron volt. And also, it is chemically and thermally stable, and it can also be weighed. So this material can be used in flexible and wearable electronics. A chemical vapor deposition was used for the synthesis of tungsten disulfide. So a fusion approach, that means the precursor sulfur, tungsten trioxide, and the substrate were placed on different zones. Here is a typical temperature profile for the ash-grown tungsten disulfide. The ash-grown tungsten disulfide were characterized by using FECM, PL, Raman spectra, and optical microscopy. Here, the first one shows the triangular WH2 plate. This is a nice triangular plate with clean edges and sharp corners. So this is a monolayer triangular plate. We also observe multi-layer tungsten disulfide. And here, the number of layers is more than one. And here also, the edges are clean and the corners are sharp. We also observe dendritic tungsten disulfide. This kind of structure occurs when the temperature of the substrate is lower and the precursor concentration, that is sulfur and tungsten trioxide precursor concentration, are higher at that portion. We also observe here the nanopolar tungsten disulfide. These kind of structures occur when the precursor concentration and the temperature both are higher. The number of layers of the ash-grown tungsten disulfide was characterized by using Raman spectroscopy. For Raman, for monolayer, the Raman peaks are at 351 and 420 centimeter inverse. So if the number of layers increases, the peak shifts to right. For the multi-layer, the peak position at 354 and 422 centimeter inverse. The band gap was calculated by using PL spectra. So here the blue one show a PL spectra for a monolayer. Here the PL peak is around 640 nanometer, which is corresponds to 1.96 electron volt, which is the reported value for the monolayer tungsten disulfide. And the red ones for the multi-layer. So as we also know that for the monolayer, the PL intensity is much higher than the multi-layer. And we observe a 55 times stronger monolayer PL peak for tungsten disulfide. And so in conclusion, we use a atmospheric pressure chemical vapor deposition for the synthesis of tungsten disulfide, and it was in argon environment. And besides monolayer, we also observe multi-layer spiral tungsten and tungsten disulfide, dendritic tungsten disulfide, and nanopolar tungsten disulfide. So this material can be used in wearable and flexible electronics, and also as it has higher PL peak at monolayer. This material can also be used in optoelectronic material. Thank you, sir. Yes, sir.
Okay. Then next.
Next, C. Avinash.
Yeah.
Avinash, are you here?
Yeah, sir. You are audible to my voice.
Yes.
Shall I share or you will share and I will present?
You can share, no issue.
Okay. Just a minute. Can you view my poster now?
Yeah, it's visible. You can start now.
Okay.
Yeah, it's
Good
visible.
afternoon
You
to
can start now.
Okay, good afternoon to all. I'm Avinash. I'm going to present the large area single layer MOS2 flexible green photo detector. And last means my previous presenter already told everything about how we prepare the MOS2 as well as WS2. Now I'll go for the detail of how a photo detector fabrication can be done over that. And most important thing in our thing is that will be green photo detector, because that substrate, if it will be biodegradable, that can be used in many consumer and disposable electronics. For that, actually important of our things actually. So some quick introduction I'm giving, that is trigonal prismatic, and it has direct band gap of material, and electron hole pair can generate in photo excitation itself. And exciton is room temperature stable, and but biodegradability of the substrate make it a bonus for use in the disposable electronics. The important thing is that the CVD grown monolayer MOS2 is a very high optical quality, but to grow over the flexible substrate, means the polymeric substrate, it is impossible. So we tried, out of many transfer method, we tried a surface energy assisted method, because it doesn't involve any much chemical contaminant. And we first time we integrated, you may be knowing that more than 1,000 number of photo detector is available in mono as well as multi-layer of MOS2, whereas some countable number of biodegradable photo detector exists in multi-layer, whereas we first time integrating the monolayer MOS2 for the biodegradable photo detector application. So by the importance of choosing the cellulose acetate, it is cellulose acetate substrate for a flexible and a biodegradable photodetector, or indirectly green photodetector, is because of cellulose acetate is a high transparent, flexible and low cost substrate, and it is insulating, it is electrically insulating, which can give the more 2D device help, as well as it is eco-friendly and earth abundant, and it is biodegradable. It is confirmed by Sturm's test, and it can substitute the toxic substrates like gallium arsenide in consumer and disposable electronics. For synthesizing the MOS2, as my last presenter told, we use actually the same CVD zone technique of 3 zone, so that high optical monolayer MOS2 we grown in large area greater than 500 micron area, so that large scale transistor we can also prepare out of it. But we have grown the MOS2 as conventional over SiO2 substrate, and after that, for preparing a flexible photodetector, we have to transfer it over a flexible substrate. So before that, we carried the Raman PL and AFM characterization, and we confirmed that this is a monolayer MOS2 of high optical quality. After that, we transfer it over a flexible substrate by using a surface energy assisted technique, and we find, and the image you can see actually in right side, that flexible, it was over a flexible substrate of cellulose acetate, and we compare its optical quality, optical characterization we carried out by Raman as well as PL. We find that there is a little blue shift around 0.6 centimeter inverse due to compressive strain, because before transfer, the monolayer MOS2 was over SiO2, whereas now it is over cellulose acetate, means flexible substrate, so compressive strain was developed. And in PL also, we find that 60 MeV of PL, 60 MeV of blue shift is happened. It is only due to compressive strain in the film. But it is clearly seen that there is no chemical contamination happened in the transfer process. After transferring the monolayer MOS2 over a flexible substrate, we went to prepare a photodetector fabrication. For that, application for that. And for large area over there, we quoted the AG electrode, which ACM image I have shown in left side, and by varying the different wavelength of light sources of different wavelength, one is more than band gap, that is more than 633 nanometer energy, that is 460 nanometer, whereas red LED of 642, it is close to band gap, and white light I have used to see how the photocurrent is varying. And in left side figure, IV data, you can see that curve is a linear and symmetric, which shows that AG is formed the ohmic contact with the monolayer MOS2. And comparing the photoresponse of before transfer and after transfer. Before transfer means over SiO2 on which the monolayer was grown by CVD method, and after transfer means it was transferred over a flexible and a biodegradable substrate, that is cellulose acetate, means CA substrate. You can clearly see that photocurrent means a dark current in this
So
before
can you
transfer.
finish quickly?
Yes, sir. Yes, sir. Just a minute, sir. You can see
Not
that.
minute, half a minute.
Okay, half a minute. So okay, so that dark current is more in before transfer. It is because of multiple reflection is happened in from S, because light due to photoresponse measurement, light was passing through SiO2.
Hello. Sumit, can you go to the next poster? It is not.
Okay, sir.
And you share the screen. Okay.
Okay, sir.
Quickly.
Poster 77. Poster 77, Anand Kumar Singh.
Yes, sir. I'm here, sir.
So Anand,
Okay, you can
finish
start
with,
now.
Is it visible?
Yes.
Good afternoon, everyone. My topic of the presentation is the molecular doping of TI nanoparticle coated chemical vapor deposition grown graphene by the nitric acid. So graphene is a two-dimensional network of the sp2 hybridized carbon atom arranged in a hexagonal structure. It received a great interest due to its unique electrical, mechanical, and optical properties, which includes high carrier mobility, high mechanical flexibility, optical transparency is about 98% in the visible light region, and the high thermal conductivity. Band structures. So typical band structure of the graphene is the band gap of the graphene is 0. Due to 0 band gap, it is required for the graphene used in the electronic devices. Doped with it required the doping, and the doping by the two methods, that is electrical field doping or the chemical field doping. And after that doping, graphene is also used in the many applications like thin film transistor, ultra fast and flexible electronics, optoelectronic devices, sensor and capacitor. So for the grown of the graphene, I have used inductive coupled plasma enhanced chemical vapor deposition method, and I have used 25 micrometer thick polycrystalline copper as a substrate, metal substrate. So for the transfer of the grown graphene on the silicon dioxide substrate, we have used wet transfer technique using PMMA supported layer. So this is the experimental setup of the Icee PEVD methods. So for the electrical measurement of the device, I have grown the metal layer of the gold with the thickness of 30 nanometer with the help of thermal evaporation method. So for the doping of graphene, I have used 3 type of concentration of the TI nanoparticle, that is 0.1, 0.5 mg per ml, and 1.0 mg ml. After that, I have used 8 molar concentration of the HNO3 doping on the single layer of graphene to for the electrical and the optical characteristic of the graphene. So in the result sections, we have clearly seen that the black graph is shown the pristine graphene, and the graphene have a typical G and which is very sensitive for the doping, and for the higher concentration that is 1.0 TiO2 doped HNO3, the maximum shift of the G and 2D peak is 5 centimeter and the 6 centimeters. And according to the doping of the graphene, so intensity of the peak is 2D peak and G peak intensity is decreasing by increasing the TiO2 concentration, and Ig ratio is increasing to increase the TiO2 concentration. The morphology of the device is changes after the HNO3 doping. We can clearly see the pristine graphene having the roughness of the near about 1.41 nanometer, and if you increase the higher concentration of TiO2, the morphology is changes, and the maximum roughness for the 1 mg TiO2 doped graphene. So we also measure the electrical measurement of the device. The pristine graphene having the direct point, that is minimum conductance point, is at the 4 volt, and if you can see that the maximum direct point shifting above the 89 volt for the 1 mg TiO2. We can also measure the carrier density. We can clearly, since then the pristine graphene having the change in the carrier density is 0, and after increasing the TiO2 concentration, the carrier density is increases. Fermi shift is increases as the TiO2 concentration is increases. So in the conclusion of our research is that we have the shifting of G and 2D peak towards the higher wave number imposes a p-type doping of single layer graphene, and also the direct point shifted towards the higher voltage after HNO3 modification imposes strong p-type doping. The change in carrier density and the Fermi layer position is also changed after the HNO3 doping on the single layer graphene. And the device which I made is used in the optoelectronics and future electronic devices. Thank you so much.
Okay, next. And whenever somebody is presenting, you don't have to introduce the introduction, because you already heard about the 2D materials. You go, what is your contribution, and try to finish.
Question number 78.
Okay.
Am I audible?
Yes, go ahead.
Good afternoon, all.
Yes.
I am Subhasmita. Today, my topic of my poster is electronic and magnetic phase designing in monolayer CGS. As we know, now a time lot of 2D materials are available, but stability is still the issue in this material, and also most of the 2D materials are non-magnetic in nature. So there are different techniques available to introduce magnetism in this material, like doping, surface functionalization, creating vacancy. But these methods are very difficult to handle experimentally. So in this our case, we have used strain and electric field engineering, because these methods are non-destructive in nature. It means it does not create any permanent changes in the material. So by using these techniques, we are trying to modulate electronic and magnetic fields in CGS. CGS actually belongs to the same family as a well-known 2D experimentally available 2D material CGT, and it has also same crystal structure. And with the application of strain, it shows a phase transition from a semiconducting to half metallic state. So half metallicity is very important for spin-bar design. And also there is a greater enhancement in magnetic property as well, because with the application in normal CGS, the TC is 149 Kelvin, but with the application of strain, the TC attains a value of 885 Kelvin. So it is obviously very far out, very great room temperature. Means CGS can be a room temperature ferromagnetic material, and also there is a further enhancement of TC up to 900 Kelvin with the application of electric field. And so overall, and this enhancement of this TC is due to the superexchange interaction between two chromium atoms mediated to selenium atom. So this extent of overlapping ultimately affect the affect the TC value. So in conclusion, CGS is intrinsic ferromagnet, and also this ferromagnetic characteristic is possessed with application of a large percentage of strain, and also it can be a half metallic magnet, which can help to design any practical spin valve. So it will be a very great material for spintonic applications, and also the stability is very high as compared to CGT. So thank you.
So good afternoon, everyone. Yeah, so I'll just start. So my name is Icee. So the topic is on tuning and control of the magnetic properties of a 2D magnet. So here, as we know, as previous, hello?
Yes, go ahead.
Yeah. So like the previous candidate had discussed on the properties of like immense uses of 2D materials. Here we are using another category called 2D magnets, which are shown immense like uses in spintronic applications. So here we are using chromium oxychloride as our 2D magnet, and we have investigated the spin-dependent electronic transport as well as magnetic properties of this material using DFT calculations. And also through this we were able to observe spin resolved conductance of around 100% spin filtering, and also we were able to tune the switching efficiency of the material. And another category was the tuning of the critical temperature, the Curie temperature of the material through the application of a compressive strain. So we could shift the so initially the system behaved the TC was the critical temperature was around 148. So we were to shift the Curie temperature of the material using a compressive strain. So as you can see, a graph is depicted on the 2D plot is depicted on the switching spin injection efficiency of the material on the application of strain. And moving on, as you can see in the magnetic properties, initially the system behaved had a critical temperature of around 148 Kelvin, and when we applied a compressive strain of value of around 8%, the TC get enhanced, or the Curie temperature get enhanced to around 298 Kelvin, which is around room temperature. And also applying strain in other three directions, in the X, Y, and biaxial direction, we were able to tune the critical temperature of the material. So in conclusion, we can say that initially the pristine CrOCl behaved as a material with having a low critical temperature. However, using the application of strain, we were able to increase the spin injection efficiency and also the critical temperature of the material. Thank you.
Okay, next. Next, Pooja Kumari. Are you there?
Hello?
Pooja Kumari, can you hear me? Yes, we can hear you. Go ahead.
Good afternoon, everyone. My poster title is High Magnetoresistance and Perfect Spin Filtering Effect in Magnetic Fostering. In this poster, we have studied the single layer fostering docked with series of 3D block elements in increasing order of atomic number and create different electronic and magnetic phases in fostering. We have also studied the transport property of fostering plus dopant atom and designed the spin valve structure. In this work, we have used first principle based density functional theory, and for transport calculation, we have used non-equilibrium Green function plus DFT methodology. We designed a fostering system by replacing the phosphorus atom to 3D block element into increasing order of atomic number. I have dropped 2.77%, 5.55%, 11.1%, 16.67%, and 22.22% of 3D block element in fostering layer. Checking the dynamic stability of our doped fostering system, we calculated the phonon band structure. We have not found any imaginary line in phonon band structure. This shows our system is stable. After that, we studied the electronic behavior through band structure of our 3D block element doped fostering. We found different electronic and magnetic stages in doped fostering system, and we have divided into its 5 categories: non-magnetic semiconductor, bipolar magnetic semiconductor, half metal, magnetic metal, and non-magnetic metal. Vanadium, copper, and zinc
doped phosphine are independent of doping concentration. Vanadium doped phosphorine so half metal behavior, and copper and zinc doped system so non-magnetic metal. We have also calculated the spin polarization and found approx 100% spin polarization in titanium, vanadium, chromium cases. For magnetic property, we calculate the magnetic moment as a function of atomic number for 5.55% doping and 16.67% doping. We have found higher magnetic moment for Mn case, and also found the induced magnetic moment has increased with increasing doping concentration. We have also studied the transport property using two-probe design of phosphine plus dopant atom, and calculate the spin injection for 2.77% doping and 16.67% doping. We have found higher spin injection value for titanium, vanadium, and chromium and iron cases for 16.67% doping. We have also designed the spin valve structure by using single phosphine block with two sides doped with heavily 3D block elements, which could solve the conductivity mismatch issues in spintronic devices, and calculate the magneto-resistance ratio at 0.2 volt and 0.8 volt. I have found high magneto-resistance in vanadium and chromium cases. Conclusion: we have made the various doping configuration in phosphate by replacing phosphorus atoms with respective dopant atoms. For stability purpose, we calculate the phonon band structure and study the electronic and magnetic behavior of the doped system. The induced magnetic moment and spin injection efficiency is going to increase with doping concentration. We have also designed the spin valve structure and calculate the magneto-resistance ratio, and found high magneto-resistance ratio for vanadium and chromium doped system. Thank you.
Okay, go ahead. Next. Next, please. Yes.
Okay, thank you. I am Shantanu Majumdar from IIT Patna.
So just
today
a second.
Hello?
Can you maximize it? So yes, now it is okay. Go ahead. Go ahead.
Okay, sir. Hi, I am Shantanu Majumdar from IIT Patna. Today I am going to talk about this device structure based on 2D material. Where I'm going to talk about is the spin orbital MRAM. So the basic structure for the MRAM device is based on the basic structure of the spintronic device is based on the MRAM. The new addition to the MRAM family is the SOT-based MRAM device, that is spin orbital MRAM. Now, most of the material used for the generation of the spin orbitor is heavy metal like tantalum, platinum, and tungsten. But they have created a lot of issue for generating a sizable SOT, like low efficiency of the damping like SOT, and the absence of perpendicular magnetic anisotropy, in which actually lowers the out of plane SOT component. Now, in this case, 2D material can be used. In 2D materials, we have seen various interesting properties that are not present in the bulk material, like perpendicular magnetic anisotropy and perpendicular magnetic component also. So here we have taken two material in our structure. One is the Mn-T4, which is a newly discovered magnetic topological insulator, and another one is CGT, that is Cr2Ge286, which is a intrinsic ferromagnet at lower temperature. So we have created a device comprising of these two materials, where the SOT will be created by the Mn-T4 layer. So in the figure 1, the band structure of the device is given, and the figure 1b, the band structure for the monolayer MPT and bilayer is given. And as you can see, we have seen a low, very low band gap at the gamma point. So, can we go lower? In the figure B, as you can see, we have calculated a spin orbit for all the direction, that is x, y, z direction. So here, in component, in plane SOT component are x and z component, and here, as you can see, the z component is lower and x component is also given a 10 to the minus 3 coordinate order value. But here at the outer component, we are seeing a non-zero variation of the SOT component at as we go along the y component. So here the basic idea of the my topic is that in bulk component, in the bulk based SOT devices, we are not able to get a sizable component of the outer plane SOT, but using 2D materials we can get we can actually remove this issue, and by using a DFT calculation, we have seen that the Y component is indeed existing in the can be indeed be induced in the materials. So thank you. That is the gist of matter.
Okay, next.
Hello, sir. I'm audible to you? Sir, I'm audible? Okay.
Yes, go ahead.
Hello, everyone. I'm Riya Vadhva. The title of my poster is Highly Sensitive MOS to RES2 Heterostructure with Self-Driven Broadband Photo Detection. As you already know, the 2D MOS2 is a potential 2D semiconductor because of their auspicious properties, so that it can be used in a various optoelectronic applications like photodetector, LED, transistor, and solar cells. Now I'm working on the photodetector application, which require 5S requirement. That is high sensitivity, high signal to dark current ratio, high speed, high spectral selectivity, and high thermal stability. Now, to the fabrication of high performance MOS2 photodetector, we came across the following challenges. That one is the low absorption due to the atomical thin nature of MOS2. The limit of the photo detection range because of their band gap, which is varying from 1.2 to 1.8 electron volt. And the one is the most important is its trade-off between responsivity and response time. As you can see in the following graph, if we found the high responsivity, we get the high response time as well. So the need for the today's era is the balanced photo detector, and also the recombination of charge carrier is very high in a single material. So we move forward to the 2D heterostructure due to their enhanced photo detection range and the favorable band alignment because of the ease of charge transportation. So in figure 1, there is a schematic representation of our experiment. We firstly grown the vertical aligned MOS2 on SiO2 coated silicon substrate. Then we patterned the gold electrode on top of it and drop cast the RES2 solution, and we made the fabricated MOS2 RES2 heterostructure. In the resultant discussion section, you can see the Raman and photoluminescence spectra of individual MOS2 and their heterostructure, and results shown that the after coated RES2 nanosheet on top of MOS2, we found the shift in Raman as well as PL that describe the interlayer coupling between them, and also the downshift in Raman spectra implies the tensile strain after coated the RES2 nanosheet on top of MOS2. Figure 3 represent the SEM and photocurrent response of the single MOS2 and their heterostructure, and we found that in case of heterostructure, the photocurrent is drastically enhanced because of the formation of favorable band alignment. Figure 4a represents the comparative photocurrent of pristine MOS2 and their heterostructure. In figure, you can see that the photocurrent is drastically enhanced in case of heterostructure, and also we found the transit photo response as well. We calculate the responsivity and detectivity for the both of the samples, pristine as well as their heterostructure, and we found the huge investment in their responsivity detectivity as well. We also calculated the response time of
both of them sample by fitting curve using single exponential function, and we got the response of two order, magnitude of two order reduced in the response time. We got the tens of millisecond in the case of heterostructure, while we got the hundreds of millisecond in case of the pristine MOS2 sample. Not to, also we got the self-powered response of MOS to RS to heterostructure. In case of pristine, we don't get that results. So here is the self-powered performance of IT characteristics of starting from 400 nanometer to 1100 nanometer. We also calculated the response time, which are further in the order of milliseconds. And also we got the huge responsivity, that is 1.3 ampere per watt in case of self-driven. So that we don't apply any bias, still we get the high responsivity and detectivity as well. This huge responsivity and the self-powered response is maybe due to the formation of favorable type 2 alignment in case of MOS2 and RES2 heterostructure. Now come to the conclusion point. We first made the high performance sensitive heterostructure with self-driven photo response, which is got the responsivity of 34.13 ampere per watt, which is approximately 18 times higher in case of the single MOS2. The shift in Raman and PL spectra implies the interlayer interaction between them, and these result corresponding due to the favorable type 2 formation of band alignment. Thank you.
Next.
Yeah, hello. Hello, sir. I'm audible?
Yes.
Yeah, I'm audible. May I start, sir?
Yes, go ahead.
Yeah, myself Shatrudhan Palsania from IIT Guwahati. So my topic is CVD processed graphene using liquid hydrocarbons as supercapacitor electrode. So I directly come on my work experimental section. We are using here as a liquid hydrocarbon benzene as a precursor material without any kind of carrier gas. So after deposition, so we found that the graphene film has been deposition over the copper foil. The foil thickness approximately 0.025 micron. So after deposition, this is the transfer method using the characterization section. After transferring all the insulator substrate and the glass substrate after the deposition, the graphene from the copper substrate. So these are the microscopic images. The bluish region indicate that the graphene has been deposited, but the red indicate that graphene is the little bit in multi-layer thick. So undistributed region that's directly shown in the Raman characterization that graphene is somewhere is defect because of the undistributed region of the graphene. Somewhere is thick and somewhere is the thin layer. So after deposition the graphene conformation, we goes to the result section that electrochemical performance of the device. We fabricated a symmetric supercapacitor device using the same technique. After deposition, two similar thin films, and they sandwiched in a particular using a particular substrate. That substrate will directly utilized as electrochemical performance matter. So these are the CV performance, and one is the galvanostatic charge discharge performance. So there are the two different capacitance calculations. So one is the 1300 approximately, and third one, another one is the 350 farad per centimeter cube. These are the volumetric capacitance actually. So after calculation, we find that the huge difference. There is a big difference. The difference directly denoted by because of the material stability. That stability has been precisely calculated using the galvanostatic charge discharge method, and this is the stable value around 350. So based on these parameters, we've been calculated energy density against power density. So our characteristic measurement of energy density around 70 milliwatt per hour against 7155 watt per centimeter cube. That is the power density. So in future application, we are achieving that the miniaturizing the surface area of the substrate that can be enhancing storage capability of a device. That storage capability could be utilized in the flexible or wearable electronics. Thank you. Hello.
Okay.
Yeah.
Do you have any more?
Yes, sir.
How many left?
Sir, 3 or 4. 3, sir. 3 more. Okay, sir.
Go ahead.
Munindra, are you there?
This is which poster number?
Poster number 51, Munindra.
Okay, go ahead. He is not there, so no problem. Next.
59, Chanchal.
Any?
Hello?
Chanchal?
Yes, sir. Sir, am I audible?
Yes, yes.
Uh, Here we have today my post presentation on growth of beta INTOC3 temperance using pulse laser deposition technique for photo detection application. Indium selenide is a group 3,6 element, which has various polymorphs and out of its various polymorphs, beta INTOC3 has a high carrier mobility and absorption coefficient. That's why it is suitable for the optoelectronic properties, and also because of various polymorphs, it is favorable for phase change memory applications. So we have grown beta INTOC3 films on various substrates using Corning glass substrate and silicon substrate. So we have found that when we deposit the films using these parameters, we found that from XRD, we found that this films are highly CXS oriented with 009 plane, but for Corning glass substrate, there is an excess of selenium, which is shown in the Raman spectra, which shows the characteristic peak for beta INTOC3, but with a peak for selenium at 143 centimeter inverse. Whereas when we deposit it on silicon substrate, there is a mixture of phase with beta INTOC3 and gamma INTOC3, where gamma INTOC3 is the phase of indium selenide. So when we do its electronic characterization, we found that for Corning glass substrate and with the gold as electrodes, which are deposited using e-beam evaporation, we found that for Corning glass substrate films, we found that there is an ohmic contact with the films with gold electrodes, and when we used the gold electrodes with silicon substrate films, we found that there is a Schottky contact, which is a rectifying contact. This is because of the ohmic contact, maybe because of the various defect levels introduced between the band gap due to the excess of selenium, and where in case of silicon, the films are of mixed phase beta and gamma INTOC3. So this be because of the formation of junction between the N-type indium selenide mixed phase. So we conclude that whereas the dark current is very high because of the defect levels, and so we suggest that with varying parameters, we can find the high photo detection in if so which forms this rectifying behavior can help us for the photo detection application. Thank you. Hello.
Next. Sneha, are you here? This is which poster number?
Poster number 1110. This poster is from Bio Group. So actually, this poster is also remaining yesterday's. That's why they shifted in our session.
Okay, so do you have any 2D materials poster? Then we can go to the bio poster.
No,
Yes?
only this one is remaining. Yes.
Okay, go ahead.
Am I audible, sir?
Yes, yes, go ahead.
Good afternoon all. This is Neha. We report on a type of organic electrochemical transistor called bioresistor. So what is an organic electrochemical transistor? It's a transistor with three terminals, gate, drain and source, in which drain current is controlled by injection of ions from an electrolyte into a semiconductor channel. The injection of ions is achieved by applying voltage to the gate terminal. So what is the difference between bioresistor and other types of OECT? In bioresistor, plant sap acts as electrolyte. So coming to the construction of bioresistor, typically channel of OECT is made of a conducting polymer. Most popularly used material as conducting polymer is a chemical called P.PSS. The key parts of a bioresistor are cotton thread functionalized with P.PSS, which acts as channel, with either ends of the thread acting as source and drain terminals. And there is a thin silver wire which is used as gate terminal, and there's a spacing of about 5 to 9 mm of the gate terminal from the cotton thread. So the plant sap in between the thin silver wire and the cotton thread will act as electrolyte in the transistor. So why do we want to monitor drought and salinity stress? Drought and salinity stress or abiotic stresses that significantly affect crop yields worldwide. So what is this abiotic stress? Abiotic stress is negative impact of non-living factors on living organisms in a specific environment. So drought stress and salinity stress are two most important abiotic stresses on plants. So focus of my work is use of bioresistor to monitor these stresses. P.PSS is a degenerately doped p-type system. In this system, there are fixed negative charges, that is sulfonate anions, which exist along PSS background, and these are compensated by positive holes along the p-dot polymer chain. So because of these very mobile positive holes, when we apply voltage drop across source and drain, VSD, we get a current ISD. But on applying a potential VGS, and because the gate electrode is immersed in plant sap, when we apply potential VGS, positive ions from the plant sap will penetrate into P.PSS channel in order to maintain charge neutrality as shown in the equation. And because of that, current is going to get lower because the ions from the plant sap are larger ions and they are less mobile compared to the positive holes. So for the same electric field across source and drain, when I apply an voltage VGS, current ISD is going to lower. This OECT, this P.PSS based OECT is a depletion mode type P-type device. So by keeping VDS constant and varying VGS, I have observed IDS with respect to T. Clear shift in transfer characteristic is observed in stress plants as compared to healthy plants. And the ions that we are talking about in plant sap are sodium, potassium, calcium, and magnesium ions. All these four ions are key players in drought stress, and sodium ion is key player in salinity stress. So when drought stress happens, inhibition, absorption of Ka plus ion is inhibited and absorption of sodium ion is increased. So what happens is more positive ions from plant sap will penetrate channel of bioresistor. So lesser availability of holes for current conduction. So lower values of ISD are observed in the case of drought stress plants as compared to healthy plants. And we work with turkey berry plants for the experiments. And in the case of salinity stress, higher concentration of salts hampers the transport of magnesium, calcium, and sodium ions into plants. So lesser positive ions from plant sap will penetrate channel, so more availability of holes for current conduction. So comparing drought stressed and salinity stressed plants, salinity stress plants have higher values of IDS. And the trend followed by the current waveform is same in both healthy and salt stress plants, the same, similar for different values of VGS. Slope is higher for healthy plant as compared to salt stress plant. Slope of healthy and drought stress plants are comparable. There's not a significant difference. And for higher values of VGS, the current falling is also like the transient settles down as we time goes on. And for higher values of VGS, the current fall is also lessened. So as conclusion of my work, I want to tell that from preliminary studies, it's clearly evident that bioreactors capable of detecting changes in concentration of the various ions in a plant during drought stress and salinity stress. So more detailed experiments we are carrying out to understand the phenomena in further detail. Thank you. Hello. Hello.
Hello. So
Was
now
I
our
off?
poster session is over.
Hello.
Hello. So can you start the session? So
Yes, sir.
okay. Okay. 1 second. I think. Hello and welcome to this final session of the day on MEMS. So we had wonderful 2 sessions, and this session promises to be scintillating as well. So we have 2 invited talks during this session. So I think first talk is by Professor Hirotaka Hida from University of Kobe. Professor Hida received his BS, MS, and PhD degrees in mechanical engineering from Nagoya University, Japan. And previously, he was assistant professor in micro nanosystems in Nagoya University, Japan. And 2013, he's been with the Department of Mechanical Engineering at Kobe University, Japan. So his current research interests include MEMS fabrication techniques, microtasks, MEMS sensors and actuators. And so today he's going to be talking about plant cell on chip devices. So this is very exciting area of research where organ on chip, plant on chip, these technologies promise to revolutionize many fields. And I'm very eager to what he has to say. So with that, I leave the floor open to Professor Hirotaka Hida. Thank you, sir, for being part of ICEE. Yeah. Hello?
Oh,
yeah.
So thank you very much for kind introduction. And so now, can you see the file?
Yes,
and
we can.
can you hear me? Okay.
Yes.
Okay, so good evening, everyone. So I'm Hirotaka Hida, Kobe University, Japan. First, it is great honor to be able to speak to you. And I'd like to thank the organization committee of ICE 2020, and especially the Professor Prempal, India Institute of Technology, Hyderabad, for kindly inviting me to speak here. My presentation today is about the microfluidic devices in plant biology. This application area is currently at growth stage, but it may contribute to the improvement of the agricultural productivity in the future. Here's the table of contents in my presentations. First, I'll introduce a plant on a chip based on a concept of lab on a chip technique. Then I'm going to talk about our recent studies of plant on chip devices, including the characterization of the mechanical properties of the growing roots, such as driving force, and the mechanical stiffness of the growing root. And also I'll talk about the chemical and biochemical assays of the plant by using the plant on chip devices, including the infection process with the microorganisms and the chemical responses of the growing roots. And finally, I'd like to make a brief summary. Okay, let me start with background of this study. The concept of lab on chip was proposed in the early 1990s. Lab on chip devices based on microfluidic platforms have various technical advantages. For example, we can carry out the carry out efficiently chemical or biological assays, reduce the sample amount to the micro-nanoliter level or below. Also, we can analyze the samples with high space resolution on micro or nanometer scale. In the last decade, numerous kinds of the lab-on-chip devices have been developed. For example, the microfluidic device integrated with nanopillar array for DNA analysis, body or organs on a chip to analyze the cells under the controllable environments for drug discovery screening. However, so far, almost all of the lab-on-chip devices have been mainly used in medical science, which is directly related to our lives. Recently, the lab-on-chip technologies are applied to plant science, so-called plant-on-chip. These devices enable us to study plant biology from a new point of view. As you can see here is on-chip assay of pollen tube guidance using microfluidic device to understand the reproduction process of plants. The reproduction process is one of the most important events for the plant, and it occurs inside the plant organs at molecular level. Of course, we cannot observe the process directly, but using the microfluidic devices, we can quantitatively analyze the pollen tubes and guide it by the attractant molecule from the ovules, as shown here. Also, by using microfluidics, we can manage many plants at one time without physical damage and efficiently analyze the phenotyping of the whole plant, as shown in this picture. Here, I'd like to focus on the root under the ground. Roots are essential organs for almost all kinds of plants to take up water and nutrients from the soil. The plants cannot move by themselves, thus they need to control the root growth under various environmental conditions, such as physical, chemical, and biological factors, including the microorganisms surrounding the plant. This list shows the factors to consider for deeply studying the root growth mechanism. For example, the driving force, mechanical stiffness of the growing root, physical interaction between the root and the soil. And also, we have to consider the biological and biochemical factors. For example, the interaction between the plant and the microorganisms. And also, the chemical responses is one of the most important factors. So in this slide, I'll talk about how the root elongate in the soil briefly. The roots grow by a cell development process in elongation region near the root tip, as shown here. Here is the cell expander part. On the other hand, maturation region, the upper part of the roots does not elongate. Sorry. This graph shows the relationship between the strain rate and the position of the root. The elongation region generates driving force for grow into the soil continuously. Thus, it can be thought as an actuator in plants. And this slide shows a simple physical model of root growth in the soil. There is a macroscopic view of the growing root. In the growth process, the mechanical stress or compressive force is applied on the roots in axial and radial directions due to the physical interaction with the soil. The compressive force in axial force directly disturbs the root growth. Also, the radial force, which is gradually increased with the depth of the soil, it also hinders the root growth. So let me move to the microscopic view. The actual physical conditions of the soil is heterogeneous, and there are numerous air gaps as shown in this picture. Thus, the root is often partially fixed, and the other part is free as shown in this picture. In case that the growing root faces to a stiff soil, the root is bended due to the buckling. This phenomenon depends on the stiffness and the dimensions of the root, but it is difficult to measure these mechanical properties, the dimensions of the root, and the mechanical stiffness of the growing root. Thus, the mechanisms of the root growth have been mostly still unclear. To quantitatively analyze root growth mechanisms, our research group has developed several kinds of the plant-on-chip devices. Firstly, I'd like to talk about mechanical characterization of the growing roots, a physical interaction in axial direction with soil. This slide shows the schematics of the micro device for the measurement of the driving force and analyzing the physical interaction between the soil and roots. We fabricated the silicon-based microchannel integrated with a monolithic force sensor as shown in this picture by using the micromassing process, including the photolithography and the deep reactive ion etching process. In the experiment, a plant seed is directly placed on the device and grown. As on this photo, we can clearly observe the behavior of the growing roots and the capturing the root by the force sensor. By measuring the displacement of the force sensor, we detect the driving force generated by the root growth. So I'd like to show the moving pictures of the growing root. The growing root is captured the force sensor and continuously growing against the physical resistance by the mechanical sensor. So again, we observe the twist and buckling of the root that occurs, and finally the root growth stopped. This slide shows the experimental result of the physical interaction assay of the growing roots. From the results, we successfully measured the maximum values of the driving force by using the developed method. This on-chip method can be used to evaluate the physical characteristics under various conditions, such as nutrient concentration, light intensity, temperature, and so on. So next, I'll talk about the physical interaction in radial direction. This slide shows a schematic view of the microchannel device having a micropillar array. I'd like to talk about the measurement principle briefly. The plants are grown on the device directly, and the root grows into the gap between the micropillars as shown in this picture. In case the micropillars are deformed by the growing roots as shown here. Now, considering the local deformation on the contact area between the root and the micropillars, the tip displacement of the pillars depends on the stiffness of the roots. Thus, we can estimate the stiffness of the root in radial directions by measuring the displacement of the micropillars. We numerically evaluated the relationship between the root stiffness and the tip displacement of the micropillars based on the finite element method. In the simulations, we regarded the root as an isotropic elastic body. This slide shows an example of the simulation result. Since the Young's modulus of the root is set to 2 megapascal, the tip displacement of the micropillars was about 50 micrometers. Comparing with this result, the tip displacement of the micropillar is less than half when the Young's modulus of the root is set to 0.1 megapascal. From the simulation results, we confirmed that the displacement of the micropillar is decreased by decreasing the Young's modulus of the root. This graph shows the relationship between the Young's modulus of the root and the displacement of the micropillar based on the simulation result. From this result, we derived the equations for estimating the stiffness of the root in radial direction. In these equations, D means the diameter of the root, and delta means the tip displacement of the micropillar. So by using this method, we experimentally analyze the effect of the nutrient conditions of the stiffness on the root. As for the root diameter, there were no significant differences. In contrast, a stiffness in radial directions of the root under the low concentration nutrient is less than half, comparing with that under the normal concentration nutrient. I think it is a very interesting result, and we can deeply understand the chemical effects on the mechanical properties of the growing root by using this method. This method using the micropillars can be applied to evaluate the mechanical stress test on the growing root. We carried out the long-term observation of the root under the high mechanical stress on the root and observed the reconstruction of the root at the cell level as shown in this picture. Normally, the shape of the cell in the root is elliptically, but the cells are deformed into the like a square shape. This is occurred by the reconstructions of the microfibrils pressed around the cell walls as shown in this picture. Okay, then I talk about the biological assay using microfluidic devices, interaction with microorganisms, plant parasitic nematodes. Plant parasitic nematodes are harmful insects to crops and inhabit the soil in region worldwide. Root knot nematodes one most damaging plant parasitic nematodes are very small organisms, less than 1 millimeter, but causes significant damage to agricultural crops by invading plant roots. The crop damage caused by the plant parasitic nematodes is estimated at $100 billion annually. As you can see here is the illustration of the infection process of the plant parasitic nematodes. The nematode moves into the root from around the root tip and migrate. Then the nematodes induce the differentiations from root cells into giant cells. They function as feeding cells for the nematodes. This root reconstruction events affects nutrient and water uptake in the plants. To prevent the breeding of the nematodes, the growth of giant cells should be inhibited. This is a technical challenge. For example, can we control the function of the giant cells by applying the external stimulus, such as physical stress? To understand the infection process of the plant parasitic nematodes, we developed the microfluidic chips as shown here. This device has micropairs inside the microchannel. By using this device, we can efficiently capture the infected root and apply the mechanical stress onto the root to clarify the effects of mechanical stimuli to the giant cells. We also established the real-time observation system for analyzing the infection process. The samples and devices are inside the incubator to control the temperature and light intensity, though the automatic photographic system is installed outside the chamber. We can clearly observe the root behavior through the glass door of the incubator by using this imaging system. And I'd like to show the moving images of the infection process. So we confirmed that the growing root is gently confined between the micropairs and observed enlargement of the root due to the nematode infection. This is a magnified view, and I'd like to show the magnified moving images and enlargement of the root mentioned here. So from the observation results, we quantitatively analyze the growth behavior of the infected root. This slide shows the time course of the root, length, and the diameter of the root. We can see the elongation rate temporarily decreased twice, around 30 hours and 50 hours after the injection to the nematodes. At the second time, around 50 hours, we find the visualizations of the root node as shown here. On the other hand, at the first time, around 30 hours, we cannot directly observe the reconstruction of the root. I think it is very interesting, and I'm not sure, but this behavior may correspond to the starting the infection process caused by the plant parasitic nematodes. And finally, we evaluated the effect of the mechanical stress to inhibit the growth of the giant cells. By comparing with the result without applying the mechanical stress, we confirm the enlargement of the root node was inhibited by applying mechanical stress using a micropure. I think it is too early to conclude because of the lack of experimental results, but I confirm three we would be able to deeply study the interaction between the plants and the nematodes by using a proposed method. Finally, I talk about the biological assay using microphysical devices. About the chemical responses. Chemical responses or tropism in plant to the surrounding environment conditions, including light, gravity, water, and so on. For example, the roots grow along the gravity positively, and the stems, which are part of the plant above the soil, grow to the light source. It is thought that the plants efficiently obtain the resources from the surrounding environments owing to the tropism. Most recently, the lateral or secondary roots of the rice are attracted to the high concentration nutrients as shown here. This phenomenon is so-called neutrotropism. However, these experiments were carried out on conventional agar plate assay, thus it is difficult to quantitatively define the conditions to cause the neutrotropism so far. So we developed a new method to analyze the tropism using a microfluidic device. Here's a schematic view of the microfluidic tip for analyzing tropism with the rice roots. The microfluidic device consists of the analysis chamber, the sum of the microchannels for creating the chemical gradient inside the chamber, and the micropillar for guiding the primary root. The lateral roots, which are analytical objects, grow out the primary root. We fabricate the device using the typical soft lithography process. So as you can see here is a schematic view of the experimental setup. The device is tilted from horizontal plane, and the primary root is located into the gap between the micropillar. After the growing of the lateral root from the primary root, a low and high concentration nutrients medium are loaded into the analyzer chambers as shown here. Then a concentration gradient is created inside the chamber due to the diffusion. We can define the area having the concentration gradient as shown here, thus analyze the relationship between the root growth behavior and the nutrient conditions. This slide shows the visualizations of the concentration gradient inside the microfluidic device with red dye. We experimentally confirmed that we can stably maintain the concentration gradient inside the microchamber at least a few hours. Under the same condition as the nutrient assay, the primary root is placed in the device, and the device is tilted from the horizontal plane. This is a magnified view of the created concentration gradient. So finally, we carried out the tropism assays on the microfluidic device. In this experiment, we used two types of the concentration variables as high and low nutrients concentration. Now to visualize the area having concentration gradient, this photograph overlapped with translucent hot as shown in previous slide. So 2 hours after the concentration gradient was created, the root tip is drastically bended in the direction to the high concentration area. This result indicates that the lateral roots of the rice have their own chemical sensors to efficiently take up the nutrient, and we can analyze the So now, we are carrying out carrying out the analysis by using this method. So let me summarize my talk. In this presentation, I'd like to introduce some of our recent studies about the plant-on-chip devices for studying the growing roots, such as the mechanical and chemical biological properties of the plant. And in the future, I think the gained knowledge might contribute to the improvement of the breeds and crop productivity. So I'd like to thank to all of the collaborators and the master and bachelor students in our group. And thank you very much for your kind attention.
Okay. Thank you, Professor Hida, for your wonderful talk. If anybody has any questions, you can type it in the chat box and I can read them out. Okay, so anybody has any questions, please type it out in the chat box and then I can read it out to Professor Hida. So I have a sort of a basic question. Is PDMS as a material kind of a good material for plant growth? Usually we see when we put cells in PDMS, they don't like the surface, or sometimes they don't like the chemical that leach out of PDMS. So do you see that kind of thing happening, and how do you mitigate it?
So your question is about the materials of the microfluidic devices in our study.
Yeah.
As the reasons we choose, your question is reasons we choose PDMS as a materials.
I guess my question is, PDMS, of course, a very attractive material, but do you see any adverse effects of choosing PDMS as the material? Either the physical properties that, it sticks to many polymers, or the chemical properties. Do you see any adverse effects of using PDMS? And is there any way to make these structures out of, say, some other material, or coat with, for example, BSA is coating used in cell studies, so that kind of thing for plant-based assays.
Sorry, so I cannot catch your question. So
okay, that's fine. So any other questions from the audience? Okay, if not, then let's thank the speaker. Thank you very much, Professor Hida, for your illuminating talk. So our next speaker is Dr. Cyprian Iliescu. I hope I pronounced your name correctly. So Professor Iliescu is from the National Institute for Research and Development in Microtechnologies, IMT Bucharest. So he's received his BS and PhD degrees from School of Mechanical Engineering, Polytechnic University of Bucharest in 1989 and 1999. So while pursuing his PhD, he worked at Benessa, where he was involved in the design and fabrication of pressure sensors. Between 2001 and 2003, he worked as a postdoctoral fellow at NTU and was involved in projects related to microphone wafer level packaging of MEMS devices and RF micro relays. So between 2003 and 17, he was with IBM Singapore as a research scientist and senior research scientist. He was also visiting PI at IMT Bucharest, so where he's now based, I guess, and where he set up his micro and nanofluidic lab. He's a member of Academy of Romanian Scientists. His current research projects relate to microfluidics for drug screening. So I think with that, I'll leave the floor open to you. So he's going to talk about microfluidic strategies for self-assembled nanoparticles. So, okay. So just a note to the audience, if you have any questions, you can type it in the chat box. We won't do live Q&A, but at the end of the talk, I'll pose the questions from you to the speaker. Yeah, thank you. So Cyprian, you can probably start.
First of all, thank you for the invitation to this conference, and thank you also for the nice introduction. So I will try to summarize my work and my teamwork in microfluidics for self-assembly of nanoparticles with a special focus on DNA compaction. This is our first. I will give you a short introduction, then I will talk about polyelectrolyte surfactant interaction using hydrodynamic flow focusing. Then I will describe two methods that we develop for DNA compaction using microfluidics. And if I have time, I will also present other work that on this direction using microfluidics for nanoparticles. Finally, I will conclude. Let me give you first a motivation of my work.
Cyprian,
you know that in the
your
last
slides. Sorry to interrupt you. We cannot see your slides. Probably need to share. Not sure why we are not able to see your slides. Can you try to share your screen?
I will share again.
So yeah, so now we can see. Yeah, so probably can.
Yes.
Yeah,
It's
so
okay now.
Yeah, you can go to full screen. Yeah, I think
Yeah, now
this
you're
is good.
perfect.
Thank you. Yeah.
So you know there is a strong development in gene therapy to treat, prevent, and control diseases like cancer, HIV, Alzheimer, Parkinson. And in this direction, there are two main directions. One is the viral vectors that give some side effect, like immunogenetic response. And there is also collateral effect. Maybe some research on viruses can affect in our days also. The second is are synthetic vectors. Synthetic vectors that here we have three main groups. Encapsulation, so you can package, for example, RNA and DNA in nanoparticles, polymeric nanoparticles. You can do by absorption on gold nanoparticles or on magnetic nanoparticles. The last method is not so good because you expose the nucleic acid to enzymatic degradation. When you do packaging, usually you work with organic solvents, and this induce some shear stress, and also they are not good for not so good for when you make the transfection to the cells. We look for this electrostatic interaction, but here the main problem is that the kinetic of the system is not so stable. So with other things, when you use this electrostatic interaction to do synthetic vectors, you have a large amount of particle that you can not use it. There's a big dispersion of the particles, of the size of the particles. So we try to approach microfluidic in order to control this kind of electrostatic interaction. And regarding this and show you an example here, polymer DNA nanocomplexes. The size of the diameter of the particles reported best is 263. Polyethylene imine DNA complex is around 500 nanometers. So this kind of dimensions are very large for transfection. Usually to go through the bloodstream and go to the target cell, you need particles that are below 200 nanometers. 200 nanometers is a maximum value that for transvection. So when we start working, we start first with a model, and we start studying polyelectrolyte surfactant interaction as a model for DNA compaction, because DNA or RNA are polyelectrolytes. And I will talk a little about this first set of experiment that we've done. So for this, we make a very simple devices. We use glass silicon technology for microfluidics because it was more stable. Initially, the device was made in PDMS, but after a few experiments, we move it back to glass silicon. The main problem was related to the reliability of the device. PDMS device we must change a few hours, while for this glass on devices we use it for one device for few hundred experiment, and can be also clean. So this is the device. It's a glass slide, and the bottom it's a silicon one. The channels are performed deeper IE in the bottom device. You see a silicon with photoresist on both sides, photoresist mask on both sides. You edge the microfluidic channel from one side. You put on with wax on a dummy wafer, and you make the inlet and outlet from the other side. Finally, you can put grower oxide to make all the surface hydrophilic, and you bond to a glass. A very, very simple process for MEMS fabrication. And this is what I mentioned about. We have a lot of PDMS chip that we fabricate for this experiment, and we have a big headache, and we have one silicon device that we use, in fact, for we publish practically 2 papers using the same setup. The testing setup that we use to materialize here it's opposite, in fact. The polyelectrolyte is flowed by the main channel, the central channel, while the surfactant is from lateral. And at the end, we have a reservoir. Or it's controlled by flow. This is the nice part of the system that you don't need to adjust all the time the pressure, and the system control all the flow through the device. Now, regarding the reaction itself, it's a two-step reaction. In fact, it's an electrostatic interaction between the head of the surfactant, that's positive charge, and the negative chain of the polyelectrolyte. And this surfactant have hydrophobic tails. So the second interaction is between these hydrophobic tails that compact the particle. So in this way, it forms the device. And why we hope to get uniform results is because on the microfluidic setup, using this hydrodynamic flow focusing, in fact, you have a very uniform exposure interaction, electrostatic interaction between this stream with polyelectrolyte and the stream with the surfactant. So, in fact, we really uniform results here. The TM image was 80 nanometer nanoparticles. They're hexagonal nanoparticles. And I will show you later, in fact, they are flat particles. What we get, it's around 50 nanometer nanoparticles. We were very happy on this result, and we say, let's try with DNA. So, just we replace the polyelectrolyte with DNA. We keep the same surfactant to be sure that. But the results were not so good. When you do nanoparticles, in order to have good results, you look at the poly dispersion index. This polydispersion index must be below 0.2 to have a uniform size particles. They are measured, this hydrodynamic diameter, for those who are not familiar, is measured with a system called DLS, dynamic light scattering. So we try to vary the DNA concentration, and you see here that particles are up from 200 nanometer up. We try to modify the surfactant concentration. We have similar results, in sense not so good results. And if you look, when you plot this, you see that in most of the cases you have two peaks instead you have two population of nanoparticles. Sometimes you have three peaks. This region is with so-called small particles with micelles. It's made only by a surfactant. Okay, so we start to ask why we get these negative results, and the main reason is the linear charges of DNA, that it's 5.9 electron per nanometer. That's larger than the polyelectrolyte that we used before. So we look for another solutions to do this compaction, also using microfluidics. And one solution was to make on-chip solvent exchange. The other solution was to use a hydrodynamic flow focusing through a diffusion buffer. So I will describe this two method more. In this solution was solvent exchange. What happened? We divide these two interaction that we have, the electrostatic interaction and the hydrophobic interaction. We separate them. So we put DNA and surfactant in ethanol. So when you put this and you have the concentration below 10% of ethanol, there is no hydrophobic interaction. It's only the interaction between electrostatic interaction here. So after this, we put water from lateral side and we remove slowly the solvent. So in fact, the concentration of the ethanol in this stream will, in the mainstream, will decrease, and at the end will be uniform. So in this way, you allow this electrostatic interaction, and the particles start to compact. So this is a simulation because we have a certain length of the channel, and we want to know that at the end of the channel, we have a uniform concentration of ethanol. Was done by one of my students. So it's more directly is presented here. We have the value in the middle of the channel, in the center, at maximum value and minimum value. So you see that finally, after 15 millimeters, the length of the channel, the concentration of ethanol is almost similar. Now we start to do some experiment, and we vary, for example, we vary the DNA concentration, and we look for the variation of polydispersion index and the hydrodynamic diameters. If you can see on this graph, you don't have a very strong variation of the size of the nanoparticles. For the experiment that we done before with the polyelectrolyte, the beautiful part was that we can tune the size of the particles using the parameter of the flow or the concentration, and also the concentration. Practically, using this kind of solvent exchange, the is imposed by the concentration of the surfactant and DNA that you have in the initial solution. You cannot vary too much using flowing parameters. So this is a function of surfactant, and also we look for the influence of flow rate ratio. There is somehow normal, no influence. As long as you have an equilibrium or you have the concentration of ethanol below 10% at the end of the process. Then we also try a long chain DNA to see how this influences the results. Sure, you have a long DNA, you have a big particles. Usually you can get hydrodynamic diameter around 200 nanometers, even for this DNA that is quite large. We can also change the surfactant, and you have a surfactant, bigger surfactant molecule, you have also bigger particles. We try also different mixing procedure. For example, we try also side flow. We try this kind of double sigma mixer, very common in fluidics. We try mixing by stirring, bulk mixing, but at the end we conclude that for this central focusing we get the best results. And here, yes, here are some images with the particle. You can see that they are quite uniform. Sometimes the particles in the TEM arrange on vertical, they're flat particles. And here we need a chemist, computational chemist, to explain how this structure is generated. In fact, one of my collaborators from France is working on this aspect. Okay, this was the method, but for gene transfer, we have a problem because we use ethanol, and it's a strong solvent, and it's not so good for cell transfection. And the question is, okay, can we make this nanoparticle in a manner that we avoid using ethanol, so we will be more cell-friendly for this kind of application? So we try using diffusion through a water stream. So what happened? We have 3 inlets here: DNA 1, water 1, surfactant. So what happened here? The surfactant and DNA will diffuse in water. So the surfactant will interact one by one with the DNA. The surfactant will diffuse faster because it's a small molecule comparing with DNA. So I will show the results that the driving let's say force that dictate the size of nanoparticles have more influence in setting up the dimension of the particles. So this was the idea. It was another chip that we fabricated in the same technology. A little design was a little modified. And here are the results. First, sure, we start to vary the flow rate, water flow rate, and we start from 0, normal. We go to 55 microliter per minute, and you'll see the pulse and constant with huge PDI when the flow rate is 10, maybe till 25, 30. And from here, you see that the of PDI indicated here are very uniform, are below 0.2. The value of the hydrodynamic diameter of the particle, it's almost decreasing with the water flow rate. So we start to see tune the flow rate, and we vary also, as I mentioned, the DNA the DNA flow rate, and you see here that DNA concentration doesn't affect too much the size of the particle, as I mentioned before. We also play with a little with the surfactant, and when we play with the surfactant, we have the surprise that we can get very nice particles, If you see here, the nanoparticle size is around 30 nanometers, and it's in a quite good range maintained. This means that we have almost one DNA on one particle. It's difficult to predict, but this is the expectation. Maybe after my colleague will finish the simulation, we'll know if we have around one DNA per particle. And this is an image, TM image. My collaborator made it in France. The image was taken with TM after 3 weeks. So there is not so much variation in terms of TM. It's very important for gene therapy application. Initially, on BLS, the particle was around 30 nanometers. Here are 37, so after 3 weeks, there's a certain increase in particle size. Okay. If time, I can present also some other works. Was chip. This time we use a PDMS chip for making polysulfone nanoparticle for a bioimaging application, and the fabrication doesn't insist. It's just casting of PDMS on a silicon mold and then bonding. The setup is somehow similar. We dissolve polysulfone in NMP, and from the other channel we have water. So it's a condensation, if you want to. So we also vary the flow rate ratio and measure the hydrodynamic diameter. So we have a very, very nice fish. We control also the PDI. You see for some value are quite good, quite uniform particles. And also we vary the concentration of polysulfone, and we measure hydrodynamic diameter. We try different focusing methods. Central focus is side focusing. There is not a big variation on this. We try this kind of fast missing, and here are not so good. So this kind of nano precipitation using flow focusing works better than this turbulent mixing. Anyway, strong mixing using microfluidic mixer. We also play a little with cells here, and here, for example, is the graph when we use water as solvent, and when you use PBS or medium, cell medium, DMEM. So when you use DMEM, the size of the particle is smaller. That's a good thing. Then we check the cell viability. This is the control. So this is when we add nanoparticles. So the effect of nanoparticle on cell viability. And it's an image when we take these images for when you use the cell for bioimaging the cell, the nanoparticles attached to the cell, so we can have a fluorescent image the cell. Future work. The main problem with this microfluidics is that you can get is through very nice nanoparticles. You can control very nice the size, but you need to scale up the process, because what you do on a very small channel, you cannot use it in industrial way. So we must think of the method, and this we are working now to scale up the process to make a real microfluidic nanofactory. We have also some collaboration with Charlotte Hauser from KAUST. She worked on peptide, and now we have a common paper on making peptide nanoparticle microfluid. Further, we'll go to peptide DNA, because peptide is more biocompatible material, contain amino acids, and is not recognized by the body. This kind of surfactant that we use is very nice, but is not so suitable for study. And we plan also a collaboration with Igor Chima, my ex-colleague from now it's Cancer Research Center in Heidelberg, for some transfection study. With this, I will conclude. The main thing is that this hydrogen flow thing give you a very good and uniform nanoparticles and can be used very nice. Sure, I mentioned the limitation about scaling up with a very good polydispersion index. And there are results that, as I show in the first slides, that cannot be achieved with the classical method. Size of the particle, DNA compaction around 30 nanometers, it's a really good performance. With this, also, I want to thank you for your attention, and if there are questions, I am open to respond.
Okay, is open to questions. So while people type in questions, I can ask my question. Firstly, very illuminating talk. Thank you for agreeing to be a speaker here. So my question has to do with, initially you said there are plasmid and viral vector-based methods and these particle-based approaches. So in the plasmid-based approach, once it enters the cell, the DNA is sitting as a DNA itself. Whereas in nanoparticle, it's stuck to the nanoparticle. So I'm not sure how well it will be transcribed by the cellular machinery. Is there a way these particles are engineered so once inside they dissociate or something like that? I mean.
Yes, that's why we intend to use more now peptide. But first of all, it's the charges that are around the particles. Viral vector have a nice thing that that they inject practically the RNA inside or DNA inside the particles. With this electrostatic interaction, the charges on the surface of the nanoparticles help the endocytosis. So that's the beautiful part of this electrostatic interaction. Sure, there need to do more stuff inside how this is released the DNA, but from the previous work, what I know, there are no problems in terms of this. They look for DNA now in gene therapy because they want to use plant plasmid DNA. This is the standard of for transfection.
Right. So there's a question by Mr. Akhil Ramesh. He has asked, can we isolate DNA using these type of devices? I'm not sure what he means by isolate DNA, but I guess you can. So that's the question.
I guess the question is if you can compact the DNA that you find, for example, in blood or in other biological fluids. Theoretically, if you put surfactant there, you can electrostatic interaction, so you can it can be done, but it's depending from case to case.
Okay. So I mean, but theoretically, you could use this as a sort of sample prep step.
Sure.
Okay. So I guess that was the question. And if there are any more questions, so if not, then let's thank the speaker. Thank you very much, Cyprian. It was great to have you here. And if somebody has any more questions, you can probably send it to me by email. I can forward it to the author. And if he has time,
Thank you.
Yeah, thank you very much.
Thank you.
Okay. So with that, we are ending this session. Keynote talks will begin soon. So please log in.